Can you see my screen?
Yes.
Thank you. Okay, so first of all, I'd like to thank the organizers for inviting me to this conference and for organizing this excellent conference. My talk today will be on d-instanton contributions to string amplitudes. So I'll begin by giving some motivation. So we know that string perturbation theory can, in principle, generate perturbative contribution to string amplitudes to any given order in string coupling. And you can imagine the resummation of this amplitude can give the contribution from path integral over the steepest descent contour, or more generally left phase thimble associated with the perturbative saddle point. Now, if we can carry out a similar analysis for other saddle points, then that could generate the contribution from the left side thimbles associated with these other saddle points. And if we could do this for every saddle point, then by taking appropriate weighted union of these contributions, we may be able to give a non-perturbative definition of string theory, okay, at least in principle. So our goal today will be to understand the perturbative contribution from a class of saddle points. And those are d-instantons, or more generally, Euclidean d-branes wrapped on compact cycles. The second motivation comes from more practical reasoning that d-instanton contributions play an important role in studying many aspects of string phenomenology. This includes moduli stabilization via KKLT or LVS scenario. And in a given compactification, the computation of Okawa couplings or gauge field kinetic terms often depend on d-instanton corrections. But before we get into these general computations, we should test this procedure on examples where the results are known from various conjecture duality relations. So in particular, one example that has been studied in detail and it has been discussed earlier is two-dimensional string theory. The topic of today's talk will be 10-dimensional type 2B string theory. But you can also consider type 3 or type 2B string theory compactive or Calabi-Yau manifolds. Okay, this is some work in progress with Sergei Alexandrov and Bogdan Stefansky. So let me describe the issues first. The dynamics of d-instantons, including Euclidean d-branes on compact cycles, is described by open strings with ends that are stuck on the d-instanton. And these open strings do not carry any continuous momentum. Therefore, the infrared divergences associated with the zero modes cannot be treated by analytic continuation, okay, which is the standard way we treat divergences in string theory. And in the worldsheet description, these divergences will show up as divergences from the boundaries of the moduli spaces of Riemann surfaces associated with open string regeneration, okay, because these are zero modes associated with open string states. So the strategy that has been successful in earlier work is to represent the worldsheet contribution as coming from sum over Feynman diagrams of string field theory. Then we explicitly remove the zero mode contributions from the internal propagators. And finally, we carry out the integral over the zero modes at the end. And this generates unambiguous divergence-free results for d-instanton amplitudes. However, if we want to compute the overall normalization, okay, which is associated with one loop determinant of open string fields in the instanton background, that requires a somewhat different approach. And this is going to be the subject of today's talk. So we'll illustrate this procedure for a particular class of problems. And these today will involve d-instanton contribution to type 2B string theory amplitudes in 10 dimensions. But I should emphasize that the method that I'll describe is quite general, and it applies to any Euclidean d-brane in any string theory. So let me now describe the problem that we want to tackle, okay, the specific problem. So we considered 4 graviton scattering amplitude in type 2B string theory. At tree level, this scattering amplitude is given by the supergravity result and an additional R2D4 contact interaction. Okay, this was worked out by Gross and Witten in the 80s. And this is the form of the tree level amplitude for this 4 graviton scattering. I have written the amplitude in the alpha prime equal to 1 unit. So this is the unit that I'll be using throughout. Kappa square, okay, is related to Newton's constant, but more importantly, it's related to the string coupling GS by this formula. And in my convention, the string coupling GS will be chosen in such a way that the d instanton tension, the d string tension is 1 over 2 pi GS. So because in the alpha prime equal to 1 unit, the fundamental string tension is 1 over 2 pi, defined this way, the S duality, for example, has simple action as GS to 1 over GS. So that's why you choose the GS in this particular way. The Kc here is a kinematic factor, and this depends on the polarizations and the moment of the external gravitons. Okay, this is a well-known factor, but I'll not write down the expression because it's somewhat complicated. So only thing, let me say that it carries 8 powers of momentum. So here is that formula again. Now this term, the first term, 64 over STU, this is a supergravity contribution. And this is S duality invariant by itself, okay, which is not surprising because supergravity action is S duality invariant. The second term is not S duality invariant, but there is an S duality invariant completion containing one loop and non-perturbative terms. This was postulated first by Green and Gutperle, and by now there is enough evidence for this. So they wrote it in terms of non-holomorphic Eisenstein series. But what I have done here is to give the weak coupling expansion of this whole function. So the leading term is 2 zeta 3, that's this one. This is the one loop term. And then it contains a series of non-perturbative terms, okay, which look quite complicated. So here e to the 2 pi tau is A plus I over GS. So A is the vacuum expression of the Ramond-Ramond scalar. GS I have already introduced as string coupling. And e to the 2 pi I k tau, these terms are contributions from k d instantons. And e to the minus 2 pi I k tau star are the contribution from k anti d instantons. And here you see a whole series expansion in GS. These are corrections on top of a given instanton. Okay, so there's a power series expansion in GS for each instanton. So from this, we can get the following prediction for the leading term in the KD instanton contribution to the 4 graviton amplitude. So here I have re-expressed kappa in terms of GS. Okay, so you don't see any kappa anymore, but you have this GS to the 7 by 2. There is a complicated factor, okay, over here. And everything else is already given earlier. So our goal in this talk will be to reproduce this from direct instanton computation, okay, without using S duality. And in fact, once this is done, one can show that all the higher order terms in the power series expansion in GS can be obtained using the differential equation implied by supersymmetry. So supersymmetry is powerful enough that if we give the leading term in the d instanton contribution, it generates the whole series, in fact, the whole function. So this means that if we are willing to use supersymmetry, then knowing these, once you have derived these, that determines the function completely without help of S duality. Nevertheless, it's important to develop techniques for evaluating the higher order terms by direct perturbative computation, because as I said, the purpose of this analysis is not to just verify known results, but to develop techniques that can be applied to cases where there is no S duality or the supersymmetry is not powerful enough. And this, in fact, is work in progress by the Harvard group. And as I said, they also determined the G string dependence of the K of the single instanton term of this earlier. So here is the same expression again. So in this expression, this term, e to the 2 pi I k times e to the minus 2 pi I k by GS, this comes from exponential of the action of k instantons. And we will not discuss this term any further. Okay, that's the standard term. Okay, because k instanton contribution will be given by, we'll have an accompanying term e to the minus k times the instanton action. Okay, and that's what this is representing. So our goal will be to reproduce the rest of the terms, okay, that we see in this expression. So let me now begin the single instanton contribution. So the leading contribution here comes from the product of 4 disk 1-point functions and arbitrary number of annulus 0-point functions. So the general rule for d-instanton computation is that you just try to maximize the number of disks because each disk gives you 1/gs. Okay, so that's why you have the 4 disk amplitudes. And because the annulus doesn't have any factor of gs, it has Euler character 0, you have to resum, you have to exponentiate it because you can insert as many annuli as you like. Okay, so that's what this exponential of the annulus represents. So we'll define n as I times the exponential of the annulus diagram. And our first task will be to basically calculate n. In fact, at this order, all the subtleties reside in the calculation of n, because these come from standard worldsheet calculations. Okay, somewhat tedious, but straightforward. So we'll be focusing mainly on this computation. And the one thing I want to point out here is that we include disconnected worldsheet because individual worldsheets do not conserve momentum. D-instanton breaks space-time transition invariance. And the momentum conservation is restored at the end after integration over 0 modes. And we'll see later how that is done. Okay? But because there is no momentum conservation on individual worldsheet components, you have to include disconnected worldsheet. Okay, so here is the expression again. Now for type 2b d-instantons, A is known. Okay, here is the expression given in terms of the Jacobi theta functions. This in fact is 0, but I have written it for symmetry. And in fact, there is a theta function identity that says that A is identically 0. Okay, these terms all cancel. So this is the result of cancellation between the Nebuchadnezzar sector and the Ramon sector of the open string states. The first 2 terms come from the NS sector and the last 2 terms come from the Ramon sector. Now, if this was the whole story, then you could just stop here. Okay, the price you pay is that you don't get anywhere close to the answer that you saw earlier, which was predicted by Green and Goodward. Okay, so you have to understand what this formula means. So to do that, we have to look at the general structure of A. Okay, and this in fact is the general form of A. L0 is the standard Virasoro generator. Okay, for the open string. Okay, this is the worldsheet formula number. Sorry, this is the space-time formula number of the state. Okay, worldsheet for the JSO projection is already understood inside the trace. So the fact that A vanishes shows that the contribution from positive L0 states cancel in both form a pair. Okay, that's a consequence of supersymmetry. And for these, in fact, there are no subtleties and the cancellation is genuine. It's not necessary. In more general cases, this cancellation may not happen, but here it does happen, and that's genuine. But this cancellation that is so cannot be trusted for the 0 modes, and we need to treat them carefully. And to do that, it will be first useful to regulate the system by introducing a non-zero L0 value, H, for the 0 modes at the intermediate steps. And we need to do it preserving BRST invariance and conformal invariance. And the easiest way to do this is to put slightly shifted boundary condition on the 2 boundaries of the annulus. And this gives a contribution to L0, okay, that will use to regulate. This preserves conformal and BRST invariance on the worldsheet. So there is no problem in dealing with this regulation. So in the regulated system, A is given by this. Okay, it's still 0, of course. And now I'm going to do a series of manipulations which look crazy at the beginning. Okay, but its meaning will become clear later. So first, I'm going to write this 8 as 10 minus 2, okay, which is an identity. Then I'm going to do these integrals over t. And this can be done here and write this as, so this gives logarithmic terms, and because you are exponentiating, you get the ratios. Now here, I should point out one important aspect of this formula. The ability to do this integral and get a ratios of h's of this form relies on the fact that this integral doesn't have ultraviolet divergence. Okay, that there is absence of UV divergence as t goes to 0. That's at UV point. Okay. Now the fact that these cancel exactly, that's a consequence of supersymmetry. That may or may not happen in a generic case. But the fact that as t goes to 0, this contribution, okay, goes to 0, so that the integral is finite from t goes to 0 limit. That's the magic of string theory. Okay, that happens in any string theory where there's a closed string tachyon. So that's the important point you should remember. Okay, so this, so even though many things simplify by supersymmetry, the main thing that we need is not supersymmetry but absence of closed string tachyons, and that's what is needed to go from here to here. Okay, the next step is to rewrite this as a set of integrals, okay, which I have written here. This in fact is an identity. Okay, so you see that nothing has changed. N would have been I because A is 0, it's still I, okay, because these things cancel, and we can show that this integral I gives you identically this. So here xi mu are the Crane-Grassmann even modes which are related to d instanton position. PQ are two Grassmann odd modes which represent ghosts. And chi alpha are 16 Grassmann odd modes which represent fermion zero modes. G alpha beta here is an antisymmetric 16 by 16 Hermitian matrix that satisfies the G square is H times the identity matrix. And as I said, the equality of this and this is an identity. Okay, everything can be done explicitly here. So after you do these integrals, you recover exactly this. For example, the xi mu integrals gives you the 1 over h to the 10 square root. The integral over PQ produces this h, okay, which is square root of h square. And integral over the chi alphas produces this square root of h to the 8. Okay, so now we proceed as follows. I'll give the steps and then I'll give the final result. So the first task will be to interpret n as Siegel-Gauge fixed path integral of open string field theory on the instanton. And this fixes the normalization of the integration measure. Okay, a priori, the open string field theory doesn't have a fixed integration measure. That's arbitrary. Okay. But when we try to interpret n, okay, which is given here, okay, as the Siegel-Gauge fixed path integral of open string field theory, okay, that fixes the normalization of the integration measure in string field theory. So in this interpretation, the modes P and Q represent Fourier-Popov ghosts in the NS sector. Then you show that the Siegel-Gauge becomes singular as h goes to 0. Okay. And this in fact is the reason why the coefficient of the PQ term that represents the ghost kinetic operator vanishes. Okay. And it's clear that when the ghost kinetic operator vanishes, the gauge choice is singular. Right? And so once we identify PQ as the ghosts, okay, then the fact that here the coefficient of PQ is h, which goes to 0 as h goes to 0, clearly indicates that the gauge choice is breaking down. So the remedy will be to work with the original gauge invariant path integral before gauge fixing. And this will get rid of the modes P and Q from the integral, but it will also introduce some additional variables on which you have to integrate. Okay. So in the next slide, I'll write down the final result, okay, and I'll at least try to motivate how that comes. So here is the final result after setting h equal to 0. This I was there, it's still there. These integrals we see, okay, as they were before. As h goes to 0, the xi and chi alpha dependence all goes away because the matrix G alpha beta becomes 0, h is 0, so there's a kind of quadratic term involving the xi mu. But you see a new mode has appeared, new mode phi. So what is phi? Phi is the mode that was wrongly fixed to 0 in the Siegel-Gauge. Okay, so that has come back. And theta is a gauge transformation parameter that was used for the wrong gauge fixing.
Sure.
So in fact, for non-zero h, if you start with this, and if you carry out a Fourier-Popov procedure, you will find that it exactly reproduces the integral that we had earlier.
Ashok, you have 5 minutes time.
Thank you very much. Okay, so now we can do the phi integral. Okay, that's the easy part. That's the simple Gaussian. And you get a factor of 2 root pi. Okay, and now you have to understand what these integrals are. So the xi mu's, I have already said that they are related to the location of the instanton in space-time. Okay. But now you have to be more precise. You have to understand what exactly is the relation between xi mu's and the x mu's. And the precise relation may be found by comparing these two things. that first we can look at the explicit coupling of xi mu to a string amplitude, and this you do from worldsheet computation. And you compare that with the expected coupling of x mu to a string amplitude, because the dependence on x mu should be of the form e to the ip dot x, because x is the d instanton position. P is the total momentum carried by all the closed string vortex operators. So by doing this comparison, one finds this relation between xi and x. GO here is an open string coupling, which is related to the closed string coupling GS by the specific relation. And this means that the product over xi mu, d xi mu, I can now rewrite as product over dx mu with this extra factor over here. The next thing is to understand the gauge transformation parameter theta, right, which appeared in the denominator. So what is this? So this turns out to be related to the rigid U1 gauge transformation parameter alpha on the t instanton. So let me explain what this rigid U1 gauge transformation is. So if we take an open string that connects the d instanton to a neighboring instanton, okay, this is some spectator, there is a U1 symmetry under which this state picks up a phase of into the I alpha. Okay, so this is a standard U1 that is there on every d brane, including d instanton, even though there is no dynamical gauge field on the d instanton. So we compare the infinitesimal transformation by alpha to the string field theory gauge transformation parameter generated by theta. Okay, take any state of the open string and compare these two gauge transformations. By doing this comparison, you find the relation between theta and alpha. Okay, and this is the relation. So integral d theta we can rewrite as now integral d alpha. Okay, with this factor. And now you see from this definition of alpha that alpha has period 2 pi, because 2 pi rotation doesn't do anything. Okay. So this integral gives you 2 pi. So this theta integral gives you 4 pi by GO. So this is what goes in the denominator. So after doing all that, this is the final expression for n that we get. These are now the instanton positions. The chi alphas are the zero modes on the instanton, the fermion zero modes that are associated with broken supersymmetry. So the x mu integrals eventually generate the momentum conserving delta function that I said was missing initially. And the integration over the Grassmann odd variables, chi alpha, they will vanish unless there are 16 insertions of chi alpha in the rest of the amplitude. Okay, so you need to bring down 16 factors of chi alpha from somewhere. Okay, and this has to be done from the rest of the amplitudes. And in fact, one can do a simple analysis and show that of these 4 disks, the only non-vanishing contribution comes from inserting 4 fermion zero modes on each of the 4 disks. Okay. So a disk without any fermion zero mode or a disk with 2 fermion zero modes give identically 0 result. So you need at least 4 fermion zero modes on the disk with a graviton insertion to get a non-zero result. So the distribution is unique. Okay. So now the chi alpha integral gives a factor of epsilon. Okay, this 16-dimensional epsilon symbol. This multiplies the product of 4 disk amplitudes with these fermion zero mode insertions. This is standard worldsheet calculation. And at the end of all this, and after you put in all these factors over here, we precisely reproduce the Green-Kuthperle prediction for k equal to 1. So this is the result for single d instanton. So I'll just take 2 minutes to finish the rest. So k instantons. So for k instantons, the center of mass degrees of freedom give the same integral as a single instanton, except for some powers of k from Chan-Patin factors. Okay, so that is trivial. The relative degrees of freedom, okay, which is the SUK part, they have to be analyzed similarly by gauge unfixing the Siegel gauge, because the worldsheet calculation always gives the result in the Siegel gauge. So you have to gauge unfix. And then you have to explicitly integrate over the out of Siegel gauge modes. And the remaining part is a supersymmetric matrix integral, which in fact had already been computed in the 90s, late 90s, while studying the index of multiple D0 branes. Okay, and in fact, these are the 2 groups which did this computation. So you simply have to take their result and put them together. Okay. And putting these results together, you will produce precisely the leading term in the k instanton amplitude as predicted by Green and Kuthperle. Okay. And as I have said earlier, that once you have the leading term, and if you are willing to use supersymmetry, then you generate the whole function. So final slide. conclusion. So what we see from here is that string field theory gives a systematic procedure for computing d-instanton contribution to the amplitudes. So we should be able to apply this procedure to calculate d-instanton contribution in situations where S-duality may not be of help. For example, in semi-realistic string compactifications, other problems where d-instanton corrections might play a dominant role, and perhaps also to find a non-quadratic definition of string theory by summing over saddle points, as I mentioned earlier. Thank you.
Well, actually, I had the question, Ashok.
Okay.
So to use supersymmetry to get higher genus corrections, if it was just linearized supersymmetry, then it would not tell you anything about higher GS corrections. Is that correct?
No, you do. I mean, you get, because you get a second order differential equation, right? Linearized supersymmetry. So once you have the second order differential equation, okay, that was a partial differential equation, but in a given instanton sector, it's just ordinary differential equations, second order ordinary differential equation. And now the leading term fixes everything, the whole function.
Okay.
So this is really linearized supersymmetry.
But linearized supersymmetry would not affect the coupling constant, right?
It does somehow. I mean, the point is because it's a derivative with respect to tau, right?
Okay. Yeah, I guess when I mean linearize, you linearize around tau being non-zero. I was going to linearize around GS equals 0. You're somehow linearizing around something else. Is that right?
Yeah, exactly. The linearized around some fixed tau.
Okay.
Which could be coupling.
Okay, thanks.
Murthy, please. Murthy, can you hear?
Oh, me, sorry. So I have a simple question. So why are d-instanton enough to compute non-perturbative contribution to the 4-point amplitude? Is there a supersymmetric explanation?
Okay, so the point is that typically what happens is that if you get the, in any given topological sector, if you have the leading saddle point, then typically resurgence fixes everything else. Okay, here of course there is a lot of power from supersymmetry. But even if you didn't have supersymmetry, right, I think just for at least in type 2b in 10 dimensions, I think the only topologically non-trivial sectors are coming from d-instantons. NS fibrin instanton, for example, doesn't have a contribution in 10 dimensions, right? They come only after the compactify, so that they wrap and give cycles. So here, I think the only topologically non-trivial instantons are d-instantons.
So do you believe that this works even for non-supersymmetric quantities?
Yeah, this procedure will definitely work. I mean, whether the supersymmetry may not help in generating the higher order terms from the lowest order. But if you want to do a systematic worldsheet computation, then there is nothing about supersymmetry that you have really used in this procedure.
Okay, thank you.
Oliver, please.
Yeah, suppose I want to apply this method for higher derivative operators in type 2b, say d to the rth, d to the 8th, r to the 4th, and beyond. What are the main problems and perspectives to get the high derivative instanton contributions?
I think there is no technical difficulty. Okay, there is no conceptual difficulty. The difficulty may be more technical, that to get the higher derivative terms, I think if you just look at the product of disk amplitudes, that's not what is going to give the higher derivative terms. You need disk, you have to insert higher point functions on the disk. But the normalization, once you have computed the normalization for k d instanton, that is fixed. There is nothing, the normalization, you don't have to compute anymore. Right? So the problems are more technical, that you have to do the worldsheet computation appropriately. In fact, if you ask for the supersymmetric ones, d to the 4, r to the 4, and d to the 6, r to the 4, these computations, so the Harvard group, I think C is on the line, so he can confirm. As far as I know, Harvard group, they computed the ratio of the d to the 4, r to the 4, and d to the 6, r to the 4 to the r to the 4 term. And that ratio comes out correctly. So once you know normalization works correctly for the R to the 4, right, at least for single instanton, you also know the normalization works, the result is correct, right? The leading result is correct for the D to the 4 R to the 4 and D to the 6 R to the 4 terms.
So that means the path is clear for the Harvard group to go for 8 derivatives and more.
Well, maybe I think C is on the line, so he can clarify, perhaps.
Yes. I mean, I mean, you know, it's still work in progress, but we think we have already gotten the higher derivative order 1D instanton contribution coefficient correctly, but we actually currently have some, well, earlier we did a calculation based on a naive on-shell worksheet calculation, and where there was some slight puzzle associated with that, and we're trying to do that properly using open plus closed string field theory, which we hope to resolve the puzzle, but that's still not finished.
And that's great news. Really looking forward to
the
that.
puzzle, as far as I understand, C is only about the higher order terms in the R to the 4, right? For D to the 4, R to the 4,
it was for all SPU dependent, but at 1D instanton order at the first subleading order in GS.
Yes. Okay.
Yeah, but you know, there's arbitrary momentum dependence. So not just at the R to the 4th order.
I see.
Okay.
Yeah,
Okay.
let me just speak up, Frans Klinkhamer. So you look at instanton, anti-instanton, but from the work on quantum field theory from many, many years ago, we also know that there may be non-trivial contributions in the topological charge 0 sector, right? So you can view that roughly as a bound instanton, anti-instanton. And then roughly it would have twice the action, right? Minus the binding effect. Have you looked at that?
Yeah. So in this case, we know from the supersymmetry argument that there is no such contribution for R to the 4th term, because the differential equation that I alluded to fixes the non-zero results to come only from the tree level and one loop. Otherwise, hard genus contributions just simply don't satisfy the differential equation. Mm-hmm. So in the 0 instanton sector, at least for R to the 4, we know that there is no other contribution using supersymmetry, not using direct instanton calculation. But you also know that D to the 6 R to the 4 does have instanton anti-instanton contribution. And that will be a challenging thing to do. I mean, in principle, one should be able to get those from these kinds of calculations, but that has not been done certainly.
Okay.
Okay, the last question from the Princeton node, please.
I guess this is us. So I have 2 questions. First, kind of follow up on the previous question. In cases which are not supersymmetric, there are higher order corrections, which usually make the instanton contribution ambiguous because it's contaminated by the high order contribution in the power series expansion. So in what sense is this computation meaningful in non-supersymmetric situations? And the second question is whether you have a physical interpretation of the split by H of the 2 boundary conditions that you used.
Okay, so the second question maybe I can answer first. The split by H is essentially that instead of talking doing the calculation for open string with both ends on a single D instanton, you are thinking of this as open strings with both ends, the 2 ends lying on 2 different D instantons. But when they coincide, the spectrum is identical to that of a single D instanton. And that's the regulator that we are using. Okay, they think of this as open string not on a single D instanton, but between 2 D instantons. Okay, about this first question, okay, of course, I don't know the answer fully, but my understanding is that if we, in every topological sector, okay, so the D instanton contribution is in a separate topological sector, okay, because you have this e to the 2 pi I k tau. So I think if we are looking for contributions of the form e to the 2 pi I k tau, then there is no contribution of that kind from perturbative saddle points. Okay, you can get as high order as you want. They will give terms which don't have e to the 2 pi I k tau. So this instanton expansion, I think, does give the correct capture correctly the series expansion, the leading series expansion of terms which go as e to the 2 pi I k tau. So it's basically the axiom which is important, 2 pi I k tau 1. That kind of contribution will not come from resumming perturbation series. It's like a theta term, right?
Okay, now we are over time. People who have more questions can leave it for the discussion session, which is going to start in a few minutes. Okay.
Okay, so maybe let's get started right away with the discussion. So let me just remind people how the discussion works. So I already mentioned yesterday, so you can check in the video of yesterday, but in very, very shortly, the idea will have 20 minutes that are totally up to Barton and Yuji to do as they please, followed by 30 minutes that should be a more informal discussion with the audience where people can ask questions, make comments, also ask questions to the previous speaker. There were many questions for Ashok that we could still ask during the discussion session. And please, during that part, so of course, keep your camera on if you are participating so that it becomes lively and informal and relaxed. And also raise your hand if you want to ask a question. And besides raising your hand, if your question is related to what we are exactly discussing right now, to the topic that is being discussed right now, wave or write in the chat so that we stay within the topic and then we move to the next topic. I think this is working well. So raise your hand and wave if your comment or question is related to what is being discussed at the moment. And I'm taking note that we are starting a bit late, and I will now count 20 minutes before we move into the informal part. So I give the floor to Barton or Yuji to do as they please for these 20 minutes.
All right. So I wish to thank on behalf of Yuji and myself, our friends, the organizers of this nice conference, for giving us the chance to talk about what has happened with string field theory in the last few years. Next. So I will take a very restrictive viewpoint of achievements. I will consider instances where the string field theory has helped provide the answer to some specific physical open questions. The set of achievements of string field theory include other things in which, for example, from the early start, the role of the BRST operator was brought forth by string field theory, and many other things having to do with Riemann surfaces, exotic algebras, BV quantization. But let's first talk about physical questions. So perhaps the most dramatic application of string field theory was to the subject of tachyon condensation, where Ashok Sen had a set of tachyon conjectures having to do with the depth of the potential of the tachyon, having to do with the mass of the D brane, with solitons, D branes as solitons, and the fact that at the tachyon vacuum there would be no excitations, and worked in string field theory, established these conjectures first numerically and then analytically through the work of Schnabel. And it's important to emphasize that those results are non-perturbative. So it was evidence that certainly the string field theory, the open string field theory, does contain non-perturbative information. Next. So the second point is that we come to realize that string field theory is the first complete definition of string perturbation theory. The first quantized worldsheet formulation works in many standard circumstances, but in some cases it doesn't quite tell you what you're supposed to do. This has to do with infrared divergences and S-matrix elements for states that undergo mass renormalization. So in a series of papers, and we heard some of this today, Sen and collaborators have pushed this interpretation and used string field theory to compute one loop mass renormalization of unstable particles to fix ambiguities in two-dimensional worldsheet string theory. And today, as we heard, to fix the normalization of type 2b, the instanton amplitudes. Next. So let us talk about what has happened in the last few years. And there's two very important things that we have in these transparencies. First, following from the solution of Martin Schnabel, we have learned how to write analytic solutions that describe general boundary conformal field theories. That is, you start with a standard open string field theory in some particular background, and you can write now, thanks to the work of many people, but mostly Erler and McAfee, a solution that describes a different D-brane configuration, starting from some canonical D-brane configuration. So this shows, again, non-perturbative information in that seems like open string field theory captures the landscape of solutions and some notion of physical background independence. That is, you can reach other backgrounds at least through solutions, even though the background independence is not manifest. And the second important thing is that the superstring field theories had a number of technical difficulties that prevented their construction, but they have finally been constructed. And for the open superstrings, we have these three works shown here. Next. And for heterotic and type 2 superstrings, that is an even harder problem, there was a complete solution in which Ashok Sen used an extra copy of the string field. So there were, usually you have just a single string field in whatever sectors, NS, R, NS, RR, but now you have an extra copy, a complete doubling that turns out essential in order to be able to write an action, and you can show that this field decouples. So the action is written there. That is the action for a type 2 superstring field theory. It takes the same form for a heterotic, depending on how you define the string fields. And there's psi, the traditional string field, and psi tilde. There's a picture changing operator G in the kinetic term for the auxiliary field, and that's it. So in fact, for the first time, we have now string field theories, covariant string field theories for all of the string theories. Next. So from the geometric viewpoint, in any string field theory, there are algebraic issues that you have to resolve, and there are geometric issues. If you want to define off-shell amplitudes, which is what really a string field theory does and helps you for doing any kind of analytic continuation and all the work that you need to do, you need string vertices. Those must satisfy a geometric version of the Batalin-Vilkovitsky master equation. So there's been some progress in this direction as well. Here, the goal is to find the simplest way of having string vertices. For the case of the open string, at least for the classical theory, the Witten vertex does the job. For closed strings, we know this is a lot more complicated. But minimal area metrics in the past have been used for open string field theory and for the classical closed string field theory. We didn't know for a long time whether those minimal area metrics would exist for higher genus or how they would look, but in fact now, work I've been doing with Hedrick, using convex optimization tools that also help in holography, now you can find some of those metrics. Next. This, for example, is a picture of a torus, a square torus with one puncture. The puncture is at the center, and there's bands of geodesics, red and blue, intersecting, and there's curvature, and it's a very non-trivial minimal area metric. And these metrics now are known to exist, at least in some cases. Next. The other direction, we heard in a previous string conference for the attempts of using hyperbolic geometry, a very developed branch of mathematics, to discuss modular spaces of Riemann surfaces. This was done by Musevian and Pius in 2017. Together with Costello, given a definition of exact hyperbolic vertices, that they have been extended to open closed string field theory by Minjiao Cho, and some analysis of the three-string vertex by Firat at MIT. And basically, I show in this picture a three-punctured sphere. In a sense, on the left is the approach of Musavian and Pius. The off-shell three-string vertex is defined by the middle region with these three red boundaries that represent the off-shell states. And in the new proposal of Costello and myself, the Pants diagram is the one that does the definition of the vertex, and it has a very natural generalization due to the fact that moduli spaces can be constructed by gluing pants very easily. So as Pius and Musavian emphasize, it's conceivable that the advances in mathematics in hyperbolic geometry could allow some computations to be done in this picture that were not possible in other pictures. Next. So another thing that has been work in string field theory in the last few years is establishing some field theory results that follow once you have a string field theory. An important remark and observation has been given by Pius and Sen, in which they noted that string field vertices have these exponential factors, off-shell factors, for all the lines that come off of a vertex. You have factors like this. And these factors, the momentum, the spatial part of the momentum leads to convergent integrals, while the energy part of the integral is divergent. So in Feynman diagrams in string field theory, the prescription for doing the loop integrals requires that this loop integral contours approach plus minus I infinity. There's an I missing there, I'm sorry. Finally, when you analytically continue the external momentums back to the real axis, the contour is not rotated, but is kept fixed at infinity, and singularities may push it around. With this definition, there's an analysis of unitarity that has been carried out, analyticity and crossing symmetry, and some discussion of Wilsonian actions. Next.
You used more or less half of the 20 minutes, like 10 minutes.
Yes, and now Yuji goes on. So Yuji, please continue.
Okay, so I'd like to tell you that homological perturbation theory of homotopy algebras is playing an important role in recent directions of research on string field theory. So traditionally, homotopy algebras such as A-infinity algebra or L-infinity algebra were used in the construction of string field theory. And the most important example is the construction of closed string field theory by Barton in this paper. Recently, homotopy algebras are used in different contexts. As I'm going to explain shortly, the construction of the low energy effective theory by Sen, so we see the homotopy algebra playing an essential role. Also, there are many papers on the relation between the on-shell scattering amplitudes and the so-called minimal model of homotopy algebras. But let me mention one paper which is very relevant to us by Kajiura. So let me very briefly explain the A-infinity algebra as an example of homotopy algebras. The A-infinity algebra describes relations among Maldacena products of open string fields. So let's consider an action of this form where interactions are written in terms of Maldacena products two-string product V2 and three-string product V3, and so on. Also consider the gauge transformation in terms of the same set of multi-string products V2, V3, and so on. Then this action is invariant under this gauge transformation if multi-string products satisfy a set of relations called infinity relations, given these. So let me explain in the context of low energy effective theory. So then the path integral over massive fields to obtain the effective action for massive fields generates new multi-string products. For example, from these three string vertices, we get effective quadratic interactions in the low energy. Here the integration, here the propagator for the massive fields. But the important point is that the infinity structure in the original theory is preserved in this path during the process of this path integral. And the homological perturbation theory provides a fairly explicit construction of this infinity structure in the low energy theory, or infinity structure in the scattering amplitude. So then multi-string products satisfying the infinity relations can be efficiently described by linear operators acting on this vector space. This is a one-string Hilbert space, two-string Hilbert space, and so on. The infinity relations can be compactly expressed in terms of a linear operator M on this space, which square to 0. So the complicated relations can be written like this. So very efficient, right? So for the action of open bosonic string field theory, the infinity structure M described by M is where M is given by Q plus M2, where Q is associated with the BRC operator, M2 is associated with the two-string product, which is the star product. Then the homological perturbation theory provides M for the effective theory as follows, where P is the projection, and the H is for the propagator for the massive field. So this inverse is defined by the geometric series as usual. So this is fairly explicit. So let me give you some examples from recent string field theory papers. There are also field theory papers as well. Based on the general framework developed by this paper by Irvin, Macaferi, Schnabel, and Boschmeller, Macaferi and Boschmeller explored cross-string deformations in open string field theory, such as the change of the compactification radius of S1 compactification in the series papers. And Euler and Matsunaga discussed mapping between Witten's covariant string field theory and light-cone string field theory in this paper. And together with students of mine, I considered gauge invariant operators of open bosonic string field theory in the low energy limit in this paper. As you see from the title of these papers, the motivations are totally different, but essentially the same tool from the homological perturbation theory here is used in these papers. Furthermore, homotopy algebras can be also useful in ordinary quantum field theory because basically Feynman diagrams here can be handled algebraically in this approach. And I took figures from this paper by them and Sviranaro-Lakis. So these two-loop diagrams can be generated by this kind of geometric series like this. So we can handle these Feynman diagrams algebraically. So I would expect fruitful interactions among various research areas. So now let's move on to the section of the open questions. So Barton, would you explain the first two items in the list?
So let me take these first two questions. Some things that have remained still unsolved in the last few years are the question of initial value formulations in open string theory and closed string theory, perhaps more seriously, and There was work by old work of Eliezer and Muller pointing all kinds of potential difficulties with higher derivative theories and initial value formulations, and an interesting discussion by Euler and Gross, but still the issue is not completely clear. And this shows in the ideas of microcausality and causality. In fact, microcausality, usually defined as operators commuting when they are separated by space-like intervals, is difficult to test in covariant string field theory, which is a path interval formulation of the theory. And perhaps a formulation of Bogoliubov could be useful in doing this. As we appreciate the role of initial value formulation and the causality that has infinitely many time derivatives in the theory and infinitely many space-like derivatives, this is also related with non-locality, which would be very useful to understand better, as it has been repeatedly suggested that the black hole information puzzle is hard to resolve in the framework of low energy effective field theory that is local, and you need some kind of non-locality. Another thing that is sorely missing is classical solutions of closed string field theory. Just like the open string field theory, I would suspect that these solutions exist and contain non-perturbative information. You can go from one background to another. But it's still, since the theory is more complicated, nobody has been able to find those classical solutions. Of course, if the theory was reformulated, perhaps that would help. Next.
So let me explain the next item. So which is the proof of the ADS-COT correspondence. I have made this intentionally provocative for this purpose of discussion session. So ADS-COT correspondence is typically realized in the low energy limit of the theory on D-branes. So you may think the theory before taking the low energy limit should be something like open closed string field theory, which would be difficult to be defined non-perturbatively. But I would claim that the open string field theory can do the job. So usually, open string field theory is sort of something that reproduces the on-shell scattering amplitude of open strings. But in this context, we are interested in the correlation functions of gauge invariant operators. Also, the 1/n expansion of such correlation functions should be perturbation theory containing gravity. So this kind of direction research has not been explored in the string field theory. That's my message for the future direction. So, and for this story to work, it is important that the important question is that whether or not the open superstring field theory is a consistent quantum theory. So if this is the case, I think we can use it to help prove the ADS-COT correspondence in the framework of string field theory. And we have the last item in the list, but before going to the last item, let me show you something interesting. So let's see what Barton said 10 years ago. So there was a conference in Kyoto 10 years ago, which I also attended, so 2011. So Barton gave a talk, and the title is String Field Theory, Achievements, Challenges, and Future Directions, which is similar to the title of this discussion session. And at the end of that talk, Barton mentioned future directions, challenges as of 2011, 10 years ago. So the first, he mentioned the missing string field theories. But as you heard from the Barton's part of this presentation, the missing string field theories have been constructed. Very nice. Then he mentioned that the missing analytic solutions, which have also been constructed. So we are really making good progress, right? Then he continued to say, but the question most likely to determine the future of SFT is a question of, guess what? Background independence. So we need manifest background independence. So Barton, would you like to say something about the background independence?
Okay, sure. Next. So It's a difficult question, and I think one could say there's been a few attempts that were interesting, and they all look very exciting and promising, but didn't get too far. We don't know whether they're wrong attempts or we didn't have the tools, or perhaps we need something more radical. So one approach, Witten wrote some way of constructing BV master actions in the space of all open string worldsheet theories, not conformal theories. It did help for tachyon condensation, but eventually with non-renormalizable interactions for these worldsheet theories, it got very difficult and was kind of abandoned. I also had some very straightforward suggestion that the L-infinity algebras or A-infinity algebras would need the zeroth product, something mathematicians always include. So there you see a product of two string fields, that's standard. A product of a single string field is the linear operator Q, and a product without a string field is a special string field F. And if that string field F satisfies QF equals 0 and Q squared equal F, you could build a new kind of string field theory. But this had not been built and had not been studied. It's kind of difficult. Finally, from open string theory, people thought of using the tachyon vacuum as a very special universal background and formulating a vacuum string field theory using a BRST operator that just was built of ghosts. In reality, that works quite well, except that this purely ghost BRST operator doesn't do some things very well. Yuji actually did a very important contribution to this field, but at the end, it just got difficult. So I think we need a new idea that will come from some of the participants in this conference. That's it. Thank you, Yuji.
Thank you very much. Let's thank Barton and Yuji for setting up the discussion.
Yeah,
and
mention 1 second, Pedro. There's the string field theory yearly conference happening, and there will be one organized by Chakrabarti, Irving, Lipinski, and Vosmera in September, and we invite people to come and see.
Very good. So as I said before, please raise your hand if you have questions, and yeah, we can start with Nathan, perhaps. Yeah?
So I had a question, which is about just the definition of the string field. So, I mean, has there been much progress on trying to define the string field in some more abstract sense? What's an allowable string field? If you allow insertions in the string field and things like that. And I guess that's related to why does the level truncation method work so well? So I guess that's for everybody. I mean, not just for you.
Yeah, I'm not aware of any specific progress, but I welcome comments from other people. Level expansion remains a little mysterious, I think, why it works. It would be interesting to see how it would work in a theory that has more than a cubic interaction, a theory that has a cubic, quartic, quintic, and I don't think there's any suggestions how you balance level versus the power of the interaction as well. People that understand maybe how the string field is defined, maybe Carlo Macaferri and Erler, that have been doing very interesting solutions in the space of open string field theory, may want to comment on this. I don't know. Or Yuji?
Yeah, it's a very difficult question, so I don't have much to say, unfortunately.
So again, if you have a comment about a particular question that's being discussed, wave and I'll figure out. Otherwise, if Nathan's question is too hard, we'll move to Shi.
So I'd like to make a comment. In fact, it's something I wanted to say in a discussion next week, but I think now is the appropriate time to start talking about string field theory. An application that has not been mentioned so far, which I think is important, is that the superstring field theory, closed superstring field theory, provide a first principle definition of remote flux background. In my opinion, it's really the only available first principle definition of our flux background beyond the low energy approximation. The alternative, for example, one sometimes talks about the Green-Schwarz string in our flux background. This to me is a effective action. The Green-Schwarz description is an effective action based on nonlinear realized space-time super Poincare symmetry or other symmetries in the ADS background. And it is subject to intrinsic ambiguity of higher derivative ambiguities. Now, in the case of, say, ADS 5 times 5, these ambiguities are, the working hypothesis that they can be fixed by impulse integrability, but that's not from first principle. So I would even say that for strings, type 2B string in ADS 5 times 5, even at the level of an expansion in 1 over R, 1 over radius, the only first principle definition of the string background beyond low energy approximation that I am aware of is to start from the Minkowskian background and turn on perturbatively a non-trivial solution to the closed superstring field NSR equation. And then you can linearize around that non-trivial solution and try to determine order by order 1 over R of the string type 2B string spectrum ADS 5 times 5. In practice, this has not been carried out in that specific background, but in principle, to me, this is the only first principle way to determine the string spectrum in the background, and further on top of that, perturbative interaction.
So this has not been carried out in practice, or is it?
Yes, it was difficult. In fact, as far as Ashok tells me once that he has studied this at some point, but it was difficult. I mean, a few years ago, Scott Collier, Min-Jae Cho, and I did the analysis thing for ADS3. In that case, it was technically a bit easier because we're not changing the geometry of the background. We're just putting on our flux, and we can indeed understand correction of our flux on the string spectrum using string field theory. I mean, we didn't really use the hard part of string field theory. We used the framework, but we only did the leading order calculation, which did not require most of the technology of string field theory. But nonetheless, conceptually, it was a string field theory calculation. And for ADS 5 times 5, deforming from flat space is technically harder, and this has not been done as far as I know. I mean, the thing is, people have studied this, of course, in Green-Schwarz formalism, but I would say that people have not gone to the high enough order in alpha prime expansion to encounter the ambiguity that would require integrability to fix from the worksheet perspective. In principle, based on NSR, there will be no such ambiguity, and it should be a first principle calculation. But that has, of course, not been actually done.
Maybe let's pass to Nathan. If I understand correctly, Nathan is waving. Waving is like this, Nathan. You are clapping. I think you want to wave. We use hand. So let's pass to Nathan.
I don't know if you're distinguishing Green-Schwarz from pure spinor, but I don't know why you think Ramond. Let's use pure spinor formalism just because that's the one I like. Why do you think Ramond is more complicated than Never-Schwarz? I'm missing some point here.
I was thinking purely in NSR formalism. In NSR formalism with the Ramond background, I would say there's no known worksheet local CFT that obeys the usual rule of worksheet CFT that we know of. The pure spinor formalism, to me, there's a little bit missing, which is just the full consistency of the worksheet CFT. But perhaps for the ADS background was not at least in the flat space, because this issue of that you cannot close the OPE without trivializing the optical homology, because there's in non-minimal formalism at least it's 1 over lambda bar singularity.
No, but sorry, we're just talking about tree amplitudes, right? You're just talking about classical. I'm not talking. I'm talking about let's say to begin with, even just determining the string spectrum, but to all ordering alpha prime. So this is a quantum worksheet problem. Yeah, it's quantum on the worldsheet, but not in string loops. I mean, it's a classical.
That's right.
I think at the classical level, the sigma model is completely consistent. I don't think there's any question about the sigma model being consistent.
My perspective is that I want to work in a formalism where I at least know full consistency in perturbation theory to all order. And then within that formalism, I want to get a spectrum as a first step. Now, I'm not saying that there's no other way to get the answer, but I want to get the answer within a framework where all of perturbation theory is in principle well defined. So that's all I'm saying.
Okay, I guess if you insist on string loops, then I agree with you. But if you're happy with just string tree level, so maybe I'll let somebody else talk.
Yeah, maybe let's pass it to Shota. Maybe he will tell us that integrability is the way to go instead of.
Well, by the way, like I see Leonardo is unmuted, so I thought like he might have something to say about this before.
I just had a very quick question for Shi, but whether in ADS 5 times S5 this will actually be a large. I mean, in your work on ADS 3 times S3, it was an infinitesimal deformation in principle you could turn on. But in ADS 5 times S5, would that be that, or you need really a finite deformation?
I was talking specifically about 1 over R expansion. So
okay,
1 over R. But you know, we know that the answer is non-trivial for perturbability 1 over R. So.
Yeah.
Go on, Shota.
All right, yeah. So actually, my question is not related to ADS 5 times S5 or integrability, unfortunately. So I just had some question about the last point about the background independence, and in which they showed like a vacuum string field theory. But I saw like as far as I understand, vacuum string field theory is for open string, like a tachyon vacuum for open string. Is there any like progress about closed string, about the cross string sector?
Yeah. So vacuum string field theory has not been done for closed strings. In fact, perhaps the most crucial question is the closed string tachyon vacuum has not been determined, and that may be the thing that is really missing to understand much better the closed string field theory. We did try to calculate the closed string tachyon vacuum in the level expansion. You may want to look at those papers, but it was not very conclusive, and it seemed that there might be a tachyon vacuum, but was never identified. So unfortunately, we have not developed enough analytic techniques to do the calculations of solutions in the closed string field theory, but there might be some way to do it. It's at the end of the day, the geometry of the vertex it's quite flexible, even in the open string theory. So, so maybe somebody will, the group that has been doing analytic solution for open strings can finally find some solution for closed strings. It would be great.
I see. Thanks.
Mukund, by the way, if you still want to ask another question, or you forgot to lower your hand?
Oh,
but let's go to Mukund now.
Anyway. The question, but it was about the Ashok talk. So I'll ask.
Okay. Go on, Mukund. Yeah, go on.
Yeah. So I wanted to go back to something that Barton mentioned about the initial value formulation in string field theory, and in more general, I'm curious what the prospects are for understanding something like a local light cone in quantum gravity, which is not a meaningful concept. So usually what we tend to do in quantum gravity theory is say we talk about asymptotic observables which satisfy appropriate causality conditions. But from much of the stuff that has been done, a lot of the rules of string field theory seem to follow very much from in line with quantum field theory. So I'm curious where the local structure of quantum gravity is buried in closed string field theory. So you mentioned a couple of things that could potentially be useful. I was wondering if someone had a comment on this.
I don't have at this point much to say, but I think this is a really important question. Basically, there's been efforts, I think, within the context of the black hole paradoxes to compute commutators of closed string fields or open string fields and figure out how they behave. Now, the computations at the free level, they're kind of not very interesting, and nobody could figure out if the definition of a light cone over an average form of the strings or other definitions should be used. It was kind of trivial. But then there were computations at the first order in interactions, and they could only be done in the light cone. And in those cases, they found that somehow the commutator doesn't vanish for space-like separated points. And that has been a little confusing because certainly if there were gauge invariant operators, that shouldn't happen consistent with causality. But somehow it seems to happen, or maybe a background dependent phenomenon. So I actually think these calculations were done in the year about 2000, and I think they were not very detailed and they were not investigated properly, actually. So I believe they should be done again, and presumably the analogs in the covariant string field theory, which, as I was saying, since there's no Hamiltonian known for the covariant string field theory, they would have to be done in the path integral formulation. So I think causality has been very important for the bootstrap and for many things, and we really have not done justice to the computation of causality.
Thanks.
Maybe I will have a quick comment on what happened in tree level, or perhaps on perturbative string theory. But there's a paper about the notion that shock waves commute by Kologlu, Kravchuk, Simons-Duffin, and Zhiboydov. That is a very sharp statement about causality that makes sense in the so a simple example of a shock wave is the integral of a stress tensor like the ANIC along a null geodesic, and you can take space-like separated such things, and these things, and there's a sharp sense in which these things commute in string theory, at least in perturbation theory. So that could be a useful starting point.
Maybe you can post the reference in the chat. We'll look at it and try to figure out whether something can be done. Being in charge of the discussion, I don't know, I would like to maybe invite Martin Schnabel to say a few words if he wants, and tell us what he thinks is the future of classical solutions, or this field of expertise that he's done so much to advance. I know if he's there.
Oh, yes, I'm here, Barton. Hello, Barton. Thanks for starting nicely this discussion with Yuji. So, I mean, in my personal view, I think the outstanding challenge is to look for the classical solutions for closed string field theory. And in fact, this is one of the things that interests me the most at the moment, but the progress is slow, but I guess I'm optimistic that there is something to be done. Also, I like the Shota's question. I think this is also something that I'm thinking about with my students, and like trying to formulate the vacuum string field theory analog for closed string field theory. Yeah. Also, I may add an answer to the first question by Nathan that he asked in this discussion session. So whether like level truncation works in closed string field theory, my answer is not clear, because as you noticed in your work with your students, it was never clear whether it works in closed string field theory. And in the context of open string field theory, when he asked what is the space of string fields, the answer is not clear, because there were some very like nice constructions in the 80s in the context of this purely cubic string field theory, some operators, some string fields that were supposed to behave nicely, but then it was found that they, I mean, they're anomalous, they violate associativity of the Witten star product, etc. But analogous objects, but slightly better behaved, were used around 2005 in these analytic solutions. So that's my answer to Nathan. That was is not clear. So as far as I know, no one really did any good systematic work on what the good string fields are. Yeah. Barton, did I answer the question?
Thanks very much for those comments. You're happy to hear all these
So
things.
she seems to have something to add here. So he was raising his hand.
Yeah. So about the space of the string field, I mean, this is kind of a question/comment. So in the context of closed string field theory, where we construct the string vertices just order by order in the string field, you know, the formalism is such that the closed string field is just a state in the worksheet CFT Hilbert space, with everything goes included. To me, this is, I mean, you know, without even worrying about you know, the normalizability and things like that. To me, the first kind of slightly unpleasant feature of this is that it doesn't have general coordinate invariance compared to low energy effective drift distribution like supergravity, right? And in particular, if we want to describe something like a black brane in type 2 string theory as a solution to a closed string field equation, this already is a bit funny because you know, if you work perturbatively, then it has a source, and you might say that okay, if we work away from the source, it's okay, and you maybe want to allow the solution, but then it would be hard to see the horizon, right? So unlike in supergravity, where the magic has to do with the fact that you can write a solution that has a horizon, and if you try to write analogous solution to closed string field equation, which by definition was a state, some funny looking maybe state in the original worksheet CFT Hilbert space, and this the presence of the horizon is extremely non-manifest, and yeah, so this to me is I'm not saying that you know there's anything wrong with it, but it's just kind of an obstacle with the kind of obscure some of the physics. Just a comment.
Well, it's
So we can move. Mukund is waving, or we could move to some other topic. Barton, up to you.
I just wanted to add a quick comment to G's question.
Okay, quick, so that's
what I asked earlier, Barton, because you know, to even define the horizon, you want some local, some. I mean, you can either say some statement about. You can talk about the event horizon if you have a stationary solution, and then you can say it's something associated with the asymptotic boundaries, causal path of future null infinity or whatever. But if you want to say some local notion, that's much more tricky, and exactly because of what you said, there's no coordinate, there's no covariance statement to make.
But just to follow up on that, I could imagine something slightly different, which is that, I mean, if you think about what we do in GR, of course, we just look at the geometry around the horizon, we change the coordinate and expand around there. I mean, I could, for example, if you think about B3 brane, black 3 brane solution type 2b, you know, when n is large, I could imagine looking at down the throat and expand and view the throat as a deformation from flat space locally. Right. So in principle, there's a way to approach that region. Now there's a question of whether you can, you know, as a solution to the closed string field theory, expand it, you know, where you look at near the throat versus looking at asymptotic flat region. Can you really show that they are the same thing, or you know, can you really describe this as a true solution to the closed string field equation?
Yeah.
I don't know.
I don't know if Martin wants to say something about it in response to that, or you know, if I were, he's thinking about this solution, but certainly there are simpler solutions in closed string field theory that perhaps can be found first, which, for example, you have a 25-dimensional background, and then you put a minimal model in the last extra dimension, and you have a dilatant background, and you go from one minimal model to another minimal model, just to understand how the solutions are written. Writing solutions that have a intricate general covariant gravitational description might take a while. It might be very difficult at this moment, but that would certainly be the goal. And I just don't know to what degree those solutions would be understandable without a little bit more background independence. So I want to maybe, Pedro, I don't know if would be kind of interesting as well if Ashok Sen, that has contributed so much to this field, wanted to say maybe what he hopes for string field theory in the next few years. I don't know, Ashok, if I put you on the spot and get you to say a few words.
Yeah, I don't really know. I don't have much to say. Maybe I should say something that, I mean, often people are somewhat scared of string field theory because it looks very complicated. But my view of string field, at least one very conservative view of string field theory, okay, which doesn't aim very high, okay, is that if you think of worldsheet theory, I think it has a lot of information, okay, but all the information is coded. Okay. And what I meant, say coded, I mean, what I mean is the following, that if you try to calculate anything in the worldsheet description, it's divergent. You cannot put it on a computer and get a number out of it. Now, often what happens is that you can resolve those divergences either by using analytic continuation or by using I epsilon. But it doesn't always work. And from that perspective, I'd say that the string field theory, it uses exactly the same data that the worldsheet theory does, but it's a very good decoder of what the worldsheet theory is trying to tell us. I mean, the extreme example perhaps is the tachyon condensation, that all the data that went into the study of this level truncation is coming from worldsheet calculation. Nevertheless, the string field theory turns this into some non-trivial result, right, which you couldn't get directly from the worldsheet. And the other examples that Barton mentioned are probably just minor versions of the same thing, that it somehow takes the worldsheet and decodes it. Okay? It tells us what the worldsheet is trying to tell us. So that, I think, is the most conservative approach to viewing string field theory. Okay? But of course, it's possible that string field theory can do or will do much more than just decoding the worldsheet description.
Great, thank you. I know, Pedro, if you call.
Yeah, I have a suggestion. Let's say we are officially over with this official discussion, and we'll stop the recording and we'll resume in 20 minutes. But we can continue informally, and in particular, Shiraz and Danielle could ask their questions, and we can continue a little bit more during the break for those of us that don't mind having a shorter break. But the official discussion, we would now thank Barton and Yuji and everyone, and for YouTube's purpose, we stop here, and now we resume in 20 minutes with Samir's talk, or Leopoldo, I forgot, and but now we can continue with a few more informal questions, maybe.
Okay, maybe I can ask. It's a very ignorant question, but it goes this way: solutions in string theory of supergravity with 32 supersymmetries are very special, and we know very few of them. And ADS5 times S5 is one of them. So I was wondering whether imposing the requirement of having 32 supersymmetries on closed string field theory, type 2B closed string field theory, is something that is technically easy to do, and whether it might lead to finding a solution. I'm sure people have tried this, but I just wonder. Yeah. Or maybe it's a stupid idea.
I don't think people have tried this yet. You know, the first workable string field theory for type 2 strings is the one Ashok wrote with his extra auxiliary field. And maybe we can ask him if he ever thought of possibly finding solutions of that. I don't know if anyone has.
And is it easy to impose the requirement of supersymmetry in these? Is that how to do that? Is that known sort of elegantly?
Yeah, I mean it is possible in it's known in principle how to do that, but it's not very elegant in the sense that you have to do it again order by order, right? You can, because supersymmetric transformations are non-linear, and you know in principle how to construct any given order in the string field expansion, but you have to, there's no closed form expression, right? So I don't think it's very easy to. It's possible in principle, but it's not very easy to do this.
And this is related to the fact that space-time supersymmetry doesn't play an important role in the formulation of the NSR formalism. It's right. Related to that fact.
Yeah. So the way you realize supersymmetry, you first look at the linearized transformation, and then the string field theory vortices automatically build a nonlinear part. But the nonlinear parts, I mean, in principle, they're all well understood, but in practice, you have to do a lot of work to figure out what they are.
Okay, thanks. So it doesn't sound very easy to do. It doesn't sound like
it certainly doesn't sound very easy to do.
Like in supergravity, it's much easier to impose the condition of supersymmetry than to solve the equations of motion. But that may not be as easy here.
Yeah, because the supersymmetric transformations there are known, right? And it truncates. Here it doesn't truncate.
Right. Okay, thank you.
I was just curious, since we have all these experts here, what's the current status of trying to understand S-duality from the point of view of string field theory? Is that a hopeless task, or are there some things that can be said?
Maybe I'll comment a little bit about that. I mean, the formulation of closed superstring field theory is entirely perturbative in the string field. But it's fully quantum, but it's perturbed in the string field. And it doesn't provide directly anything more than perturbation theory.
Right, but some non-perturbative results are available, right?
Yes. And further, on top of that, as we just heard from Ashok, we can get some decent contributions. I mean, it's we only know kind of a very small corner of it, but in principle, a lot of these contributions can be captured by open plus closed string field theory. With open string on decent, so it goes beyond the closed string field theory framework. Now, with all these data, you can at least compute, in principle, quite a lot of observables that are very, very non-trivial tests of S-duality. In fact, there's non-trivial test of S-duality already a level of perturbation theory, which is this 3-loop full Graton scattering, right? The C6R to the fourth term. Combined with supersymmetry, there's a S-duality gave an unambiguous prediction about a perturbative 3-loop term, which has been checked directly in perturbation theory. Now, with the Jensen computation, there are more things you can test. So there are, there's a lot of data you can use to check S-duality, but it's of course not, if you want to prove, this is, I'm supposed to discuss this next week, is proving duality, quote unquote. I mean, it's not going to prove S-duality in any way, because the formalism doesn't have that.
But there's a different, I mean, like in n equals 4, we also can't prove S-duality right now, but we could imagine sometime in the future with the new understanding of quantum field theory proving it. But I guess I thought for string field theory, the hope was that, yes, right now we kind of only understand it perturbatively except for some things, but at least initially, and maybe still, the hope was that there is some non-perturbative formulation of string field theory where proving S-duality would merely be as, in the category of, class of difficulty of proving it in n equals 4.
I think that has to wait probably for a background independent formulation.
Yeah, I mean, I'd also add that, I mean, if we do get to prove S duality in n equal to 4, starting from the action,
yeah,
maybe that will tell us how to go about it in string theory, right? But I think otherwise I have no idea how to approach this problem.
yeah.
I think it's fair. I don't know if others agree that closed superstring field theory is still in a pretty ugly form. Well,
yeah, I completely agree. Yeah.
Beauty is in the eye of the beholder. I think sometimes, efficient, this Ashok extra field has been felt like maybe this is not ideal, but I feel that it's so efficient in doing the stuff that we will understand someday how it is an elegant thing after all. But there's also, I did mention in the approach that Yuji and Kunitomo used to do type 2 string theories. Kunitomo just published a paper with a type 2 superstring field theory a couple of days ago. And the effort continues for yet alternative versions of the closed superstring field theory, but we'll see what happens. Certainly, it is a complicated action, no question about it.
Maybe ask a question about it. So in n equals 4, we would, with integrability, we would not consider 3-point functions as the fundamental building block. It would be too complicated. We don't build higher point functions by gluing together this 3 vertex, the 3-point function. We break the 3-point function further into 2 hexagons, and that is the building block. It's the hexagon. So could there be a formalism of closed string field theory where the fundamental block is an hexagon that with two of which you can make a sphere with 3 punctures? And could that be a simpler formulation, perhaps?
That sounds a little like doing an open string reformulation of closed string field theory. Is that right? Because the pants diagram of closed string theory, if you cut it, you get a hexagon, which is kind of the vertex. That is the off-shell vertex in hyperbolic geometry for open strings. It's kind of a hexagon with 3 open strings and 3 boundaries. And,
but the boundaries are not exactly, understanding those boundaries looks hard.
That's where the boundary conformal field theory data is. So maybe, certainly in hyperbolic geometry, the building of all the moduli spaces of Riemann surfaces, starting with Pants diagrams, 3 is canonical, is beautiful, it's efficient, it's as nice as it can be. That doesn't mean it's all straightforward, but it's very natural.
Can I ask a question about the Ashok talk?
Okay, yeah, go ahead.
Yeah, so this is about the K instanton story. So it's interesting to contrast this your analysis of multi-instantons to where all the non-abelian dynamics, of course, is essential to how we usually deal with Yang-Mills instantons in a multi-instanton situation, right? Usually in quantum field theory, from pattern perspective, with multi-instantons, we do it just like a single instanton. We expand around the instanton configuration, we have a moduli space. But with the multi-instanton, moduli space is often singular. And this expansion of around the instanton configuration, conceptually really is supposed to break down when the moduli space is singular. And often we cheat, but there's no it's not really on rigorous footing. But here, one would have said the same thing about the instantons in type 2B, except that you know how to resolve the singularity of the moduli space with a non-abelian dynamic. Now, is there an analog of that in gauge theory?
Yeah, I don't know. I mean, there seems to be a genuine singularity, right? I mean,
Yeah.
Yeah.
but you know, in at least in this kind of you know, this kind of ADHN type kind of effective field theory with some degree of freedom on the instantaneous in the gauge theory, one could imagine something similar, but I don't know any kind of first principle way of doing that in the ordinary quantum field theory context.
Yeah. Yeah, I don't know.
So can I interrupt just for a minute so we can just check the share screen of the next set of speakers, and then we can continue the discussion again. So
I think most people are turning off cameras and getting some coffee and going to the restroom. I think it's a good time to stop, really, and thank once again Yuji and Barton and everyone for
thanks,
a very
Ben,
fun
for
discussion.
moderating.
And let's resume in 10 minutes with the conference. But yeah, do the share screen.
Thanks.
Thank you very much.
Thank you.
Nathan?
Hi, Michael.
Hi, I just want to say hello to you.
I saw your face. How are things?
Fine, fine, absolutely fine. Except for the weather.
Daniel, if you're connected, if you still have a question, just maybe lower your hand. I think I can lower it for you, but just wanted to make sure. Okay, I lowered your hand. Sorry.
Okay, I think everybody's now co-host, so we can go one at a time. So Samir, you want to check your share screen? I don't know if Samir is hearing me.
He was here a second. I sent him a message a second ago. Samir.
We can start with somebody else. So
I can start if you want.
Go ahead, Juan.
Can you see it?
Yeah, but maybe full screen.
Yeah.
And if you can just flip one side, yes, perfect.
Wait, can I try my screen as well?
Yep.
Okay. So I seem to be, give me a second to find the file. Leo, so
yeah, sorry, I cut in front of you, but I think it's fine.
Yeah, go ahead.
Sorry, I'm done. Checking. I think it worked.
Okay.
Okay, and then Leo, for you, I'll do 10 and 5. For Samir asked me. Oh, Samir, yeah, Samir, yes, we're testing.
Yeah, okay. I'm just trying the full screen.
Oh, here am I. No, sorry, I'm talking to the other Samir. Murthy.
Which Samir? So mine was working.
There's too many.
Yeah, you got to say which Samir.
Sorry.
About the generacies.
No, but is there a slightly different pronunciation? I feel like, sorry that I'm asking this.
It's just a different transcription in English, that's all.
Okay, okay.
Yeah, it's the same name but different way of writing.
Okay, no, this is yeah, it was because in the chat, like, sorry, I didn't mean to make confusions. So Samir Murthy, did you try? Sorry, I was. Let's try this again. As you can see, this session is not going to be chaotic at all. It will be very smoothly run. We'll all be fine. We can still see but we see the top. Like, I don't know if that's your intention.
Wait a
It's
second.
not like on full screen mode.
Oh, that's right. Now?
Yes, and now maybe switch one slide just to see that. Yes.
Perfect. And there's some pointer, right? Usually there's a pointer and.
On Zoom, it might be disabled because the annotation was disabled.
Oh,
so,
okay.
So you won't have the default Zoom pointer.
Okay,
like
but you see my cursor moving.
But yes, we do see the cursor, so that yeah, and if you highlight, we also see that.
Okay, I'll try. All right.
Yes. Okay, and then for you, Samir Murthy, I'll give you a 5-minute warning. Yeah.
Yes,
for
please.
Leo, I'll do 10 and 5, and for you, just 5. And you guys know me, so I'll start making grumpy faces if we go over time. Okay, Samir Murthy, since we have just maybe less than a minute to go, do you want to just start sharing your screen so we can start right on time? Okay. So it's 20 past. And
okay,
I'll just say, I'll do some fillers, don't worry.
Okay, no, it's fine. I just didn't, I had it on mute.
Oh, okay, no. So let me introduce you. Sorry.
I'm ready when you.
Okay, very good. So welcome everyone to the second session of the day. Very exciting session, very filled with black holes, all sorts of exciting things about black holes. And I'm very happy to introduce the first speaker of the session, who is Samir Murthy for King's College London, who will tell us about black holes in ADS5 and phases of 4D super Yang-Mills. Go ahead, Samir.
Thank you very much. Thanks for the invitation and for the nice organization of this conference. My title is Black Holes in ADS5 and Phases of Four-Dimensional Super Yang-Mills Theory. To set the context, let's consider the prototype ADS-CFT example, n equal to 4 super Yang-Mills theory with SUN gauge group on a 3-sphere S3 times time, and the gravitational dual, just type 2 string theory, type 2B string theory, on a space which is asymptotically ADS5 times S5, with conformal boundary, which is the same S3 times time. Setting the ADS length scale to 1, the Newton's constant is 1 over n squared. Now, this 5-dimensional gravitational theory has a black hole solution which preserves 2 of the 32 supercharges of the theory. And this black hole, the horizon of the black hole is weakly curved. So it's big in the sense that the area and therefore the entropy scales as n square in the gauge theory units when n becomes large. And the first question we ask ourselves is, can we account for the statistical origin of this black hole entropy? So natural place to look is the 116 ppm states in the dual Yang-Mills theory, which are counted with weighted by the fermion number and some charges by the so-called superconformal index. And I'll make this more precise shortly. And so the question now is, if the log of the index, the free energy, does that have the same n square scaling as predicted by the existence of the black hole? So this question was first developed and posed in these nice papers. And at that time, the answer seemed to be no. And in the last 3 years, there's been new progress. And now we understand that not only is there an n square scaling, but in fact, we can extract the black hole entropy on the nose, including all the numbers at large n, from the superconformal index. And in doing so, we understand new things, both about the gravity as well as about the gauge theory. So I'll keep this n equal to 4 as a running example throughout the talk. But of course, the question is more general. It can be posed in any minimally supersymmetric conformal field theory with some large n dual. The only difference now is that the theory has 8 supercharges, so the black holes and the states are 1/4 BPS. So first, I want to explain a little bit the meaning of this question. Okay, what is this index, and what do we expect here? Well, so the n equal to 1 superconformal algebra has a U1 R symmetry. The charge is called Q. And S3 has 2 angular momenta, of which we'll only consider the diagonal J. So the superconformal index is like a Witten index, trace minus 1 to the f, times some operator which commutes with the supersymmetry which defines that index. And the simplest case is just 2j plus q times the parameter tau. This can be refined by adding more operators, but in fact, all the statements I'll make can be illustrated with this simple index, and I'll only stick to this today for simplicity. Now, you can do a Fourier expansion in tau, and that defines the microcanonical indices. Here, this 3 comes from n equal to 4 super Yang-Mills, where the R charge is quantized in units of a third. On the other side, you have ADS5 supergravity with a metric and a gauge field whose electric charge is this Q, and the black holes have the same charges. And now in this context, it's useful to scale out Newton's constant. So to define the small charges, J1, J2, and Q. And as before, we'll stick to the diagonal J. So you have J and Q. But in fact, they're not independent. Supersymmetry imposes a relation, nonlinear relation between them on the solution. And therefore, the black hole entropy, which a priori is a function of those 2 charges, it can be written as a function of one combination, which you can choose to be precisely the same n as over here. Okay. So here you have a sequence of integers. This is a smooth function. And the main question is, does the sequence of the log of these integers approach this entropy function asymptotically? Okay, so here is the entropy function. as a function of the charge. You see it grows as a function of the charge, but also as a function of the rank in this direction. Now, what's the meaning of this asymptotic symbol? Well, there are two meanings which people ascribe to this. One is the large N limit, where the charge and the rank goes to infinity, keeping the gravitational charge fixed. This is the regime in which the black hole lives. The other one is the Cardi-like limit, where you hold fixed the rank of the theory and just scale the charge to infinity. Okay, we'll discuss both of these as we go along. So this is the index, this is the entropy. And now I want to tell you a little bit about the index explicitly. So here's the canonical index. It's written as an integral over unitary matrices of size n of an exponential of an infinite series, which is controlled by this so-called single letter index. Okay, that's the same trace as defined as the one that defines the index, but on the space of single letters, namely just the fields and the derivatives of the theory at one point. And this exponential then collects the letters into supersymmetric words, and then the integral projects onto the gauge invariant subspace. Okay, so now, as usual, if you want to calculate such integrals, you diagonalize the matrix, and because U is unitary, the small ui live on a circle. Okay, let's say they go between 0 and 1. These are eigenangles or eigenphases. And when you write the invariant Haar measure in terms of the flat measure of the eigenvalues, you pick up some van der Waals determinant, which is a two-particle interaction in the space of eigenvalues. And now notice that the original action itself is also a two-particle interaction. There's only trace U, dagger. And therefore, the whole action, the whole integral, can be written as an integral over n eigenvalues of an action, which is only which is a sum over pairs of eigenvalues with a potential depending only on the difference. Okay. So here I've written explicitly the single letter index for n equal 4 superangles. So you can write the potential explicitly as well in terms of some infinite product. Okay, this is a very nice function. There's lots to say about that, but I won't because of time. I just want to show that this is completely explicit. So now we have both sides of the problem, the first question completely well defined. So we can study this on a computer. So here are some results. So this is the x-axis is the charge, and the y-axis, the solid line is the black hole entropy formula, and these dots are the logarithm of the absolute value of the microcanonical index. Okay, and you see that even for very low rank, this is U2, U3, U4, etc., there's a remarkable agreement between these two. Then you begin to see some patterns. There are oscillations, which you see better here. Okay, and then at very small values of charge, something else happens. So all of these things are to be discussed. I'll make some comments about them. But the main question is, can we understand, can we explain this agreement from a theoretical point of view, analytically? Okay, and in order to do that, instead of considering the sequence of integers, it's useful to consider the canonical index, the generating function. Okay, so that's where we'll go next. In fact, in the ADS context, the masters of black hole thermodynamics had already taught that it's natural to consider the canonical ensemble. If you fix the temperature and the chemical potentials, then the black hole is some finite energy localized excitation in the bulk because of the gravitational well in ADS. And in this context, the basic ADS CFT equation is an equality between the partition functions, okay, with the usual map of parameters. Now, the gauge theory partition function is defined, as usual, as a thermal trace, which informs us about the microcanonical degeneracies. On the gravitational side, we do not have a Hilbert space understanding, and instead we take a path integral and try to write it as a sum over saddle points. Okay, saddle in the large N context means solution to the equation of motion. And at each saddle, you write the exponential of some effective action. And as Gibbons and Hawking taught us, after appropriately regularizing that action, that should be interpreted as the free energy of that saddle or of that phase of the theory. And we know some phases. We know empty ADS is the ADS black hole, and there can be many others which we don't know about. Okay, so these are two completely different ways of understanding the same thing. And in this beautiful paper of Witten, he explained how to understand these saddles or phases from the gauge theory ensemble. And in particular, how to understand the Hawking-Page phase transition as the deconfinement transition in gauge theory. Okay. So now we want to take this as a template, and now we want to apply this to our supersymmetric problem in a hope to do better. Okay, we want to be more precise and get more details. Okay. Now, when you try to do that, there is a conceptual problem that hits you. So people ask, why should the index be equal to the entropy? Okay, so here are my thoughts. Here's the index defined in gauge theory, trace with a minus 1 to the f. Now, by the usual Feynman understanding of quantum field theory, this trace is a path integral over gauge theory over S3 times S1, where the S1 is fibered with this parameter tau, and the fermions have supersymmetric conditions around the circle. Now, by our understanding of ADS-CFT, this path integral should be a path integral in the gravitational theory, whose boundary conditions are set by the same S3 times S1. And now the fermion, the gravitational fermion, the gravitini, should have supersymmetric conditions around the circle. Okay, so this is some gravitational version of the index. And the question is, does the supersymmetric black hole contribute to this index, okay, as a saddle point? Now, this is a subtle question because the Euclidean version of the supersymmetric black hole has a divergence. It's because of the fact that in the interior of ADS, instead of capping off with the horizon, there's an infinite throat. And relatedly, the temperature and chemical potentials all get frozen. So the usual Gibbons-Hawking procedure is singular. Okay. So the technical question is, can we regularize this solution and the associated products? So in order to do so, we have to sort of extend our solution space. So there's actually a known 4-parameter family of solutions which are not PPS, 2 angular momenta, a mass and a charge. And in this space, there's a one codimension surface of extremal solutions when the horizons approach each other, and another codimension 1 surface of supersymmetric solutions where the mass and charge are related. Okay? And our black hole lives here at the intersection. And over here, you can check that all the potential, this is the temperature, chemical potential for the charge, and this is for the angular momentum. They all got frozen. These are values in Planck units independent of the charges. Okay. So clearly what you have to do is to get out of this point and then approach it as a limit. Okay. And if you want to maintain a supersymmetry, then manifest supersymmetry, you do it in the horizontal direction. Okay. So this is what we did here. So you go here, and over here you redefine the new, redefined chemical potentials. So beta goes to infinity, omega minus omega star goes to 0, such that the small omega and phi for angular momentum and electric charge, these are finite. And when you measure these potentials somewhere here, you find that they're related as such. Okay. Now, what are the solutions over here? The solutions in the Lorentzian theory are not physical. They have closed time-like curves. But in the Euclidean theory, they're perfectly well defined. They're regular solutions, except with one property, that they're complex. Okay. So here I've taken real slice, and then there's a perfectly regular cigar-like solution with a capped horizon. And these are supersymmetric. And I should make one comment that on the cigar, there's only one spin structure allowed for the fermions, which is antiperiodic. But in fact, the solution has a holonomy of the R-symmetry gauge field such that when you take the fermion and transport it around the circle, it actually picks up a phase of +1. Okay, so these are supersymmetric, and therefore they contribute to this gravitational index. And now the question is how much? And now you can run the Gibbons-Hawking procedure because everything is well defined. So in terms of these redefined chemical potentials, you can calculate the on-shell action with the appropriate regularization. Okay, then you have to take a limit as beta goes to 0, but happily, this action is actually independent of beta, as you might expect from supersymmetry. So omega is 2 pi I tau, and with that notation, the free energy of the black hole, the on-shell action, is the following. It's pi I n squared over 27 times a cubic function here divided by a quadratic function. Okay. This function we'll see again and again in the following. Okay. So one point is that I want to re-emphasize that these solutions are complex, and we really don't understand all the rules of ADS-CFT with complex sources, especially at subleading orders in n, and there's some nice progress on this in a recent paper. Okay, now what have we achieved? So what we've done is to recast this question of Bekenstein and Hawking of whether this sequence of integers approaches this thermodynamic entropy to a question of ADS-CFT in the canonical ensemble, namely, is it true that the free energy of the black hole is asymptotically equal to the logarithm of the canonical index at some saddle point? Okay, and these two limits translate to two equivalent limits here. Okay, now the exponential growth of these sequence of integers translates in the canonical ensemble to the exponential growth of the canonical index itself. In other words, log of in has a singularity at tau equal to 0. Okay, and the saddle point lies somewhere very close to that. Okay, so that's where we'll move next. We want to study the saddle points and the singularities of this function. Okay, and now you can ask, well, why only tau equal to 0? There might be other singularities which signal other phases. Okay, so that's where we're going next. So this question of the behavior of this canonical index has been studied intensively in the last 3 years from different points of view and by different groups. And by now, we have a good picture of the answer. Okay, so let me present the answer first, and then I'll mention the methods. So we expect that the index can be written as some sum over saddles. Here's the Q plane. Q is e to the 2 pi tau over 3. And the interior of this is the unit disk, which is essentially the upper half plane in the tau variable. This function I of tau, the index, is perfectly holomorphic in the interior of the unit disk and potentially has singularities at the edge of the unit circle. Okay, and near that will lie the saddle points. Now, first we look near tau equal to 0, and there we find that in fact there is no growth. Okay, there's a bit of a surprise because of our expectation. Okay, the leading growth appears at the cube root of unity, and over there, the growth of log of in is the behavior of log of in is exactly that of the black hole free energy. Okay, so in order to study the black hole, you have to change variables tau goes to tau plus 1, and then zoom in tau goes to tau to 0. Okay, and then it was shown here that this change of variables is perfectly consistent with the ADS-CFT dictionary as applied to this complex saddle. Okay, so that's one method. Now, the second statement is that there is actually a complex conjugate saddle with the same growth as that of the black hole, but opposite phase. And in fact, at the end of the day, it's the sum of these two which provides for these oscillations that I showed you in these plots. The next statement is that, well, why only cube roots of unity? Generically, at any root of unity, there is an exponential growth of the index. Okay? There's some number theoretic condition which I'll show you in a second. So tau is a rational number minus n over m, and q is a root of unity. Okay? So these are the main statements, and I want to explain, well, just mention a little bit the methods. Okay, so first, let's zoom in towards the black hole. Okay, there we go. So remember that the index is written as this integral over eigenvalues defined by a potential, which is given by this infinite product. So as tau goes to 0, we need to do some asymptotic analysis of this infinite product, and the answer looks like this. The action, the potential, begins as 1 over tau square, then there's a 1 over tau, and then there are regular terms as tau goes to 0. Okay, so this is what the potential looks like, and therefore all the eigenvalues in this limit, they want to clump up. They all want to clump up at one point. Okay? And then you can evaluate the saddle point value of the integral and so on. And so in the original papers, in the first papers, we studied the singular terms, the 1 over tau square and 1 over tau and so on. And then this was extended in various directions. So apologies if I missed any paper, by the way, throughout the whole talk. Please email me later. I'll be more careful in the future. But more recently, in this nice paper, the all orders expansion, perturbation expansion, was found as tau goes to 0. Okay. And then in this paper with Arash, Arabi, Ardehali, we found the all orders expansion near every rational point. And this is what makes for this picture. There's one way to understand this picture that I just showed you. Okay. So by the way, this whole method can be done at finite n. You'll probably hear more about this in Leopaldo's talk. Okay, the second method is to directly study the matrix integral at large n, trying to use the usual large n techniques. Now, from all that I've said, it's natural that we should look for complex configurations. Now, complex here means complex in the eigenvalue plane, the U plane. Remember, originally U went from 0 to 1. This is work with Alejandro Cabo Bisset, who had this beautiful idea that we should study periodic configurations of eigenvalues. And that's because the potential is already periodic with period 1, and it's almost periodic with period tau. Okay, so we wanted to mirror that. So what we did was
5-minute warning, Samir.
Thank you. What we did was to deform the potential to make it explicitly doubly periodic. Okay. Now, with such a potential, it's very easy to show that the uniform distribution along any period is a saddle point. And therefore, you have a family of saddles labeled by m, n, which is any point on the lattice generated by 1 and tau. Now, to calculate the action of this saddle is more difficult, but we were lucky in that our deformation is very closely related to a function studied by number theorists called the Bloch-Wigner elliptic dilogarithm. And they give us a formula for the Fourier expansion of this function along the 2 periods. So it's a double Fourier expansion. And now if you have the Fourier series, and if you want to calculate the integral, this is not very difficult. It's essentially the average value, and so it's a 3-line calculation. Okay, so that's the sketch of the method. I should say that in the original paper with Alejandro, we had some doubly periodic extension of the potential, which was not meromorphic. And now in collaboration with mathematicians, Stavros, Garoufalidis, and Don Zakir, we understand that there's also a meromorphic version of the whole story. Okay. There's also a third method called the beta ansatz method, pioneered by Benini and Milan. I won't talk about this much. I want to say that whenever we can calculate anything in more than one way and we have control over it, the answers agree. So let me show you the answer now. So we have this set of saddles labeled by m, n. Tau goes to minus n over m. So tau tilde defined here goes to 0. And in this small parameter, the effective action is the following. It's n squared pi I over 27, the cubic function divided by the quadratic function that I showed you. This chi1 here is 0 or plus or minus 1, depending on some mod 3 condition. Plus a constant term, which I won't talk about because of time, which is also very interesting. Okay, so let's focus on this. So in particular, it means that the 0, 1 saddle, the action is 0. And the 1, 0 saddle, the action is here, is this, which is precisely the free energy of the black hole. Okay. So now let me show you all this in a picture. So this is the tau plane. And you can put yourself at one point and ask, which of these infinite number of saddles dominate in magnitude? So at imaginary tau equal to infinity, it's the 0, 1, it's the pure ADS that dominates. When you go towards tau equal to 0, it's the ADS black hole that dominates. So this is the new, I've shifted tau goes to tau plus 1. This orange region is the black hole. There's this complex conjugate saddle that you see here. Here I've cut off imaginary tau at 0.1. If you go down further, you see this very beautiful and rich picture that near every rational point, there's a new saddle point, and it has its own sort of chamber of where it dominates. Okay, it's also a very chaotic picture. And now I want to make some comments about this formula. Okay, so what we have at the moment is something like this, that the canonical index is a sum over rational 2 pairs of integers mn with this effective action that I just showed you. This can be extended to flavors and in other directions. I want to focus on this. Firstly, this is not an exact formula. We don't even know if these are the only saddle points. At large n, I think, well, I personally think that these are the only saddle points, but I don't have a proof yet. But even if this were the only saddle points, this is not supposed to be a convergent expansion. Instead, you think of this in the following sense. Whenever tau goes close to any of the rational points, this effective action dominates, and you have the complete perturbation expansion. Okay. So if you are in one of these chambers, you have the perturbative series of the entropy of the action, free energy, and then there are non-perturbative corrections, let's say in e to the minus 1 over tau. But if you stick to one point and then at that point, if you first take n squared to infinity, then all these non-perturbative effects completely die. Okay, so it becomes an exact formula. In other words, inside a chamber in the larger limit, you have an exact free energy formula, and the phase boundaries become sharp. That's one comment. This clearly is a prediction for a family of gravitational solutions. I should have said something. Oh, I won't say it. Remember that the effective action had a 1 over m in it. Maybe I'll show very quickly. Here, it's a 1 over m here. And that clearly means the entropy goes down by m. That suggests an orbifold. And this was understood. The solution was constructed in this recent paper. Okay, this is my last point. That quite surprisingly, every term in this expansion, this effective action, can be derived completely from the three-dimensional effective field theory. So think of this as S3 times S1 and do a Kaluza-Klein reduction on the S1. It's like a Cardi philosophy. It's not a vacuum energy, but you can write down what is the effective field theory in the 3 dimensions. And that is governed by some Chern-Simons theory. You have to integrate out all the Kaluza-Klein modes. You can do that. And what is important is both the background as well as the dynamical fields. And surprisingly, you find this full effective action, including the black hole growth, as well as all the subleading coefficients. Okay, so then that essentially finishes my time as well as my talk. I'll leave you with a summary of things that I discussed and also things that I would have liked to discuss but didn't have time. Thank you very much for your attention.
Perfect, Samir. Thank you so much. So let's react with a warm applause. So thank you. Okay, so it's perfect because it gives us a few minutes for questions. So please use the raise hand feature if you have questions for Samir. Otherwise, I'll start interrogating him. But okay, Yifan Wang, please ask a question.
Hi, Samir. Thanks for a nice talk. So just have a question about this expansion that you have in terms of the sum over this saddles. Can I understand this through some modular property of the index?
Okay, thank you very much. That's a very nice question. The answer is no, and then maybe. So, so indeed, in the last 5 years, so the first thing many people guessed was, well, maybe just like in 2 dimensions, this
yes.
one also has a modular property. But it's clear that under SL2Z, there is no modular transformation. So by modular transformation, I should make it clear. I mean that there is no automorphy property, no symmetry. Okay, there is a very interesting relation already due to Felder and Varchenko that at one point in time, one function is related to another function. So this was already there. That's something like a co-cycle property. So there is no, as far as we understand, modular automorphy property. However, it looks, and another way to understand it is that the effective action begins with 1 over tau square. As you know very well, modular forms begin with 1 over tau, so it cannot be an SL2Z modular. However, in this work with Alejandro, what we understood is that there is some secret modular type property underlying this, and this is because of these relations to this Bloch-Wigner function. Right. And the statement is that that this function is what is called a period function. So roughly, very roughly speaking, the lack of modularity can be controlled by another function. So we can discuss this more. But there is something, and there's work in progress with mathematicians.
And do you think this notion of this certain lack of modularity can be also generalized to other 4D-into-1 theories?
Yeah, I think if you understand this n equal to 4 theory, this is not an easy problem. If you understand this fully in n equal to 4, then generalizing it is I think, less difficult.
Okay, thank you.
Okay, next on the list, Mukund, please go ahead.
Hi, Samir. I was curious if for these other solutions you have, which are complex Euclidean solutions, is a Lorentzian causal structure understood?
I don't understand it.
So are they
short answer?
So it sounds then like we understand what solutions in the Euclidean quantum gravity path integral contribute to the entropy.
Yes.
But we don't have an interpretation in terms of some
state
horizon states in some horizon or just Lorentzian geometries.
Okay, so two answers. Firstly, I agree, as you said it. And in fact, let me remind you that for CFT2 as well, it's the same thing. If you remember this Maldacena-Strominger family and this fairy tale expansion, the same thing. Two of the saddles are understood in the Lorentzian theory and the other infinite numbers are not. So I certainly don't have an understanding in terms of horizon geometries, but there is some understanding in terms of what the states are in the Yang-Mills theory itself, which is also interesting. I had no time to talk about this at all. I'm happy to discuss that.
Great. Thanks.
Okay, great. Shiraz, please go ahead.
Hi, Samir. Thanks for the really nice talk. If I understand right, the entropy that comes out of this index at charges or energies of order n squared is given by black holes, and at charges of order 1 in units of n is given by multigravitons. Do we know what the formula is for the index entropy at charges of order n or n to the 3/2?
So of course we know the formula, but I guess you mean, do we have a good sort of nice analytic expression for the?
Yeah, can you write down d of n in that region? And yeah.
Not so. This is exactly this point. So let me say I don't have anything now, but I think this can be done. I don't know exactly whether it's n to 3/2 or not, but there is. Maybe let me just show you a picture. I had something of this sort. So this is exactly what you said. So this was my entropy plot. These are the gravitons. I can discuss this more later, but let me just go to what you said here. It is over here. So these were my entropy plots at very small charges. Over here, as you said, you understand this completely in terms of gravitons. You can see explicitly that there is an agreement with the graviton function. And then this index, which are these dots. So this red one is the graviton index. These one are Yang-Mills. So over here it agrees with graviton, then it starts increasing, and then it goes up to this black hole. This is exactly what you said. So what we understand is, analytically we understand this point. Analytically we understand the asymptotics. So this part I showed you in the talk. And now usually, so there are two expansions one can do. So either coming from up or coming from down. Going from down is something that's not been studied much. So what I understood in my paper is an analytic understanding of why or of how the index exactly equals the graviton, the index exactly equal to the graviton index up to some value of charge which is equal to 2 times n. But there's an expansion where you can start studying these deviations. Okay. So that's one possible approach. I'm just telling you whatever I know. And the other possible approach is to start from up, so and then start coming down in charge. Okay, so you can try to then do both of these and see if there's an interpolating formula. This is where things stand at the moment. But my hope is that there'll be more analytic structure to be understood here.
Okay, I think sorry, Shiraz, you wanted to. Do you have
Just
time?
to say thank you.
Oh, sorry. Okay. So let's move on to the next talk. And there will be a discussion right after this. And so please hold your, I know there were more questions for Samir, but okay, final round of applause. And please, ask more questions to Samir during the black hole discussion round. Don't forget about that, or via Slack as well. And now let's start with Leo. Very good. So next we have Leopaldo Pando-Zayas from the University of Michigan, and he will tell us about logarithmic corrections to the entropy of ADS black holes. Please, Leo, go ahead.
So thank you very much. Thanks to the organizer. This is clearly a challenging time, and a lot of effort has gone into putting this conference, so thanks a lot. My title is, for some people, self-explanatory, logarithmic corrections to the entropy of black holes. So it goes nicely after Samir's talk. But let me nevertheless motivate a little bit why this is a reasonable and interesting thing to do. So first of all, the Bekenstein-Hawking entropy is very universal, and we all like this formula as sort of a gateway to quantum gravity. But it is so universal that that it might obscure whether your computation of the degrees of freedom or your treatment of the degrees of freedom is really correct. So in the cheesy analogy of black holes being the hydrogen atom of quantum gravity, this is like getting the Bohr energy levels correct, but that doesn't tell you that you know actually how to treat the electron. So you look for corrections to this formula. There are two kinds of corrections that come from treating gravity as an effective field theory. So there are massive fields that you integrate and they give you higher curvature corrections, which here I have denoted as ... There are other kinds of corrections that come from massless fields, and they contribute to this logarithmic correction. So just in a one sentence statement of this talk is I'm going to explain some of the progress in understanding this particular coefficient a logarithmic correction to the entropy in the context of ADS-CFT. So we have field theory on one side and gravity on the other. And again, this goes very nicely after Samir's talk. The setup was explained in the context of ADS-CFT. We have two ways to approach this coefficient, and we want to make sure that we understand how to do it and whether it matches or not. So there is in fact a long history of using this sort of test to better understand the degrees of freedom behind accounting. So I'm borrowing here from a very eloquent review of Ashok Sen. He used this subtitle, an infrared window into UV physics. And the reason is because the coefficient of the logarithmic corrections is determined macroscopically on the gravity side from the massless particle spectrum. And it is somehow insensitive to the UV completion of the theory. So if you compute it in your supergravity and you have this number, and I am a string theorist or a loop quantum gravity person, and I tell you I did my microscopic computation, I can check whether you are correct or not. This is kind of a litmus test. So for any enumeration of quantum black hole microstates, this coefficient that measures some sort of scaling of charges must agree with what the low energy supergravity says. And of course, it has been used by Ashok Sen and collaborators to check various asymptotically flat black holes in string theory and provide a precision test for the Strominger-Baffa counting. This was done by Sen. There are a number of reviews. And this can be done also to challenge loop quantum gravity, also by Ashok. The important thing that I want to highlight is that behind this whole set of computations in asymptotically flat black holes, there is this quantum entropy formula, which essentially is a prescription for computing this coefficient, but it builds up it builds on another formula, which I will discuss. So we would like to have some sort of gadget like the quantum entropy formula for ADS black hole that will tell us how to go about computing these corrections more generally, rather than case by case. And other applications of this sort of approach was presented by this paper here, Pathak, Porfiriadis, Strominger, and Varela, to check a microscopic realization of Kerr-CFT. In the context of ADS-CFT, a very beautiful application was also was in this paper by the Charya Grassi, Marino Sen, where they study the free energy of ABGM theory. And in general, you can go for any 3D n equal 2 theory. These free energies on the 3 sphere are usually given exactly by an Airy function, and you can expand for large n and look at the coefficient, and this coefficient was reproduced in this beautiful paper from 11-dimensional supergravity. So in this talk, you can view this talk as or what I'm going to explain as a continuation of this sort of well-respected, let's say, tradition. So this is the outline. I will tell you first a little bit about how to do the microscopic computation for the ABGM theory. But this, again, very quickly, you will see that this is true for a large class of 3D n equal 2 Chern-Simons matter theory. But my focus is always on basically logarithmic correction. So I have to go beyond large n. I will then describe the gravity macroscopic computation. And after that, of course, I will turn to the n=4 superconformal index, where we can essentially try to run the same script. In this case, because we would like to have a fairly universal description of how to go about this in the context of the ADS5 black hole, I will also use a version of CFT to estimate these logarithmic corrections. So here's ABGM theory. It was mentioned yesterday by Shiraz, and I think in general is an object that we know. Here's written in n=2 language, so it's a quiver with two gauge groups, UN plus UN, and the Chern-Simons levels are k and minus k. The index that is of relevance here is the topologically twisted index. You can think about it in the Hamiltonian formulation as more or less along the same lines that Samir explained. It's a Witten index with some that you decorate with some charges, flavor charges in this case, and it counts half BPS states. So the formula for any 3D n=2 theory, you can write a formula for the index. This formula is obtained by localization. I believe Zaffaroni has given talks at previous strings conference about this subject, but roughly, if you think about ABGM, there are two gauge groups. So you see the contribution for the vector multiplets here in the denominator. Then you have two set of bifundamentals. Once I call A in my quiver diagrams, they contribute to the partition function, to the index like this, and then the B's for 3 and 4, they contribute. So this is now by now a mature subject. So given a 3D n=2 field theory, you can compute the index basically algorithmically. What is important is that the evaluation here, you have to sum over some solutions of equations that look like the Bethe-Ansatz equation. So it's called the Bethe-Ansatz approach, but it's very algorithmic. So you solve these equations, you plug the solutions, and you have the index. So one important advantage of this approach is that this is an expression that is exactly in n, granted that you have of the solution of the Bethe-Ansatz equation. So it's very easy to put this in a computer and study numerically, which is what we did. So if you study this in the Larsen limit for k=1, so that this is due to ADS4 times 7, the leading piece goes as n to the 3/2. This blue term here, it's very symmetric. And it was obtained by Benini, Christophe, and Zaffaroni in 2015. And that reproduces the Bekenstein-Hawking entropy of the dual magnetically charged black holes in ADS4 × S7. So Na here, sorry, are magnetic charges, and delta are their chemical potential, but you have to, there's an extremization procedure. Again, this is all sort of background. The key important result is that when you compute this index on field theory, you get these logarithmic corrections. Again, this was obtained with my colleague Jim Liu and student Vimal Rati and Wenli Zhao, who's now a PhD student at Princeton and had a very nice paper today. So this, in fact, as I was explaining, this I can do more generally for a large class of Chern-Simons matter theories. I'm interested, of course, in those that have known supergravity duals. So I can essentially think of replacing the 7-dimensional sphere by any Sasaki-Einstein's 7 manifold. There's a list here of explicit examples that we worked out in this paper with Yuji. And for all of them, you get that the logarithmic term is minus ½ log of n. So the natural question at this point is, of course, can we reproduce this coefficient from the gravity side? From the gravity side, you have a black hole, some background, some gravitational background, and you're interested in quadratic fluctuations around those background. Once you integrate those, you end up with essentially a computation of determinants. In the context of a curved space, of course, a very efficient way that is respects to some extent diffeomorphic invariance is to use the Higgs kernel expansion. So you can write these determinants, in terms of the Higgs kernel, which again, this is roughly a way to think about it, but it contains also information about zero modes. So you have to be very careful and subtract the zero modes. And another important fact is that this Higgs kernel admits a silly DeWitt expansion for a small tau, but because in this talk we are interested in logarithmic terms, you see that all I really care about is the terms from the Higgs kernel here that are tau independent, because the logarithmic part is already going to come from this term. So I am interested in a particular silly DeWitt coefficient, which would be n equals d over 2. So then, because of these operators are usually Laplace-like operator or maybe Dirac operator, but they are kinetic operators, it is natural to also think of this parameter as rescaling naturally. And this is, you can see how the scaling structure enters into the answer. So the final answer is essentially a formula of this type. So the silly DeWitt coefficient of d over 2, and then subtract the zero modes. And of course, you still have to add the zero modes as appropriate. Now, on very general grounds, this coefficient vanishes in odd-dimensional spaces. There can be contributions, subtle contribution for boundary, but in general, from bulk, it will be zero, just because you cannot write the right curvature invariant of a given weight. So I guess for some people, this is known as the integrated trace anomaly. This is mathematically the same object, but you can see that the origin is slightly different here. I'm thinking of, I have a theory with some scaling defined, and I'm looking at the coefficient as that scale change. All right, so let me just finish this very quick introduction. Again, this is all very standard. There are many books that help you compute these kind of contributions. But the key facts that I want to highlight is that the coefficient of the log is independent. That coefficient is independent of the cutoff. You can change your cutoff and that number will not change. In odd-dimensional spaces, and we are interested in 11-dimensional supergravity, the log can only come from zero modes, okay, on boundary modes. So what we need to do to compute the partition function is to subtract the zero modes, because you counted them using the Higgs kernel, and then add them appropriately with this beta, which essentially explain how to, the appropriate integration for the zero modes. And then, of course, consider the Gauss contribution. So let me, oops. So let me very briefly explain what the result is. So there's a two-form zero mode in ADS4. There's more generally, well, there's a two-form zero mode in ADS4, and that two-form zero mode contribute to the ghost. You need a series of ghosts to quantize the three form of 11-dimensional supergravity. One of them is a two-form ghost. This is work by Siegel in the 80s, and this is how it contributes to the partition function. So again, this depends on how this beta 2 is how you have to add to form zero mode in 11-dimensional supergravity, and it is essentially 7.5. Many of these computations were performed by Sen in the context that I explained at the beginning, and then you have to count how many zero modes, to form zero modes you have. In this case, there's this subtlety on how to approach the stream of black hole, and you are instructed to approach it through the non-streamer branch. And here's the answer. If you use the ADS-CFT dictionary that relates the scale to the rank of the gauge group, you will see perfect agreement. All right, so this is the computation on the gravity side. It matches nicely the field theory side. Let me explain that this is also the result for the large class of ADS-CFT duals that I explained at the beginning. So for all these Sasaki-Einstein manifold, I obtain on the field theory side the same -1/2. So I have to make sure, or I have to understand how on the gravity side they are the same. So the two-form zero mode that contributed came from ADS4, and there was nothing there was nothing that could contribute on a 7. So what I really want to make sure is that there's no one-form zero mode in any of these Sasaki-Einstein, because otherwise I will have a contribution coming from the three form from the three form. But it is established that in 7-dimensional compound Einstein manifold of positive curvatures, all of these all satisfy this property, there is no zero mode. So the first the Laplace of one form's harmonics is is bounded. So we immediately get the result for all these spaces.
Just
now,
10-minute
yes.
warning.
Sorry?
Just 10-minute warning. That's okay.
Thanks. All right, so I explained this computation for black holes that came from this middle column here for M2 brains probing cone over Son Sasaki Einstein. There are other black holes that you can obtain if you consider an M5 brain wrapping a hyperbolic 3-manifold. In this case, from the field theory side, you can compute, well, there's a systematic algorithm to compute the field theory, and then there's on top of that, there's the 3D correspondence that maps data in the 3D theory to some Chern-Simon invariants, which are known. So you know now the field theory partition function analytically and very clearly, and you can do the computation on the gravity side as along the lines of what I explained. And this essentially gives you this formula that we obtained with Dongmin Gang, Nawu Kim, and then with Francesco Benini and Dongmin Gang in these two papers. This is a slight generalization. Of course, the scaling of n is slightly different for this kind of supergravity solutions. But you see B1 here is the first Betti number. So I will have 1-form 0 modes coming from the hyperbolic 3-manifold, and they will contribute. And G is because I'm considering the theory not on S1 plus S2, but on S1 times an arbitrary Riemann surface of genus G. So this formula, again, was obtained on both sides, this logarithmic correction on the field theory and on the gravity side, and also much. All right, so one thing that I want to explain is that a lot of this work has been done on sort of on case-by-case basis. So there's a ADS-CFT pair, and you compute, and the result agree. But it would be really nice to have something like sense classical entropy function. This is a function. This is a function that basically will give you the Wolf entropy. So this would be the entropy that has all the higher curvature contributions. So this is a very important problem. We still, so there's been some work, of course, in extending that construction of the classical entropy formula in ADS spaces by Morales and Sanleven and Goulart. And recently I reviewed it with Joel Gosch, and currently Joel Gosch, we did ADS4, and ADS5 we are discussing with Joel Gosch and Victor Godet. We think that this is probably a more efficient way to capture the other kind of correction that I have not talked to you about, this higher curvature corrections, but there is still a number of details to work out. The quantum entropy formula of Sen has been very successful for asymptotically flat space. What I have shown to you is that at least for ADS4 black holes, the formula, in fact, does not give you the right answer. The right answer we are getting is by using the full geometry, the ADS4 asymptotic geometry. Let me show you just very briefly. If you take the near horizon geometry of the black hole, you will have a space that is ADS2 cross M9. M9 now would be S2 bundle over S7, and you can run the same computation. Now it's a little bit more involved. There are more zero modes. Generically in ADS2M, you have informed zero modes. So in ADS2, you will have gravitino zero mode, graviton zero mode, 1-form zero mode, and then you can form 3-form zero modes by wedging this one forming ADS2 with the 2 forming in M9. And the answer is known, was also simultaneously obtained by Jion and Lal, and does not agree with the quantum entropy formula. So we're looking for some sort of big machinery that can help us understand this. In this sense, it was great that there was this developments about the ADS5 black holes that Samir just explained very beautifully. These 3 papers started that revolution. In fact, my background is a picture that I use in a Viewpoint article describing this very interesting development, but it has been extended to ADS4, ADS6, ADS7. And one question that we would like to have is, so given that, so we have using ADS-CFT at the, let me go here, using ADS-CFT as an arrow here, we have been able to understand microscopically the entropy of ADS black hole, but perhaps because it's such a universal quantity, there can be alternative approaches to it. So maybe we can take some sort of limit, near horizon limit, Alhazen, or maybe Barton-Horowitz limit, kind of like Kerr CFT, and have an explanation for that entropy from this near horizon description. Okay, I will. So this is for the ADS5 black holes.
Sorry, just 5-minute warning.
Okay, thanks. For the ADS5 black hole, so there's the index that Samir explained. He also pointed out that in this paper, in a paper with my student Gonzalez Lescano and Hong Liu from Michigan, and my colleague Jim Liu, we explored the index beyond to the logarithmic approximation, which is where we are interested, and we obtained this number. So coefficient is 1. I will not go into the details because there are 2 approximations Samir already explained. There's the Cardi-like limit, and there's a large n that uses the Bethe-Ansatz approach. But in different ways that we play with the formula, we came up with the same coefficient. This coefficient then was confirmed by another analysis for other gauge groups by Amariti, Fazzi, and Segari. And it has also been given an effective field theory explanation as a log of the degeneracy of vacua in these 2 recent papers by Kazani, Komagorsky, and Ardehali and Murthy. So we are fairly confident on this log of n from the field theory side. From the gravity side, we have not yet been able to reproduce it, but I want to give you some insight. So from this near horizon geometry that I explained, some sort of more general way of looking at this, which essentially is Kerr CFT with extra global U1 charges, you can compute the leading piece and of course match the entropy, but you can go ahead and look at logarithmic corrections in this framework and you get precisely the same result. So, and that extends also to the rotating string. So the main message that I have, there were a lot of computations, but let me make it. Let me try to crystallize what I was saying in the context of ADS. One has to be a little bit more careful about. There's yet not a universal formula or a quantum entropy formula that we can use. So we go on cases by cases. In the case of ADS4, there was some obstruction to moving to the near horizon region because there were 0 modes, and in that case, of course, you have to look at the full space. In the case of ADS5, there were no 0 modes, and you can go to the near horizon, and the computation seems to agree on those 2 points of view. That's, I think, is sort of where this is pointing. I did not have time to talk about, so once you have a CFT2 description of the black hole that is reliable because there are no 0 modes obstructing it, you can try to apply an analysis a la Maldacena and get some insight into Hawking radiation, and that we did with Juan. As I said, it's still outstanding to compute the log directly from type 2b supergravity, but there's some small progress. The question of higher curvature corrections, the other type of corrections that in my first slide will essentially ... I think that there's been interesting, exciting work by Bobiev, Charles, Christophe, and Reis. But perhaps I think the right conceptual home for those is the Wolf formula, which one can hope to get as a generalization of sense entropy formula. And I have some ongoing work on that. So I want to finish just by stating that, so ADS-CFT has de facto, right? Because we have a unitary description of black holes, solve many of the puzzles, but we have not seen the solution explicitly. And I think this is a very exciting time where some of these questions are being answered very explicitly. So thank you very much.
Great, thank you so much, Leo. Warm round of applause. Thanks. Well, I don't know if you wanted to keep your slides up in case
I can keep them up.
And you wanted to point to them, but
right.
It's also fine to not do it that way. But okay, let's start seeing who wants to raise their hand first. Don't be shy. Okay, maybe I'll ask a question very quickly. Just to put things in context, this obstruction of building the quantum entropy function for the ADS black holes, is it related to the nature of the attractor mechanism in ADS?
I think for the quantum entropy formula, so I am a little bit ambivalent about this. So I think the quantum entropy formula is obstructed by really zero modes that that you can see in the higher dimensional ADS, but maybe not in the lower dimensional ADS description. The attractor mechanism, at least at the level of Bekenstein-Hawking entropy, everything seems to work fine.
Okay.
So it is when you try to say I have now not only well, I call it classical, but it's probably a misnomer. So the wall entropy seems to work from near horizon, but we have trouble with this other part.
Okay, so it's on the quantum. Okay.
Yeah.
Thanks. I'll keep on asking questions, but again. Oh, there, so hard. Please go ahead.
Hi, Leopoldo. Thanks for the nice talk.
Sure.
Given, sorry that I cannot turn on the camera. I'm in the middle of a move. Given that in the field theory side, this log n can be explained by the degeneracy of aqua. Essentially, it's the same degeneracy that you find in a deconfined gauge theory. And wouldn't that mean that on the ADS side, that should also correspond to some flat connections, like different saddle points with some different flat connections that are very similar to the degeneracy of aqua that you find in any deconfined gravity dual?
Yeah, yes, I think that's precisely correct. So I think on the field theory side, now, again, thanks to this recent work on the effective field theory of the index, I think we understand that from different points of view. Also, just from the slightly more computational point of view, we have, if you look at it from Bete-Ansat's approach, you can simply see that this is a degeneracy in the holonomies. So this part I think we understand. But what we don't understand is how it comes from type 2b supergravity, let's say.
I would think it's just the two-form gauge field that is the gauge field of the one-form symmetry on the boundary. There is a two-form gauge field in the bulk, which is the gauge field that corresponds to the discrete one-form symmetry on the boundary. And since the discrete symmetry in the boundary is spontaneously broken, that's where you get the log n from. It should correspond to some flat connections of this two-form gauge field.
I see.
Okay, I'll ask another short question since I don't see any hand raised and I'm tempted. So for the ADS5 case, you are imagining doing the computation in 10 dimensions, right? So
yes.
From ADS5 times S5. So in that perspective, the heap kernel is not going to be trivial. Like you'll get contributions from.
Yes, but that is true. However, if you actually sit down and try to do them, there is an amazing amount of cancellations. So I think, and I was secretly hoping for the answer, and the answer is very universal. I did not emphasize it, but it's true for any ADS5 black hole in ADS5 plus Sasaki-Einstein 5. So it's again very universal. The field theory we know is completely for many n equal 1 Kuiper gauge theories is precisely the same value. So I knew it had to. Well, I know it has to come from something perhaps along the lines of what Zohar just mentioned. So because let's say the width coefficient that you want to compute is non-trivial, but because of the structure of the supergravity solution, I have seen an insane amount of cancellation. So it looks like all those cancel, and then you're left with one counting argument.
But is it important that the background is supersymmetric, or do you think it would also hold if the black hole itself is non-BPS? Because there were some also miraculous cancellations in 4D.
Yeah, no, I am aware, but I don't know. I don't want to. Yeah, I don't want to commit to that.
Okay. Thank you. So I think I don't see any more hand raised. So this is the last call. So let's thank again Leo for a really interesting talk. And now, Pedro, I think you're the boss, right?
Yes, very good. Thank you very much. Thank you. So we'll move to the last discussion of the day and the first black hole discussion of the conference. So let me just remind people. So Juan and Samir are totally in charge of the first 20 minutes. And the goal is in the last 30 minutes to have an informal discussion. And one thing I forgot to emphasize in the last meeting is that there is a Slack channel where 300 people are already there asking a few questions. So do join and ask more questions there after the discussion if we didn't have time. And use also the discussion to ask questions about related talks of the conference that we did not have time to. So Juan or Samir, I don't know who is going to go first, please.
Juan, you're muted.
You are muted, yeah.
Well, thanks to the organizers for organizing this wonderful conference. I will first make a few remarks, and then Samir will make few remarks also. So in the 70s, people derived the black hole entropy formula, and they suggested that black holes could be viewed as quantum systems when they are viewed from outside, and that there should be e to the area over 4G Newton states. And also, in addition, it should evolve unitarily. In other words, we can replace the geometry by a quantum system for all questions that we can ask about the black hole as long as we are sitting outside. But the question is, what are these states? Now, there are some key results from string theory. And the first result was in the context of supersymmetric string theories, and in addition, supersymmetric black holes in those supersymmetric string theories. Those are black holes that are charged and are extrema black holes. And these black holes can be counted precisely using strings and d-branes. And this reproduces the area formula, and not only that, but corrections to the formula, as we just saw in Pando-Zayas' talk. And we also saw the talk by Murthy, where we see that this project continues, and we get more and more precise and completely precise formulas for the entropy of the state. However, all these computations involve starting from the black hole picture and then changing some coupling or the expectation value of some field to a regime where we can do a weak coupling calculation in terms of, for example, branes and strings, and we do the counting using this picture. And then we argue that because we are computing an index or a protected quantity, that number should be the same also in the strong coupling picture where we do have the black hole geometry. And there are many alternative limits and possible counting schemes. We could also represent the black hole as some oscillating branes or as some gas of gluons, as we saw in the last two talks. But the question is whether we can see these microstates directly at strong coupling and using the Lorentzian gravity description. So what are these microstates as states in the Lorentzian gravity description? So it's been a project of trying to construct BPS supersymmetric fastballs. So this would be large families of smooth horizonless gravity solutions. And the state of the art is some papers, a series of papers by these authors and many others. And they appear to reproduce a fraction less than 1 of the entropy. So you could view this as a half empty, half full glass, but it looks like there might be such solutions. But one question is how this ADS2 description, or the black hole description, which contains an ADS2 near horizon geometry, how is that geometry connected with other possible solutions? Is that an average? And in particular, a physical question is, what geometry do I see when I fall into a black hole? Now, there are also black holes with non-zero temperature, and from ADS-CFT, we can certainly consider these black holes, and we can view them as fluids or states in strongly interacting quantum systems. And when we can calculate the entropy and we find quantitative agreement, this agreement is usually based on the Cardy formula for ADF3 times CFT2 or some variation of this. There is one case where numerical computations were done in the case of the zero-brane quantum mechanics, so that's a sort of a different approach for this problem. Now, there is also a separate development, which is a better understanding of entropy formulas. As I said in the beginning, these pictures of black holes are based on the original Bekenstein-Hawking entropy for the black hole. But now we have better formulas that give us the von Neumann entropy of the black hole. These are developments that started from the Ruta-Kanagi formula and generalizations. And the main result is that they have shown that the von Neumann entropy of a black hole depends on the geometry of the interior, the geometry we have in the interior. So this would suggest that the microstate of a black hole is somehow encoded in its interior, at least up to the RT surface. So if we have a definite microstate, we expect that the RT surface should be trivial. And but there are some problems or maybe puzzles, which is that the number of possible interiors is apparently larger than the number of microstates. So this is this bag of gold discussion where we can have very large spaces behind the horizon. And the way this problem is addressed is through these ideas of state dependence and code subspaces and so on, which I don't have time to discuss. And also there is another problem, which is that these geometries, when you evolve them in time, they contain a singularity. And hopefully this is just a speculation, maybe these two problems cancel each other, that somehow the singularity might play some role in cutting down the number of microstates or in explaining some aspects of black holes. And I think this is an exciting possibility, because perhaps the proper understanding of microstates might teach us something about the singularity. But these last two sentences are just my own speculations. Recently also, there's been a lot of progress that I guess will be reviewed in other review talks, or in other review talks and discussions on the page curve and the long time behavior of black holes. And these recent results were obtained using wormholes, and these are just new topologies of space-time. And they give results that can be interpreted as averaging over coupling constants in the quantum system. And in this situation, one can wonder whether the microstates should be more properly understood in a many universe wave function. So we might need the wave function of many universes to properly understand the black hole microstates. And certainly this is a point of view that's been recently highlighted in papers, for example, of Maroff and Maxwell. Now, I would like to finish just presenting one example of a string theory solution. This is not really a black hole problem, but it's an example of a string theory background with some kind of known microstates, you could say. So it's a classical Euclidean solution with entropy, which goes like 1 over G Newton, where the states that give rise to this entropy are known. And this is the so-called self-gravitating string solution of Horowitz and Polchinski. And the idea is we consider a highly excited string state that self-gravitates, and that's supposed to be equal to a certain, or is supposed to be related to a certain smooth solution of the Euclidean background. So we can think of the left-hand side as we can think of this as a kind of string star. So we have a highly excited thermal string, and which is described by some smooth Euclidean solution involving a winding condensate. So this solution involving the winding condensate is a solution to the Euclidean action, which contains gravity and also a winding mode. So it contains, we have a Euclidean time circle of length beta, and we have chi is a field corresponding to the winding mode on the Euclidean circle. And this solution is reasonable and can be approximated by this action as long as we are very close to the Hagedorn temperature, slightly below the Hagedorn temperature. And in this case, the size of the solution is larger than the string scale. And this works very nicely in 4 dimensions. I have here some formulas on how the size and the mass of the state depend on the deviation, but these are not important for us. What I want to emphasize is that from this action, you can derive the free energy, and you can also in particular derive that the entropy formula, which takes this form. So it's again an entropy formula for this classical solution. It arises because the mass of the winding mode depends on beta. So in this case, we know what the microstates are. They are just simply these oscillating string solutions. Now, as an exercise, you can imagine generalizing this for the black hole case. I'm not saying that the black hole case will be given in terms of strings, though many people have said that. That might be a possibility, but the question is, well, this case is not exactly identical to the black hole case. The circle never shrinks and so on. There is no horizon, blah, blah, blah. But it's similar I think it's similar in spirit in the sense that we have a Euclidean solution similar to the black hole Euclidean solution, which gives us the entropy, but we would like to find what the Lorentzian microstates are. Okay, thank you.
Thanks a lot, Juan. And let's switch to Samir, and then we will. Yeah, so let's maybe all thank Juan while Samir shares his screen. Perfect. And you did exactly 10 minutes, so it was perfect.
Okay, so can you see the screen and the cursor also?
Yes.
Thank you.
Yeah.
Okay,
Please.
thank you for the invitation to speak at this wonderful conference. So I'll just summarize what how I think about black holes and what I think we have learned from string theory. So here is the black hole information paradox. You start with a star, you collapse it, it becomes a black hole that emits entangled pairs, which up to some small corrections, which could come from any quantum gravity effects, are entangled between the outside and the inside member. So here is a picture where you see entangled pairs coming out. And so the entanglement keeps rising with the number of emission steps, and that leads to a problem at the endpoint of evaporation. This is a very robust problem. So if somebody says they'll try to make small corrections to each pair, epsilon is small, you can't actually trade that against the fact that n is large and say that somehow you'll delicately encode all the entanglement and in the end you'll be okay. Even if you take into account these small corrections, the entropy of entanglement actually keeps growing. So if you put corrections of order epsilon, you can't really lower the graph by more than 2 epsilon. So in fact, what one learns from all this is that the page curve actually cannot come down if 2 things are true. If the horizon dynamics can be approximated in any way by semi-classical evolution, which means the horizon in any description looks like this room. And second, in the description, in the proof of this small correction theorem, one does assume that there are no long distance, non-local effects. And so I'll come to that in a minute. Okay, so what's the solution to the puzzle in that case? A lot of people have worked on this thing which we call the fuzzball paradigm. And there one just says that if you start with the bound state of strings and branes, at weak coupling, it might have size of Planck length or string length. At strong coupling, what do we get? So naively, you might think that it will still be a small core of Planck size at the center, but around it, you will develop a large horizon, which is basically like the vacuum here. But that's not what you find. If you try to estimate the size of this bound state, you find that the size of bound states in string theory grows with the number of branes in it and with the coupling. And in fact, the estimate of this size performed many years ago shows that it's of the same order as the black hole radius for that much mass and charges. So then this suggests that maybe you just never get a proper horizon in string theory, and therefore you never have a problem. Everything is like a star or a planet. And now after this initial estimate, many, many examples of string bound states have been constructed. And in each case, one finds that you get a fuzzball instead of a horizon. So here is my cartoon of what the fuzzball program has been doing. So initially so all the states of the, let's say the D1, D5, P bar, like the extreme or near extreme or black hole can be written in terms of some 5 branes, which are in green here, some D1 branes, which are in red here, and momentum and anti-momentum modes, which are in blue. So these are all the states can be written in that form. You can do initially all the 2 charge extremal states were made, and one found they were all fuzzballs, no horizons. And then slowly more and more of this graph was picked up. And so basically, it's a little bit like the picture we have for M theory. You first capture all its limits, which are essentially the string theories, and you can perturb around them. So here we have all these kind of states which have been explored. And then in the middle, of course, you can say it's very messy, so we can't make a generic black hole state. Of course, you wouldn't want to. But here, all these states actually radiate. So then the small correction theorem catches you and then tells you if these states in the middle are not fuzzballs, then you have to actually have one of these 3 things in your theory, either non-locality over long distances, or remnants, or a non-unitarity. So you are either forced into one of these 3, but if you don't like those, which I don't, then in fact, whatever you're learning from these limiting cases will have to continue to the inside also. So I think with all the things that we know, it's hard to imagine, at least for me, that there is any alternative to the fuzzball paradigm in string theory, that you simply get a fuzzball and we are done. So recently there has been a lot of interest in what I'll call the wormhole paradigm. And there the idea might be that you want to maintain some kind of a semi-classical horizon dynamics in some approximation. But then, well, to solve the information puzzle and get the page curve to come down, you might have non-local effects of various kinds. So I do not find myself in agreement with at least what I have understood of these ideas. And so in this context, let me just try to say one thing, and that is, let me just try to write down what is the constraint we get from the small correction theorem on any ideas of this kind that one might want to try. So let's consider a scenario that is very tempting, but where the page curve will not come down. So please look at these assumptions and just keep them in mind to see in what situation the small correction theorem will tell you the page curve does not come down. So let's assume that the exact description of the black hole is something very complicated. This is the exact string theory. You can put it into a computer, and we are not even assuming that it's anywhere close to the semi-classical description that Hawking had. Suppose string theory does something very messy in this region. We won't even ask what it is. All we assume is the dynamics here is unitary. We'll also assume that far from the hole, physics is normal. That is, once you go past some distance, 100 m or whatever you like, all the physics here is the nice normal local physics you can read off from some standard string theory text. So no big non-local effects. And now suppose you assume now that out of these complicated degrees of freedom, there is some way to extract a semi-classical dynamics, which is described by, let's say, a scalar field phi satisfying box phi equal to 0. We are not even going to specify what this map is, but there is some map in which it sort of looks like a semi-classical approximation. So in that approximation, now you have no choice, but you will get the creation of entangled pairs as the slices stretch. But we'll be very generous with our assumptions. We'll first ask that this effective field description. I've always put the effective descriptions in red and the exact things in black. We'll always ask the effective field description. It only has to work for low energy modes, say wavelength longer than 1 Fermi, where we understand the physics, nothing near the Planck scale. We're not even saying anything about that. And this effective dynamics also doesn't have to be 100% accurate. It only has to work up to some correction. And we won't even ask this map works for all times. It just works over a space-time region around here, which can produce, let's say, a few pairs. If I don't even have that, then of course, there's no sense in saying I have a semi-classical description there. But after you produce a few pairs, you may need a new map to get to make a semi-classical approximation. So you might think that we have put in all the possible assumptions. And with that, now in the exact theory, suppose you put into a computer, there's some radiation, some mess is going out. And the semi-classical, there is some kind of an approximation. So I have both these things. And then the exact thing goes to infinity. And here, as we said, everything is normal. It becomes some gravitons. And this also becomes some gravitons because at infinity, we have assumed everything is just given by normal low energy string theory. But because this was an approximate map, these will agree, but they can have an order epsilon disagreement. So that's, we have allowed that. Okay, so with all that, which might seem like a reasonable description of the exact theory and then some semi-classical approximation, the entanglement graph in the exact theory will not come down. Okay, so that's the point. In the approximate semi-classical theory, of course, going up. That was Hawking's original calculation. But with the assumptions we have made here, in the exact theory, which let's say string theory fed into a computer, the entanglement will actually keep rising. And that's the power of the small corrections theorem. So it leads us with two very sharply different possibilities. If we just take the fuzzball paradigm, then the whole thing is like a piece of coal and just radiate from its surface like a piece of coal. There's no semi-classical approximation for Hawking pairs to look for, and you're done. Okay. And so that's it. But then the difficult part, of course, to show that you can actually support structure at the horizon, which is what all these fuzzball constructions do. But suppose you actually want to keep a semi-classical approximation in some sense to emerge with all these limitations we put. Very simple, for a few pairs, you want to get a semi-classical approximation, then there must be something non-local going on between here and here. You can need a non-local identification of bits or non-local Hamiltonian terms or so on. Something has to be done because otherwise it won't work out. It's not just entanglement, you need some change to the exact theory. And I think that's just very important to understand. This is the last slide I have, so let me just put it up here. I think, so again, with the fuzzball paradigm, I think that's the right way to go. To me, it looks like the right way forwards. There are many, many exciting things to do. And really this picture that the black hole actual states really don't have a smooth horizon. They are these interesting structures we find in string theory. You can't make them without string theory. All that we have learned from all the contributions of string theory that all people have put in the last 30 years goes into constructing these guys. And in particular, lots of inputs from Juan's work in the mid-90s and later. So we now understand the string states. Every time you try to take them and see what they actually make at strong coupling, they seem to make something like this. And that seems to be the end of the information question, at least as far as I can see. And with this, there are very many exciting things to do. I mean, you get good agreements of emission rates. You can get an understanding of scrambling, energy gaps, 3-point functions, 4-point functions, some recent work on observational signatures. So many people are doing very many interesting things with these. My own interest has been in trying to see what all this might apply for cosmology. There seem to be some interesting things you can say about possible sources of energy for inflation and dark energy and so on. On the other hand, when I look at the wormhole paradigm, I find that I find all those things very interesting. So I've been reading all those papers with great interest over the last couple of years. But in each case, I find that every time one puts in this approximation, one ends up with some problem with the exact theory, which now for me would be string theory, which is something I'm not comfortable in reconciling myself to. Each of those approaches ends up in one of these problems. I mean, the simplest is that you may either end up with remnants in baby universe and the page curve doesn't come down. Okay. Or if you want to bring it down, the need to have non-locality of Hamiltonian interactions. And again, I'm talking about the exact theory. The full exact theory will need interactions, non-local interactions all the way across to distance n cube. Or some of those papers have non-unitarity of evolution in the black hole interior in the exact theory. And again, that may not be manifest. So each time I've looked at one of these things, I get stuck a little bit with this because I'm not comfortable with the assumption that the full exact string theory will actually have these kinds of behaviors. So a little bit more details of how I ran into these troubles.
Samir, maybe it would be good to conclude so to move to the discussion. We are a bit over time.
Yeah, thank you. So some of these were in my talk on this forum called Quantum Gravity and all that. But again, people can also talk to me in person, and I'd be very happy to see if there's any way of getting out of this. Okay, so that's essentially all I wanted to say. The fuzzball paradigm to me seems to be the right way forward. It has the inputs of everything we have learned from string theory and giving us very many exciting things to do. While if we try to make semi-classical approximations for the Hawking radiation, we seem to get into trouble. On the other hand, there are probably very good ways of using the black hole interior if you focus on the dynamics of infalling modes with energy much bigger than the temperature. That's what we call fuzzball complementarity. And it's a story which I've been thinking about for the last several years, and I'm happy to talk to people about that. But again, it's important to notice that these modes, E much bigger than T, have nothing to do with the information paradox, which only involves E of the order of T. So for the information paradox, I think we shouldn't be looking for these anything to do with the pair creation modes or the standard black hole interior. I think for the modes which are relevant to the information paradox, this is the only picture. And I think there's a large amount of evidence that seems to support this picture. So that's what I would tend to believe in. Okay, thank you.
Thank you very much. Thanks, Samir. Let's thank Samir and Juan. Let's thank both for a very nice introduction. Let me just suggest two things. So one is raise your hand. We will call you. And of course, if Juan or Samir think there is a particular person that would fit nicely at a given point, just override me and call that person. And if what you are then going to discuss is related to what is being discussed, wave so that we keep stay within the same subject. The second thing I want to remind is that there are two other discussions. One is called the black hole information paradox, and another one is on averages. So if you have questions that are not clearly related to those two sessions, then it's perfect to start here. If you are not sure, you can ask here. But the questions that are clearly not about those other sessions, let them go first. So if you think your question is better for one of those other two, please hold for a few minutes at least, so that we make sure we have time for the other ones on black hole microstates. Okay, so I open the floor now, and maybe we can start. Having said that, with I don't know, Eva. Say.
Okay, you can tell me if this is on topic or not. I think it is. So I want to ask about this notion that the two problems are connected, the singularity problem and the problem of the bag of gold that Juan mentioned, in a context where we have some understanding of what's going on as we approach the singularity. So let's suppose we think about a system that starts out with a single universe, and we ask, does it evolve dynamically to one with multiple universes? And if so, what's the dynamics for that? Because you mentioned that as a scenario for what's going on. So if we look at, let's say, non-supersymmetric BTZ black holes in the regime of parameters where, as you approach the singularity, there's a circle inside that has anti-periodic boundary conditions, and it shrinks slowly. Then we know that the dynamics associated with the singularity is the condensation of winding strings there. As you approach the singularity, those winding strings may condense in a spatially dependent manner, meaning the condensation sets in, in a inhomogeneous way. So at that level, there would be, in some sense, baby universes forming dynamically, but the whole thing is approaching the singularity. So I'm not sure if that could explain this picture that there are multiple universes that dynamically are, that evolve from a system with a single component. So either in that system or in any other you would like to discuss, is there a particular prediction of this scenario for dynamics that leads in real time to topology change? And would that make a prediction in particular for these winding string condensation dynamics?
I personally don't know the answer to the question, but I think it's an interesting question. How the two ideas are related.
Yasunari, yeah, please.
Yeah. Hi. Yeah, because precisely about that point, if you form effective description of the interior for, say, very high energy mode and hard mode, like what Samir was saying, from the degrees of freedom of the black hole, which is e to the a, or its tiny portion of it, then that's a finite dimensional system. So it's obviously cannot be used to evolve, time evolve infinitely towards the future. So in that sense, the theory has to break down. So you should have a singularity. It's in that sense, is that kind of, it has to be connected to the finite number of degrees of freedom and the singularity, at least in that sense.
Daniel?
Yes, I'd just like to respond a little bit to Samir's presentation. So Samir, I agreed with almost everything that you said, except for the part where you said that massive non-locality on the scale of m cubed is radical or unacceptable. And so I would of course, I would have agreed with that, had I been around, 30, 40 years ago. But we already know that that's a true feature of ADS-CFT, right? We already know that the space-time in ADS-CFT is emergent. And so that degrees of freedom, for example, things like commutativity of radial separation in the bulk is only an approximate notion. It only holds in certain states and only to some approximation. In general, it can be violated at order 1. And so I think once we, in ADS-CFT, right, it's certainly our best understood theory of quantum gravity. And I would say that it comes down strongly on the side of radical non-locality at the scale of distances that are of order m cubed. So I agree with you that if we view that as unacceptable, then we're going to we have the problem that you're saying. But I think that, everything we've learned, in the last 10, 15 years about the emergence of space-time, quantum error correction, entanglement, and so on, is kind of exactly giving us a language for talking about massive non-locality and the emergence of space-time. And we now have also this new tool of using these Euclidean replica methods, which somehow seem to fit together very nicely with this idea of the emergence of space-time from entanglement. So I would suggest that maybe we should view that that option maybe as the right one.
Can I just comment on that though? I think I'm glad you brought that issue up, because I think that is maybe at the core of a lot of thinking about this wormhole paradigm. But I think there may be a mistake at the following step. So if you look at ADS-CFT, everything that we see from there is actually because of Hamiltonian interactions. Like if you take the CFT, every point in the CFT is interacting with its neighbors. That's what generates the entanglement. And if you look at it from the bulk point of view, then the gravity at one point is interacting with the gravity at the other point. So everything is actually happening with Hamiltonians, and ADS-CFT is completely right. I think what I'm not comfortable with is the following. I take 100 D branes here. I make a little black hole of size 1 meter. I take 100 D branes a million miles away, make a little black hole of a size 100 meters. Take a very simple black hole like the 2-charge extremal. We actually know all the states. We've constructed them. But we can entangle these two D branes, right? These 100 D branes can be entangled heavily with those. All I see is that when we make all the corresponding gravity states in the first 1 meter pit, and all the gravity states in the second 1 meter pit, which is a million miles away, I simply get two balls of gravity entangled with each other, but no physical connection, no non-locality.
Yeah, but somehow if we entangle them in just the right way, then they'd be, all the observables, and we're learning more every day, for example, like in Ying's talk yesterday, behave exactly as if that connection were really there. And moreover, if you think about, as I said, I think it's important to realize that this issue comes up already in the ADS vacuum. You don't need to hide things behind horizons. You just ask, how do you think about local bulk physics in the vicinity of the vacuum in ADS? How is that consistent with the fact that everything is really described by a boundary CFT, right? And it's something, I think it's just true that the radial direction is not an exact property of the dual CFT. It's not something that's true in all states, even approximately. It's something that's only true in certain situations. And the mathematics of that, it just is sort of very compelling. Exactly the same mathematics tells you that if you entangle your two set of D3 branes that are a million miles away, there will indeed be a connection between them, right? I don't think this is just philosophy by now, by now there are many calculations that all point towards the self-consistency of this picture. There are toy models where you can solve things exactly of various kinds, tensor networks, the SYK model, etc. Right? So it's not like we're just waving our hands and saying massive non-locality and then giving up, right? We have the mathematics, a lot of the mathematics of that. We don't have all of it, right? But I would say we understand it much better now than we did, 10 years ago.
But Daniel, I have read a lot of those papers, and let me disagree for the following reason. When you see something in ADS, I see everything actually working because there's a Hamiltonian connection. When things are far apart, I think the mistake that is being made is that Hamiltonians lead to entanglement. That is obviously true.
I'm not sure. In gravity, the Hamiltonian is a boundary term, right? In gravity, the Hamiltonian is a boundary term, Samir. So I don't understand what you're saying.
So Hamiltonian, actually, the on-shell value of the Hamiltonian is given by the boundary. The actual evolution is not given by the value of the Hamiltonian, but by its variations, and that's not a boundary term.
No, but so it's not even about the Hamiltonian, Samir. The degrees of freedom in the middle of the space are not independent from the degrees of freedom at the boundary. That's the statement of holography, right? It sounds crazy, but we've learned how it works in large part. So I don't want to monopolize this. Maybe
Suva. Maybe let me just jump in. I'm not. I think it's okay if I jump in, because since I'm clearly not an expert, maybe I can say it and be corrected. But my feeling is that this would fit maybe better in discussing more information related the things like in the black hole information session. And,
sure, sorry, I was just trying.
I think to discuss really microstates and so on. Maybe there are other aspects that could be covered, but I don't know.
Yeah, Leo.
Yeah, my question is, yes, sorry. Yeah. My question is rather broad. And it's related to this work that we have just discussed in ADS-5 and in higher dimensional ADS. Now we have this very precise counting of entropy. But I guess I'm just trying to see if this is a message I should take. But that's not the entropy that will be related to the black hole. There's some other computation in n = 4 that one should do to get to that entropy. Is that the correct statement of your talk or your presentation today?
Well, the question, so you computed the entropy when you did the field theory side by going to weak coupling and computing this index and so on. So that's a computation at weak coupling. The black hole is a solution that exists and is described by gravity when the coupling is strong. And the question is, how do we see those microstates in that gravity picture? Or that's part of the question. Yeah, so if you assume the duality and you assume the weakly coupled Yammel's description, then and the index proper, the fact that the number doesn't change, you definitely get that. And well, the computations you did in the bulk by counting the zero modes and the determinants and so on, that's a computation directly done at strong coupling that is computing the number of states. But it only tells us about the states in a statistical way. That doesn't give us an explicit presentation of the microstates. In the first slide, I put this slide that says that the central dogma, so dogma means an assumption, it's something that we think is true, but we have not derived it, and we have not derived it from the gravity point of view directly. Starting from gravity and seeing the microstates is something that hasn't been done. I mean, of course, through the techniques of string theory and supersymmetry, we have many approaches, and we know a lot. But a very direct gravity understanding of the microstates, I think, would be wonderful.
Thanks.
So, sorry if I can just jump in because it's connected to what Juan said, but then you can bump me down the list of people to speak just for a moment, which is, I've been hearing this controversy like we all have for now over a decade. And I want to ask both of you, Samir and Juan, the following. There's a sense in which the fuzzball proposal is obviously true. And it is the following. If I can use ADS-CFT, let's take a state which has enough energy and, if you like, charge, and view it, say, in the conformal field theory. Now, there are many such microstates with this energy and charge. And therefore, if you believe ADS-CFT, there should be many such states on the gravity side. Well, most of those states are not going to correspond to smooth geometries. And whether you call them fuzzball or not, therefore, they will have gravity duals which are highly curved objects. So in this sense, isn't it obviously clear that, if you try to correspond microstates with microstates, you're going to have for, every microstate in the boundary theory, some kind of a fuzzball or highly curved state in the bulk. Given that that's true, then isn't the question, as Juan was saying, why is it that a black hole, which is a smooth geometry, often is a good approximation, or in what sense does it emerge as a good approximation? I mean, is that a way to think about the question, or am I just thinking about it wrong? Sorry.
Well, exactly what each microstate looks like, well, that's part of the question. What does a typical microstate look like? And I think we don't have an answer to this question. So there are some ideas.
Sorry. Will it even be a classical geometry? I mean,
well, I think there is some argument. Let me try just to make an argument that it will be some kind of classical geometry. So this is an argument based on tensor networks. That the idea is that there are some qualitative similarities between tensor networks and space-time. So let me assume that these similarities are exact, and we can think of, so then if you have a very complex state, typical microstate will be a very complex state. So it might be represented by perhaps a very long tensor network. And that length of the tensor network implies that the interior would be very long. And so it will be perhaps a smooth geometry with a long interior, perhaps filled with very different kinds of particles. So that might be one picture. But we don't know. It might be a singular space, as you were saying. So we don't know the answer to what the typical microstate is.
Can I also respond to Sandeep's question? Yeah. So I think there are two mistakes that many people might have been making in the past when they were first looking at black holes in string theory. And so both those points actually go towards your question. The first is that the black hole information paradox is actually the following question. If your quantum gravity theory has just some structure at the Planck scale, how do you actually keep some structure at the horizon? So that's the actual paradox. The no-hair theorems keep telling you that the structure will all fall into the horizon. Just saying that you have some massive jiggling at the Planck scale doesn't support anything. So not actually realizing that structure won't stay there. People just have something in the back of their mind. I'll have some complicated mess, it will stay there, so I'm okay. The information paradox really is that if you have structure only at the Planck scale, no matter what structure that is, it's actually all going to fall in. So the paradox is to show how do you get around that? And what we actually find in string theory is that there are these structures which are not just something happening at the Planck scale, but when you have a large number of quanta n, the physics, instead of being at the Planck scale, jumps to something like n times the Planck scale, and you get these extended structures. Now, if you don't use every facet of string theory exactly correctly, like even if you make a mistake of a factor of 2 in the string coupling and its connection to the Newton's constant, the fuzzball just collapses or becomes singular or gets a closed time-like curve. So really all of string theory goes into that, and that's what is the resolution of the puzzle. But the other half of the problem is that then people also started wondering whether out of all this mess, locally we could have effective degrees of freedom that would behave like local semi-classical physics. And then the small correction theorem comes and tells you, no, you shouldn't be looking for that. That's not possible. So in fact, both these mistakes, I think, were being made. First, people were thinking, okay, it's easy to get that kind of blob, and all we have to see is how does it give you a semi-classical approximation? Actually, neither of those is true. Supporting that blob is the problem, and then that blob doesn't have the local semi-classical approximation that one intuitively was thinking about. So you can still get local semi-classical physics possibly extracted for this E much bigger than T in for what I was calling fuzzball complementarity. But I don't know if that is true. It's just something we can make a bit model for. It's something which is possible, but I don't know if that is true. But for the information paradox, it's, I think, the opposite of what you said. The whole difficulty is in showing how does the structure support itself. And as we were just learning from the kind of thing that Juan has been doing recently, there can be other solutions. The CFT stops describing in Juan's picture the interior of the black hole once too much stuff falls in, and on the CFT only captures a part of the ADS, and the deep interior of the black hole is actually captured by something far outside. So you could have other solutions. So ADS CFT itself doesn't give you a unique solution, but the fuzzball paradigm itself, in the sense of your question, is the most conservative answer. That every CFT state in the boundary is a mess in the bulk, or a fuzzball in the bulk. It doesn't have to be an even near classical, it can be very messy, but how the structure supports itself is the question. And the way it supports itself is because the compact dimensions are no longer trivially tensored with the non-compact dimensions. So those structures are not obvious if you they don't exist if you don't have string theory. And some of the old work of Juan with this Lewin Maldacena mouse paper goes back to showing how you get some of those structures. So it's all very much coming from string theory. And without that, one hasn't actually addressed the information puzzle.
Subrat?
Yeah, sorry. I just wanted to say a couple of things. First, I wanted to agree completely with Daniel Harlow that I think this issue of what you're calling non-locality is actually the fact that the Hilbert space doesn't factorize, and it's something we do learn from ADS-CFT. But I think, as we have shown in several papers over the past few years, it also follows just from an analysis of the constraints of gravity. So that's just a robust analysis which doesn't require any exotic assumptions. And I don't think there's been any mistake that's been found in that. One may not like it, but I think it's an aspect of gravity. But turning perhaps more to the issue of microstates, I think the real question is that one needs to address is, if one looks at correlators of the metric or of 2-point functions of the metric near the horizon, are these correlators the same as what one would get from a semi-classical geometry in a typical state, or if they're not? And if the fuzzball proposal is that these correlators are somehow different, in a typical state than a semi-classical geometry, then I think that just contradicts several principles of statistical mechanics, as we showed in this paper with Pushkar. The input that goes into that is that using the Euclidean theory, you can compute fluctuations about the semi-classical geometry. And so you can't really have a basis of solutions in which these values of correlators are very different from the mean value. So I think that's something which suggests that one will never be able to push this program through to get a large set of solutions which differ widely from the black hole and still represent all basis states or a substantial fraction of basis states.
So is that a question for me? Maybe I can just make a comment.
Maybe we can let other people speak because we.
Please, yeah.
Let's say, Andy, do you want to make a comment?
Yeah, I want to make a quick comment on what Sendip said and then ask a question. So I don't think there's an obvious sense in which any context in which there's obvious sense that the fuzzball is right, because the entropy formula says that there's one degree of freedom per Planck area. And, so there has to be structure on the Planck area. And I don't understand why we would expect where there's structure on the Planck scale where quantum fluctuations become strongly coupled, we should hope that it would be described classically. And indeed, that would seem kind of a bad thing, because it seems to me that if it were described classically, that a black hole would be like a classical computer. And it seems much more likely that a black hole is a quantum computer, because it has to do so many magic things, scrambling, and all the basic things that black holes do. So I don't see that I mean, it could be right, but I don't see why we should expect it. The expectation would be that we need the full quantum space of possibilities to describe a black hole.
Andy, I wasn't saying it has to be classical, but I hear you. I was.
But if it's not classical, it's not a fuzz. I mean, quantum. I think the fuzzball proposal is that it's classical. Maybe I've understood.
No, so that's not the proposal. No, absolutely not. Those solutions don't have to be classical.
But then you don't have any equations. We don't have quantum equations.
Well, you do, right? What you've done is you've actually captured all the possible limitations, sometimes limits, like even you put some of these states of the D1, D5P structure that you had made at weak coupling. Some of them have, let's say, one string sitting inside a cap. We can find the dual to that, that's the string, using the PPV approximation. And then you find if you put a condensate of strings, it again turns back to something classical. So you have quantum wave functions.
You can't solve quantum gravity at the Planck scale and write down solutions. At least that doesn't seem.
So
that isn't what I've seen in your papers. I've seen classical equations that you solve.
No, absolutely. All the limits are when you put, what happens is in the CFT, if you put many quanta per mode in the CFT side, the solution becomes close to classical. So what we do is it's like a black body radiation. If you have one photon in a box, you can solve it. If you have many photons in the same mode, you get classical electromagnetic waves. You can write a laser beam kind of thing by classical electromagnetism. We do both these limits. When you have something like a generic state of the black body, it is of course messy, but having captured the two limits, then you ask in the middle, if both of those didn't have a horizon, then you say in the middle, you shouldn't have a horizon. But if suppose somebody said, no, the ones which are more messy do have a smooth horizon, then the small correction theorem tells you must have some non-locality, which is fine. If you still want that, you can have that. But because you've captured all the limits, I don't think there can be any solutions really, in my belief, which do have a smooth horizon. So the game is whether you can actually have a horizon or not. And having captured all these limits, I think there's no room left.
Okay, let me. Yeah, that could be. Let me ask my question. It's from a comment of Juan's, but Samir maybe also. So you made the statement that we might try to find the microstates in the interior of the black hole. And does that mean that they're not in the exterior? And also, I got the impression with all the recent work on the wormholes and so on, that actually the drift of things was that there was much more happening far outside the black hole than we thought. The old picture that was in my mind, which has been modified by this replica stuff, is that black hole entropy in any kind of strongly coupled picture was some kind of state squeezed up near the right. I didn't really know. but now it looks like things are going out to M or 2M or whatever. So how are you reconciling this? Is it in the interior and the exterior, or just in the interior? Or
well, they might be different dual pictures, but the reason I made this remark is because there is a concrete formula, which is the Ryuta-Kanagi formula, which tells us that when we have black holes in certain pure states, like a black hole produced by collapse and so on, or even near pure states, the entropy of these black holes, the von Neumann entropy, is computed by looking at the interior and what's going on in the interior. So in the past, we paid attention to the entropy formulas, let's say the Bekenstein formula, to formulate our ideas of black holes. So now, whatever idea we have about black holes, it should take into account these new entropy formulas. So if we are going to say that black holes stop at the horizon and we have some fastball, then we miss the possibility of explaining why a black hole that forms from collapse will have low entropy, for example. We will not have a formula that can compute it. At least that formula ceases to be valid. And so I think our thinking of my opinion is that we're thinking about black holes should incorporate the latest black hole entropy formulas we have at our disposal. And it is the same formulas that tell us that sometimes some black hole interiors, when they're entangled with radiation, they should be thought of as part of radiation. It's exactly the same formula.
There's a question by Mark van Hamston.
Oh, yeah, actually it was kind of a variation on Andy's question that he just asked, but maybe I'll put it to Samir. So it was, again, basically trying to understand what is the role of solutions that, so as Juan mentioned, it seems like there may be possibly many pure state solutions that have smooth geometry behind horizons, this bag of gold kind of space-times. And I'm wondering, suppose, I don't know that we've established that there are a lot of these, but it seems possible that there could be many of these solutions, these kind of pure state solutions with horizons. And I'm wondering, how does that fit in with the fuzzball paradigm? It seems like, I think for me, that was something surprising after all the fuzzball discussions.
Yeah, maybe I could comment on that. No, that's an excellent question, because I do think a lot about the bag of golds problem. And it's a very serious problem, because if you can just make a bag of gold initial slice, no matter what its evolution, you might then say, that you have that many states, and that's more than the Bekenstein entropy. So in fact, if you look at my recent papers on the Vector hypothesis, actually, I try to address exactly how that works out in the context of fuzzballs. So let me just give you a very rough, like one-line kind of answer, which is not 100% accurate in this form. The idea is that there are so many of these actual fuzzball states, which are all coming because the compact dimensions can be, can twist around the non-compact ones in non-trivially tensor ways, because you have all these other solutions available. When you look at the space of all these solutions, the simple bag of gold solution where you just take the slice to be thin, smooth and long, but the compact dimensions are still trivially tensored, that solution is completely destabilized. It's not a good eigenstate. If you try to make that slice, it's not an eigenstate. Localizing on the entire superspace of states, space of all 3 geometries or 10 geometries to 9 geometries to that form, actually gives you a state of high energy. So if you actually try to make the bag of gold slice, because of the other solutions available, the solution is actually not a solution which is close to being on shell. So if you actually look at, the presence of all these other solutions don't allow you to actually make a state which stays inside the horizon as something which is close to on shell eigenstate. And that's very important, because if you could make that state, if you could make even one state which is stable at least for order a few crossing times, and or maybe longer than the crossing time, and which has a smooth horizon, you could then use it to create entangled pairs, and you would be back in the information paradox. So it's very important that these kind of smooth horizon things are destabilized by the large number of fuzzball states. So the exponentially large Bekenstein entropy of the states, that comes in as being crucial. And then you find that the large entropy of these states give you a measure in the phase space, which is comparable to the classical action. So the whole thing actually cannot be close to a classical solution. What looks like a smooth solution is not a smooth solution, and that's how the puzzle gets resolved. I don't know if that rough thing helps, but we can talk about it offline.
Yeah, I'm not sure I understand what when you say that the thing is destabilized by the fuzzball solutions.
So the energy,
what does that mean?
It means that if you try to find the energy of the actual quantum state, which is localized with having a trivially tensored, it has no spread in the fuzzball direction. So I mean, you're just trying to focus on configurations which are narrowly confined to the compact dimensions being trivially tensored. In the whole space of all possible gravity solutions, you localize your wave packet to something quite narrow. But it does want to spread out over there just to minimize its own energy. And the moment you realize that you are squeezing it in those directions, the amount of energy you are having to put in to squeeze yourself away from those directions, fuzzball directions that you don't want to go, makes the mass of the solution more than ever.
Let me have a suggestion, sorry, that like we did in the previous discussion, I think we should start in 20 minutes sharp. So let's thank Samir and Juan, but we can continue informally for a few more minutes still. But let's thank Samir and Juan and say that officially the discussion is over. Of course, there is Slack, so do use Slack. But if we have more questions, I think if people stay a bit longer, we can continue discussing a little bit. For example, I had a question for I think it should be probably for the speakers of the previous two talks. So maybe I can start this more informal asking them. So you explained these beautiful developments about the index. What is known about the states that describe this 1/16 geometry? Is there a description of these are the states that that describe these black holes? Maybe it is in the end related to all these fuzzballs or something, but do we know examples of families of such 1/16 big heavy operators in n=4?
To me?
Anyone that has anything to say about it. Yeah. Tony. I think you are muted.
Maybe I can make a quick comment on that, since Samir kind of mentioned my paper with Jiming back in 2013, where we made a conjecture, but we believe our conjecture was wrong because it contradicts the expected now understood asymptotic large and large charge, but we still don't know at when it breaks down, or whether it could hold at some finite end. So, and so I said, you know, at the time we're precisely trying to answer this question of trying to see what these 160 BPS states that could be responsible for the black hole entropy look like, just in terms of elementary fields in n=4 nodes. And the only thing we could come up with, otherwise it looks like multi-gravitons. And we believe that they're not all, but actually I have still not much clue as to what the missing states are.
Yeah, I'm not asking to have a finite fraction of them, but it would be nice to have one or two that we could look at.
It's actually something that it's so hard to construct one example.
Yeah, Samir, go ahead.
Yeah, I just wanted to make a comment on what she said. Maybe you should remind people what the conjecture. So I had some comments on this, but I didn't have time. If I can take 30 seconds, it's easier with my slides.
Right.
So I just want to tell Shi that there is some progress on this, on the question that you asked, namely, when does it break down? So let me. So this is precisely the question that Pedro asked. So let me just remind people what was the conjecture. So sort of ADS-CFT 101 says that when n is equal to infinity, the single trace operators, let's only talk about BPS operators. The single trace operators are in one-to-one correspondence with the single gravitons. The next statement is that the next statement is that multi-trace operators should be multi-gravitons. So which should follow from the statement, but there, of course, there's a subtlety of how n is scaled. And if you, again, keep n strictly at infinity, then this is true. Otherwise, one has to make sense of this statement. Okay, how much are you putting operators together? Okay, so this was done in this nice paper of Chang and Yin. And then they also had numerical work based on which they conjectured that essentially that this statement is also true at finite n. Okay, she, please correct me if I'm not paraphrasing correctly. Now we know that that is clearly wrong because so here's the entropy of gravitons, here's the entropy of black holes. Okay, so the graviton entropy does not scale with rank at all, while here you have an n square growth. Okay, so what is happening? So this is my paper last May. So this last line is the index entropy of multigravitons. It's the index of multigravitons. These are the index that I showed you in the talk. This is U2, U3, U4, etc. And what you see is that the index of the gauge theory agrees precisely with the index of gravitons only, but until some point, and that point is precisely 2 times the rank plus 1. Okay, so when charge is equal to 2 times the rank, until then it agrees exactly, and then it starts to deviate. Okay, and that happens for U2, U3, etc. So this is an observation, but this observation can be proved. It can be proved precisely. So I do this in this paper, and this you do this using the following idea. So this is the answer to one of your questions. So you do this.
Sorry, can I just say that I think the numbers coming here are the indices, right? I mean, I don't think this. You're still talking about the index.
Yes,
but I was talking about the actual counting of your state. I don't think this I don't think this necessarily. I actually studied the numbers in your paper recently. I don't think it indicates our conjecture breaks down at a specific value of n, at least not in the case I was plotting in this table, because it's actually because the numbers you're comparing here is the index and not the.
Okay, so then it has to be. Let me say this. It gives you a bound for it. It has to be so because the index is the lower bound on the number of operators. So already, so it has to break down here or less than that. That much is clear. If you're asking,
what's the n scaling where things start to deviate?
This is precisely what I'm saying. So this is so when the charge is equal to 2 times. It's not for the index. You can make a precise statement. It's 2 times the rank plus 1. So it's 2 times m plus 1. So it's expected that at scaling of order n, this thing should deviate because of the Cayley-Hamilton theorem. There are new constraints or something, and in the index you can see that precisely. Therefore, for the number of states, it has to happen at least starting from here. Right?
It sounds like it has a little bit the flavor. Sorry. It sounds like it has a little bit the flavor of accounting that Jan de Boer did for the symmetric product in ADS3 cross S3, where he could match the elliptic genus to a spectrum of BPS spectrum of multigraviton states up to a certain point, which there I think was some fraction of n, n1, n5, and then above that there was a deviation between the elliptic genus and the supergravity multigraviton spectrum.
Right. So,
but Samir, this is not this table doesn't show that the conjecture breaks down within the numbers you have shown here, because it would only show that if the exact index exceeds the actual number of the BPS cohomology we constructed, which is not equal to the speed graviton, because there's cancellation. In fact, I've checked this. I think you have to go to much higher charge.
Now I understand. Okay, so now I understand what you're saying. Okay, so maybe
I have to go to much higher charge. I mean, we know it has to break a certain large n, but I have not been able to find evidence that it breaks, let's say, for n equals 2 or n equals 3 at any value of charge.
Okay.
I mean, I would love to know where it breaks down, but I don't think this table shows that.
Wonderful. I agree with you. So maybe I paraphrase. Maybe I just repeat what you're saying to make sure that I understand and it's clear to everybody as well. So here we're calculating the index of gauge theory, comparing the index of gauge theory with index of gravitons. And you're saying, well, you want to do you wanted to do at the time a more refined thing, which is numbers on both sides. So here what I showed is that the index starts to differ over here. And you're saying, well, that doesn't tell you where exactly the numbers start to differ. Did I get that right?
Right. Because we
Okay,
actually
wonderful.
did exactly.
So this, I think we can.
Yeah. I mean, if it breaks, we will actually be able to literally see in the computer code, what is the state. We'll be able to write it down explicitly.
That's right. And I think now we can do that. But in fact, what I'm suggesting is something even simpler, which I'm trying out with a student, which is that you can play the same game, what you're suggesting, with the index itself. So we can just try to write out all operators that make up these 11 and 6 and 9 states and ask which are the ones which differ with the graviton. And the reason is that those operators, and this is trying to address Pedro's original question, those operators we know because of this, because of the index calculations, they do sort of interpolate between those small numbers and the exponential growth. So it's enough to, what I'm saying is that at first shot, it's actually enough to answer the question over the index itself. If we can say, what are all the operators that make up the index somewhere over here, it gives us a good, there's one sort of way to go forward and ask what makes up the black hole. So that was my suggestion. I completely agree with you that there is much more to do if you want the full cohomology. I wanted to make one more comment.
Maybe let's go to Giuseppe and then let's close it. Maybe I think otherwise no one has time to even get a coffee. We are really getting close to the next session, and we should just test the share screening as well.
I had a question for Juan. He's still around.
Yeah, I'm here.
Oh yeah, I wanted to understand what is the lesson that you get from the self-gravitating string solution? Is it giving you showing you how the averaging occurs?
Yeah, I find it interesting because it's a solution of the Euclidean theory that has a classical entropy. So it's morally similar to a black hole. I mean, the details are different. And it's further been conjectured that this might be continuously connected. We're trying to understand whether it is or it's not continuously connected to the black hole. But so I think sounds interesting. So.
The entropy is order 1 over G, 1 over G Newton, but it does not have a horizon, right?
Yeah, that's right.
How does this work? Doesn't the Gibbons-Hawking argument requires a horizon to give a classical entropy?
Yeah, so it uses the non-locality of string theory in the sense that because there is this winding mode that winds from the size of the circle, so it knows about the size of the circle. I mean, in some sense, you could say, well, this is similar to a star that is held at finite temperature. So the free energy of the star can be computed by thinking about the local temperature of the gas everywhere, and then the total free energy can be computed in that way. And then it would depend on, so you can say it's trivial because of that this winding mode is just telling you about the local contribution of the entropy of the strings or free energy of the strings to the star itself. But so I think it's the similarity is a little bit more in the mechanics of the solution, not exactly. I'm not saying it's identical. I'm just saying it's an interesting. It's an interesting solution.
Okay, thanks.
Thank you, and I think really now we should stop even the informal discussion. So thanks a lot, Juan and Samir and everyone for a fun discussion.
Thank you.
And let's check the screen sharing for the next session.
Thank you.
And continue on Slack, of course.
So Steve and Mukund, I think you can already share screen.
Okay. Steve, do you want to try or should I try? Let me try.
I'll try. Oh, okay.
Right.
Go ahead. Go ahead.
Go ahead, Steve.
All right, I'll try. Anything happening?
Yeah,
Yes.
we're seeing your screen, but not this.
Yeah.
not the top.
We are learning what journals you're. Now we see you. We learned what newspapers you read.
Yeah. Okay. Let me try again.
So it probably gives you some choices which screen you're going to share to.
Let's try this. How's that?
That looks
Yes,
better.
very good.
Okay. So I'll stop share and Mukund, you want to try?
Yeah. Thanks, Steve. Can you see that?
Yes, very well.
Yeah.
Sounds great. Back to you, Steve.
Okay. All right, so I'll put my screen up. Just,
Okay.
Very good. And then
I'll just leave that up.
Yep, that's fine.
And then Nathan, I guess since I'm timekeeper, I guess Steve gets 40 minutes and then 10 minutes for questions. Is that right?
That's right.
Yeah. Okay, great. And so, Steve, would you like to be warned 5 minutes before 40 minutes? That is at the 35-minute point, or how should we do this?
Why don't you let me know? Yeah, 5 minutes is. Why don't you let me know 10 minutes actually? Okay, 10 minutes before, like 30 minutes. That will give me time to make an adjustment.
Yeah.
Is that okay, Sandeep?
Sandeep disappeared.
Okay.
Frozen.
I think it must be his connection. My connection is still fine.
So you're hearing me still?
Yeah.
Okay.
I hope it comes back soon. Well, if he doesn't make it back, I can be the chair until you're out.
Okay. Okay. So we're going to start on time at 20 of.
Yep. Okay, so we can start Sandip Trivedi. We lost his connection, but when he comes back, he'll be the chair. But let me give a special thanks to Steve Schenker because he's acting as a fireman as well as a physicist today. He's Douglas Stanford was supposed to give the talk, and he had a daughter last week, and Steve was sorry, I'm not just in time for filling. Hi, Sandip. So I just was introducing Steve, but now I can pass it to you.
No, that's fine. That's fine. Okay, well, anyway, sorry about my internet snafu. Let's see if something happens. Step in, Nathan. And anyway, Steve, great to have you here. And please go ahead. I'll give you a warning at 35 minutes, if that's okay.
Okay.
All right. Excellent. Thank you.
Well, let me join the other speakers in thanking the organizers for doing a terrific job in organizing this conference in difficult circumstances, as we all know. I also want to applaud them for being willing to experiment with new formats to make the Zoom world we live in, at least for a while longer, work better. As far as my own presentation goes, as Nathan mentioned, I have to start with a caveat. I've needed to prepare this talk quite quickly. And so I'm sure I've made some physics and referencing mistakes. So if you see something, please email me, politely, hopefully. And I'll try to post a corrected version of my slides on the conference website. All right, so with that caveat, let's start. All of us know here that black hole horizons appear to display irreversible dissipative behavior. And we also know that this is in tension, or apparent tension, with the unitary quantum time evolution of the boundary theory in gauge gravity duality. And there's a simple example of this involving observables outside the horizon. It was actually pointed out, I think it's over 20 years ago by Juan Maldacena. And that's to study the long-time behavior of two-point functions, operators far away from the black hole. A bulk semi-classical calculation of this two-point function decays indefinitely. This is the quasi-normal mode behavior. But if you do a boundary calculation, just insert a complete set of energy eigenstates, you find a double sum with matrix elements squared of e to the I times the difference of energies. These are oscillating phases. Now, we expect that black hole energy levels are discrete. The system is a finite entropy system. We're imagining finite volume and non-degenerate because black holes are chaotic. There's no special symmetries if they're non-extremal. Then at long times, this quantity should stop decreasing. It should just be the sum of these oscillating phases. It'll oscillate in an erratic way. And if it's sufficiently chaotic, the answer should be exponentially small at the entropy. And so the question one, right, and we'll talk about here is what is the bulk explanation for this? And of course, this kind of tension is an aspect of the black hole information. Well, we're not going to be able to give a complete answer to that, but we've learned something in the recent years, and I'll try to summarize that. The first thing is that the main actors in this story are these oscillating phases. So let's use the simpler related diagnostic. It's called in the quantum chaos community the spectral form factor. You take out the matrix elements, you just have a double sum over the phases and some Boltzmann factor-like thing that tamps out the high energy part of the spectrum. And it's easy to see that you can write this as the product of two partition functions for one for each sum, analytically continued to Minkowski time. Well, one of the things that has enabled us to make progress is that to look at these very subtle phenomena is that we have simple concrete models we can look at. One such model that's played a big role is this famous SYK model. It's just an ordinary quantum mechanics of n fermions coupled together, let's say 4 at a time. And the couplings are random. They're independent, random, Gaussian distributed variables. And so this model is presented naturally, not as a given boundary system. It's a one-dimensional quantum system, just fine. The bulk will be 1 + 1 dimensional, but it's an ensemble of boundary quantum systems. And we're going to often study averages in the ensemble, which we'll denote by these angle brackets. One advantage of having such a concrete, simple system is if you don't know what's going on, you can actually do computer experiments. And this is something our field doesn't have enough of, and we've been able to do that here. So a number of groups have done this. Here's a result for the spectral form factor. It's a function of time, and this is the spectral form factor. This is a log-log plot. And what you see is you get, at early times, you have a rapid decrease. This is the quasi-normal mode behavior, or its analog. But then at late times, you have this linearly rising ramp, as we call it, that levels off into a plateau. These are very long times, exponentially long times. And this is an exponentially small signal. Now, the slope is contained in the disconnected contribution. Just if you have separate ensemble averages of late, and it vanishes at late time, like quasi-normal mode behavior will. The ramp and the plateau are in the connected part. This is an ensemble average quantity. And these things are the signatures of random matrix eigenvalue statistics. They quantify, as we'll see a little later, long and short range eigenvalue repulsion in the spectrum. These are exponentially small effects, but they're leading at long time. Whenever you have to examine exponentially small effects, it's good to arrange a situation where they are the leading effect, so you can actually make sure they're not hidden behind something else. And one important point about random matrix eigenvalue statistics is there's a very strong belief that these are quantitatively universal in quantum chaotic systems. And we think that boundary quantum systems in ADS-CFT are quantum chaotic. So this should apply to quantum chaotic systems. And so we have to try to look for a bulk explanation of this. Well, let's imagine we try to do it in SYK. We're looking for a connected contribution. You study SYK by studying these collective fields made of fermion bilinears. Here we want something that connects the two systems. Let's call them left and right. And the link to gravity is made because at low energies, low temperatures, collective field saddles in SYK are given by bulk correlators on the bulk JT gravity geometry. So the rule is you go to 1 + 1 dimensions, you find some solution of JT gravity, and you compute the correlator of some bulk fermion field in that geometry. Well, to anticipate it a little bit, here's a wormhole geometry, a space-time wormhole. Here's a correlator connecting the left and the right side. This would give the answer for a candidate saddle for a wormhole. So we can think of G and sigma, these collective fields, as proxies for bulk degrees of freedom, since they're a way of coding geometry into correlators. It turns out that this ramp region is explained by using a geometry that we call the double cone. It's basically a piece of the eternal ADS-Schwarzschild geometry. And you identify pieces of it periodically in time because you're thinking about partition functions that are traces. So you identify this with and this, the red line with the green line, the red line with the green line. And this thing, if you pull it apart, looks like has the topology of the cylinder. In JT gravity, surfaces are weighted by their Euler character. And so the weight here is either the Euler character times the ground state entropy. Cylinder has Euler character 0, so it has weight 1. That's exponentially smaller than the Euclidean black hole, which is the topology of the disk or the cigar, which has Euler character 1 and has contribution e to the s1. Two of them have contributions e to the 2s1. One important thing about this saddle point is that there's a zero mode. You can make a relative time rotation of one side with respect to the other. And so there are roughly T of these. The zero mode has that kind of volume. And that gives a linear T dependence. That explains the ramp. It turns out these are true saddles. There's a weak pressure that you can stabilize them. I won't go into this in more detail. Well, it turns out you don't have to think about SYK. You can work directly in JT gravity. So Thomas Mertens will talk about this. And it turns out JT gravity is precisely dual to another kind of ensemble of boundary Hamiltonians. You just draw the Hamiltonians from a random matrix ensemble, each is a matrix, tuned to give the leading JT gravity density of states. Because it's a random matrix ensemble, the fine-grained random matrix statistics is the same, is exact. Every random matrix potential and gives the same fine-grained energy statistics. This connection to 2D gravity is formally analogous to these old matrix models of string theory. In particular, you study the 2, p minimal string and take the p goes to infinity limits. And this will be discussed, I hope, in Thomas's talk. But here we're taking a different perspective. It's an old one, but that the string joining and splitting, these interesting Riemann surfaces we all talk about, becomes JT baby universe, one-dimensional real universes, joining and splitting. The genus expansion parameter is e to the S naught, non-perturbative in the Newton's constant. S naught goes like 1 over G Newton. The matrix is not like an n by n Yang-Mills field. It's the full second quantized boundary Hamiltonian. It would be like the Hamiltonian of super Yang-Mills. This is effectively an e to the S by e to the S dimensional matrix. It's huge. This kind of setup, where we have many baby universes, is often called a third quantized setup or universe field theory. This seems to be where we are. And there are natural extensions of this idea to supergravity and to gravity coupled to gauge theories. Well, we can interpret the spectral form factor behavior as an overlap in Hilbert space. Well, in order to study thermal things in Hilbert space, you typically double the system and form, let's say, the unnormalized thermal field double state, the form that you all know. Then you time evolve on one side of the thermal field double and you form TFDT, the time evolved thermal field double. Then it's easy to see that this partition function is the overlap of the original state with the time evolved state. And the product of these two partition functions is just the modulus squared of this matrix element. Now, time evolution here is a chaotic Hamiltonian. It begins to randomize the state in the doubled Hilbert space. That's a simple rule that for random vectors in the Hilbert space of dimension d, the overlap squared goes like 1 over d. Here, d is e to the 2s. It's a doubled Hilbert space. And so this thing is of order e to the minus 2s relative to the beginning. And that is what the spectral form factor behaves like at the beginning of the ramp. The small non-zero overlap, the minimum size of the spectral form factor, is due to the finite dimensional Hilbert space we're dealing with. So here we see that wormholes provide the bulk explanation for the small non-zero overlap, indicating the finite dimensionality of the Hilbert space. And this is a recurrent theme in recent developments. It plays a central role in the replica wormhole story, for instance. Wormholes are the way the bulk tells us about this fact that you can't fit an arbitrary number of orthogonal vectors into the Hilbert space. And it increases at late time because this time evolution is not really a Har-random unitary. And I won't elaborate on that right here. It's a side point. Well, the fact that these two left-right systems are decoupled raises a factorization puzzle. The averaged matrix element, which gives the partition function, goes to 0 at long time. The phases oscillate and there's nothing to cancel. But the squared matrix element does not. This is the wormhole contribution. Okay. So if you just imagine doing a calculation in the bulk, you'd have disk times disk. That's the decaying part. That's the slope. That's if you just squared this thing. But if you did this, you would get disk times disk plus a wormhole. And these are not the same. So the wormhole explanation of the ramp leads to a factorization puzzle if the boundary is a single quantum system, because then you'd obviously have these two things being equal. The ensemble average restores consistency because you can easily have the ensemble average of the square being different than the square of the ensemble averages. And this connection between wormholes and ensemble averaging goes back to the 80s in the work of Coleman and Giddings and Straumann. And in this context was emphasized by Maldacena and Mathur. Well, we can then return to correlation functions. I won't say much about this, but I'll try to give just a brief sketch. You study the long-time thermal two-point function, and we won't normalize it. Well, you just have one boundary here, one trace. So you need geometrically to have one boundary. Well, the short time behavior will just be given by the disk, but you'll find a ramp because you have those oscillating phases. And so that has to involve some kind of wormhole. And the natural topology is a wormhole attached to the disk, sometimes called a lid geometry. So the Euler character of this is -1. So this has weight e to the minus s times a linear ramp from some almost zero mode here. And this is in fact the behavior you expect for applying the eigenstate thermalization hypothesis for those matrix elements. But there's a nice interpretation of the fact that this thing stops decaying actually because of the formation of a wormhole. You imagine a quantum created by this operator, let's say at 0 time. As you evolve in time, it falls behind the horizon. We're all used to that. That causes the exponential decay, and we're all happy with that. But then there's a small probability that you can make a tunneling kind of process that forms a wormhole. And it has amplitude e to the minus s and a factor of t because you have lots of these wormholes. And that allows the quantum to escape, get back out to the boundary. You create a baby universe. And then this operator O of t that lives close to the boundary can act on it, making a non-zero correlate. Recently, this group has been discussing more complicated multi-point correlations, in particular OTOCs, and they've developed a very nice bulk understanding that gives insights into aspects of the unitary black hole S matrix. This is a much more subtle quantity, and they've done a sharp analysis. So I want to have you look out for this paper. Talks have been given about it, but it hasn't been put on the archive yet. Well, if random matrix behavior is universal, and this is a touchstone for us, then this kind of phenomenon should apply to higher dimensional black holes as well. Kristan Jensen will talk some about this. Perhaps there's a wormhole explanation for the spectral form factor view. Well, this group, Kotler and Jensen, have found candidate higher dimensional Euclidean wormholes that might do the job. In particular, the boundary has a thermal circle as you need for the partition functions. And in fact, from a closely related point of view, you can see that this construction of this complexified double cone from eternal ADS-Schwarzschild geometry is general. And recently it's been argued that this is stable against a standard decay mechanism that people worried about, brain nucleation in these two papers. You can do other things in higher dimensions. You can imagine you have a genus 2 boundary of your wormhole in 3D gravity. Here you have a nice stable wormhole solution that was discussed in some of these earlier papers by Maldacena and Maos. Well, here's a truly terrible cartoon of what such a wormhole would look like. There's a genus 2 surface here linked by some kind of wormhole. If you make an eigenstate thermalization-like hypothesis, for the OPEs that you'd get by factorizing this on handles, the statistical CFT prediction agrees with the weight of this bulk gravitational cell. So there's some sort of fragmentary evidence that maybe 3D gravity, which doesn't have any ultraviolet problems, is dual to an ensemble of 2D CFT. Well, if that's true, what kind of ensemble would you be looking at? Well, there's some obvious instructions for this. Quantum field theories, in particular CFTs, are much more constrained than generic quantum mechanical Hamiltonians that are basically just matrices. You need locality and all kinds of other problems. We know of a few families of 1 + 1 dimensional CFTs. So people have taken a natural family, the Noreen moduli space, and averaged it and see what you get. It turns out this is consistent in the bulk with the sum over partition functions of a bulk U1 to the nth Chern-Simons theory on different 3D geometries. You have n currents in this model, so you have to have n U1s in the bulk. And these CFTs are built from free fields. They're not chaotic. You wouldn't expect a ramp. And in fact, these people have analyzed this and you don't find a ramp. And there are other rational examples that presumably don't have ramps either. So the question is there some kind of ensemble of theories that are chaotic the large C, large gap theories that might be the things you need. Oh, there are no candidates, at least that I know about. And so this raises the question that, because this is kind of an approximate notion of averaging, is there the notion of an ensemble of approximate CFTs? This is a question that a number of people have asked about, and I think deserves more thought. Is there some kind of notion like this running around? Well, we've been talking about the ramp surface. There's this other part of the spectral form factor called the plateau, and we need to talk about that. I say that I think our gravitational understanding of this is much less satisfactory than our understanding of the ramp in terms of wormholes. But I'll tell you some of the approaches people are taking. First, let's understand it in random matrix theory. The spectral form factor in time is essentially the Fourier transform of this density-density correlator averaged in the random matrix spectrum. Here's a random matrix spectrum. If you have an eigenvalue at E, what's the probability of finding another eigenvalue in E prime? Well, it looks like this. Here's a formula. There's a disconnected piece. It's basically the density, the leading density of states in each separate factor of the spectral form factor. This, when Fourier transform, gives the slope. You have a piece down by e to the minus 2s from this that goes like 1 over e minus e prime squared. Fourier transforming that says that levels don't like to be near each other at large separation, gives the ramp. But then you see this oscillating part. And the Fourier transform of this cuts off the ramp and actually turns this thing level. If you imagine going backwards, you have kind of a sharp corner here that when you Fourier transform, it gives something oscillating. And this oscillating behavior is really the smoking gun for discreteness of the spectrum in an average quantity. This, if you look at it, this means that their levels aren't right on top of each other, and these wiggles are nearest neighbor, second nearest neighbor, and so on. Well, cosine of e to the s is like e to the I, e to the s. That's non-perturbative in the genus expansion. In fact, you might call it doubly non-perturbative because e to the s is non-perturbative already in 1 over g Newton, or in g Newton. And it turns out you can trace this. One way of thinking about it is to go back to the string theory analogy. You have these Riemann surfaces that define the genus expansion. Well, this kind of non-perturbative effect is a de-Bruijn effect in a string theory where the world sheet gravity is JT. Call it the JT string. Well, so you can analyze it using techniques developed in topological and minimal string theory to analyze brains. The way this goes is you can extract this density-density correlator from this product of resolvents by looking at discontinuities here. Then, and this is the crucial step, you can relate this resolvent to the ratio of determinants if you differentiate and set this energy equal to that energy. And so you get the density-density correlator from 4 determinants, 2 upstairs and 2 downstairs. And the crucial point is that the determinant operator basically inserts a certain kind of brane. In the minimal string, it's called an FZZT brane. And the way you see that is straightforward. You write the determinant is e to the trace log. Trace in gravity means 1 boundary. E to the trace, if you expand it out, means you have no boundaries, 1 boundary, 2 boundaries, and so on. So in fact, in evaluating this, you get many disconnected geometries, many disconnected world sheets in the string theory interpretation. This is just Polchinski's calculation of de-Bruijn effects. But here, world sheets are space-time geometries in this third quantized situation. So we have many disconnected JT space-times. Here's a picture of them. Each one of these is a little JT space-time. So it's a many universe quantum. Now, sometimes you think of universes, baby universes embedded in some mythical thing called superspace. Nothing to do with supersymmetry. So in some sense, we have a de-Bruijn in superspace, whatever that means. But you can do this calculation and find that density formula called a sine kernel formula. There's another approach to these non-perturbative effects that actually is the main approach that's used in the quantum chaos community that I want to just emphasize, because I think it's interesting to think about. It's called a nonlinear signal model formalism, and it's really goes back to work of Efetov. And one of the other beautiful things about it is it gives the best argument, I think, that I know of, why random matrix statistics are universal. It follows essentially from a symmetry kind of argument. So again, you extract rho from this ratio of 4 determinants. And then you represent the determinant here as an integral over some matter field. If you think of this Hamiltonian as having color indices, then you have matter fields that are not a matrix in color space, but a vector. Now you have several matter fields, and they're labeled, let's say, by capital A, which we'll call a flavor index. You get determinants upstairs if the matter is Grassmann's, and 1 over determinant from scalars. So the system has both Grassmann's and scalars in it, and it has, in fact, a graded flavor symmetry, because you have Grassmann's as well as scalars, a U2/2 flavor symmetry. These 2 determinants are evaluated at E, these are evaluated at E prime. So you break this nice symmetry if E is not equal to E prime. So this thing functions like a master that breaks this symmetry. Now you integrate out the color stuff. That's like integrating out gluons. You should think about this as kind of fundamental matter. And you can think about this in the bulk descriptions being created by flavor brains. So you've integrated out the color stuff and getting the dynamics on the flavor brains. You get an effective action for the meson fields in a QCD analogy that are these color singlets. And these are describe the open string dynamics on FZZT flavor brains. So the idea is a very QCD-like picture. You have quarks and glue, you integrate out the glue, you get an effective pion description of the dynamics. And just like with pions, you describe the infrared dynamics, that's E close to E prime, in terms of a nonlinear signal model with a target given by the flavor symmetry. Here it's this graded coset. The ramp is due to perturbative, I should have put quotes here, pion fluctuations around a saddle picked out by this master. The non-perturbative effects are due to another saddle. Just like in the pion Cairo-Lagrangian, you have solitons that are interpreted as baryons. Here you have another saddle, a bit like a baryon. In this context, it's called the Andreev-Altshuler instanton. And that explains the wiggles, the non-perturbative effects. And this universality of this thing only depends on having this right symmetry breaking pattern, plus a discrete symmetry that plays a role in determining this set. Now, the role of this in high energy physics in this gravity story has been emphasized recently by Altland and Sonner in a very nice paper that presents things in an accessible way. And they have a picture here of this phenomenon. Think of this as the bosonic part of the sigma model manifold. There's the perturbative saddle point. Fluctuate around it, and you get the ramp. Fluctuate around it, and with this new saddle, you get this transition to the plateau. And then at very late times, corresponding to E almost exactly the same as E prime, symmetry is restored, and the fields cover the whole sigma model. They call this causal symmetry restoration. And I raise this because the gravitational interpretation of these ideas is still an open question, and I think that deserves more thought. Further, it turns out that you can think about the plateau without all this extravagance of extra brains. Okay. The spectral form factor is really a 2-boundary form. Does it inevitably require arbitrarily many boundaries to fully describe? Do you really need this many universe interpretation? Well, there's very interesting work of Okayama and Sakai that gets away without it. The trick is here, you work at fixed temperature, not energy. You don't focus on some energy band. And at fixed temperature, you integrate over all energy bands. And that smooths out the ripples in this density-density correlate. The spacing changes as you change band. Then you work in the time domain, and you find in the simplest case, which is topological gravity, that the spectral form factor is just given by this explicit formula involving the error function. And it gives this nice smooth curve with no sharp feature. In fact, this thing has a convergent power series in e to the minus s naught times time. E to the minus s naught is the genus counting parameter. This looks like a genus expansion. So there should be a geometrical interpretation. And a number of us are trying to puzzle out what that means. I should point out that you can write an analogous formula for JT, and Douglas Stanford has done this. So this seems like an interesting thing to pursue, and might obviate the need for this many universe set up in this context. Well, in some sense, a really important question to address is the one that we would have thought about some years ago. The standard presentation of gauge gravity duality does not correspond to an ensemble of boundary quantum systems. There's one super Yang-Mills theory. It's essentially a unique theory. And so the question is, what happens if you don't average? At present, it's too hard to examine a theory like super Yang-Mills for these very fine-grained, subtle, non-perturbative questions. So we can again look for a toy model of this non-average behavior by taking some of these simple ensemble theories like SYK or JT and look at a single member of the ensemble. Now there's a basic result. If you're in a situation, let's say, where wormholes dominate the average kind of calculations, like on the ramp, then the variance of the spectral form factor as you vary across the ensemble is of order the signal squared. There's big fluctuations. You see this by doubling the system. Here's a left-right, and here's another copy of the system, L prime, R prime. And then you fill it in with wormholes, geometries. This is just the signal squared, but there's another configuration where L is linked to R prime and L prime is linked to R. By permutation symmetry, these obviously have the same weight. Subtract off this, and you get the variance is given by this. So the variance is equal to the signal squared. This means the answer depends sensitively on the element of the ensemble. It's noisy. Okay. And this is a fundamental thing that wormholes go hand in hand with. They go hand in hand with noise. Well, here's a picture in SYK. This blue curve, again, is the ensemble average answer. And here, this red curve is a single sample of fermion couplings. And you can see that the slope is what we call self-averaging. It doesn't matter what member of the ensemble you have. But the ramp, there are these fluctuations. If you think about it, you can argue that the autocorrelation function in time is short. So you can think of different times as different members of the ensemble. And these fluctuations are an indication of this order 1 variance. Further, random matrix universality allows you to study this noise. And in fact, this noisy ramp should be generic in gauge gravity duality in quantum chaotic systems. And it's a consequence of this kind of discrete fixed spectrum. It's a erratic spectrum. It's a consequence of microstates, the kind that was discussed in the last discussion. And so we have to ask, what accounts for the noise in the bulk description? There's actually an even simpler quantity to look at. Just look at one copy of the partition function. At short times, this is given by the Euclidean black hole. This is the piece of the slope. But at late times, if you just look at the formula for a given Hamiltonian, it'll oscillate erratically around 0. And the variance will grow with time. So if you square it, you'll get this linearly rising ramp. But in a single copy of the partition function, there's no generic geometric candidate for this noise. There's an important exception. In certain special cases, a fuzzball would explain something like this. But these are special. They're mostly extremal, although not always. And so in some sense, this would be a reflection of a non-extremal set of fuzzball geometries or configurations. Again, you take the modulus squared, and you get this noisy ramp. It factorizes. This is just a square of a number. But it also contains something that looks like a wormhole signal. You can get rid of the noise, let's say, by time averages. And it looks like noise and factorization puzzles are part of the same question. And the question is, how do we get a handle on that in the ball? Well, the short answer is we don't know. But there are a couple of approaches, or more than a couple, that have been explored. And here, in my final time, I'll just mention a couple of them that have come up. One is to take seriously this many universe picture, going back to the work of Coleman and Giddings and Strominger in the 80s. This has been recast in the ADS-CFT context by the very interesting work by Murthy and Maxfield. See also this nice work in a paper called Eigenbraids. Here we'll follow this Murthy-Maxfield setup. The idea is you think of a many boundary Hilbert space, many copies of the boundary in the ball. You have a no boundary state, a state with one boundary, a state with two boundaries. These are boundaries in the sense of ADS-CFT, an ADS boundary. And then you have a partition function operator with one trace. You apply it to no boundary and you get one boundary. You apply it to one boundary, you get two boundaries. And you define the inner product in this Hilbert space from geometry. One boundary, which is no boundary, expectation value of partition function squared, a little like the spectral form factor, no boundary, is given by all the geometries that fill in having two boundaries. Well, there's two natural candidates. You can have a disk and a disk. That's two decoupled Euclidean black holes. Or you can have a wormhole. It's pretty clear that this quantity doesn't factorize. The expectation value in this state of z squared is not the same as the square of expectation value of z because of the wormhole. But then you can ask, are there states where things do factorize and you don't have this puzzle? And there are. There are eigenstates of z that are called in this game the alpha states. You figure some state out where you apply z to it and you get the number back. And you can think of this state as one element of an ensemble. That's a place where you would have factorization. Well, where does the noise come from in such a description? You can think of the alpha state as written out in this way. So it's a sum of no boundary with some funny coefficient, one boundary and some funny coefficient, two boundaries and some funny coefficient, and so on. A lot of complicated numbers. Then let's say you look at the expectation value of one z in this particular state. That's like one set of fermion couplings in SYK. And then you draw geometric pictures. Well, here is the bra state with its boundaries. This is one component of it. Here's the ket state with all these boundaries. And here is the operator, the insertion. And you draw geometries here. Well, there's one geometry that just looks like this disk. And then the state boundaries are just connected together. Now, these kinds of configurations are just determining the normalization. They give alpha inner product alpha. And so this is the thing that would give the smooth decay, the smooth early time decay. But now you have other configurations where the operator boundary connects to the state boundaries. And then the state boundaries have to rearrange themselves. And you have lots of configurations like this that will depend sensitively on these numbers. And these configurations, the ones that don't have this disk here, are the noisy contribution. And because you don't have disks here, these things are down by e to the s from this. And this is a picture where the noise would come from in this kind of many universe setup. It would be coded into this complicated state in this way. Sandeep, how am I doing for time?
I lost track. I'm doing a terrible job. You're actually out of time.
I have a few more minutes.
You have 10 minutes.
I have 10 minutes.
You have, I mean, you're done with your 35 minutes. And in my reckoning, Steve has 6 minutes more. I don't know, Nathan.
Okay, I'll just go on and cut me off.
Yeah,
I get in trouble.
There's
another.
About...
Yeah. Okay.
Yeah.
So there's another approach that my colleagues and I have been exploring recently that tries to get away from having all these many boundaries. I'm not sure we've succeeded. But again, the idea is to make something minimal. The spectral form factor in Z is really a one boundary object. Can you do something more lowbrow? Well, so we retreated to where, in some sense, we started this talk, which is SYK. But now we imagine that we fix the fermion couplings once and for all. This is the kind of thing you do in a computer experiment. Now, it turns out you can formulate a collective field description, these G's and sigmas that are fermion bilinears, even when you have fixed couplings. So again, G of TT prime is described by this correlator. It codes this geometry. Now, this is only a toy model of gravity. You don't know what the bulk is really, but the great virtue of it, its saving grace, is that we have an explicit representation for the entire quote unquote gravitational pattern. That is, we can write Z as an explicit integral over this bilinear in time, this bilocal in time, this bilocal in time, of each of the items of action that depends on these fields. If we average this action, we have a simple explicit form. Even if the couplings are fixed, this is in principle calculable. You can do it numerically, say. And even if it's complicated to compute numerically, you can study its statistics. So we know a lot about what this action for fixed couplings is. And so once we have this action in these fields, in principle, we can explore all the nooks and crannies of this gravitational pattern. This is an exact rewrite, so it has to have the noise in it. Where in this integral does the noise come from? Where is it hiding? Now, in fact, we can only do a detailed analysis of this in a toy model of this toy model, where we restrict SYK to having just one time point. Okay. Then things are just ordinary integrals, and those we can poke around in. And so we can ask, where does the noise come from? Well,
really sorry to interrupt, Steve, but if you could wrap up in about a couple of minutes, it'll give time for a few questions at least, if you don't mind.
Yes, I'll wrap up in a couple of minutes. Well, a scenario in full SYK motivated by the simple model, it's not something we can derive, but it seems plausibly motivated, is that Z is given by the disk saddle, which we all expect, and that there's another saddle point in this integration space that looks like the correlator's a wormhole geometry, except all we have is the one side, the G left-left fields, if this is the left boundary. We don't have the left-right fields that you need to make a full wormhole description. And so we call this other saddle a half wormhole. And it is the source, we think, of the noisy late time behavior. In particular, it depends sensitively on which particular set of couplings you choose, whereas this contribution doesn't. And it vanishes on average. So we think this gives that, and this gives that. And these new saddle points are there in what you thought was a one boundary integral, although it seems like it's suggesting maybe there's another phantom boundary out here. But you see it in this one boundary pattern. You can then ask about wormholes. You can study Z left, Z right. The way it works is you have the ordinary wormhole, but you have other saddles, a pair of half wormholes. And this link tells you what kind of action you have. Factorization then says that this thing must be the product of these two things. At late times, the disk goes away, so you get an equation that looks like this. Wormhole plus quote unquote linked half wormholes equals unlinked half wormholes. Here you have G left right not equals 0. Here you have G left right equals 0. And here the product of systems, there's no G left right at all. You've gone from here to here by integrating out G left right, which after all is just an auxiliary field that gives 1. So it looks like these things must be equal. They're just different ways of doing the same integral. So it looks like there's a multiplicity of both descriptions for the same number, depending on whether you put in a G left right kind of wormhole field or not. Well, let me conclude since my time is up. There are lots of questions always that these ideas raise. And let me just mention the big one that's in the back of everybody's mind. Are these ideas relevant for the standard holographic systems we're used to, like Superman? And we don't know the answer. Fortunately, we'll have time to agonize over this. There's a discussion on these and related issues on this coming Friday at 12:20 Brasilia time, which I have to remind myself is 8:20 California. And there's also other discussions. There's, if you'd like to time travel, there's one we just had. There's one also on Friday about the black hole information problem. And there are these interesting talks that will bear directly on what we're addressing, as well as many others. So with that, let me stop, and hopefully I've left a little time for specific questions. Thank you.
Well, let's thank Steve for a great talk. Thanks a lot, Steve. We'll go right into the questions. There's a hand raised. Kumrun has his hand raised. Please go ahead, Kumrun.
Okay. Hi, Kumrun.
Hi, Steve. Thanks for a very nice review. So if you take any large N dual theory, all the integrals in that theory will give you a large N dual description in terms of Riemann surfaces, the two surfaces. In that context, SYK or the Mirzakhani model, all of those can be interpreted exactly in that same way as arising from this large N duality. So for example, this ensemble of universes you were talking about in that context becomes D-branes in a Calabi-Yau threefold.
Yes.
So why should I think about the 2D as the right description of that theory, whereas I know these are just observables in a 6D theory? And is it also not the case? Doesn't this also suggest that these 2D is a very special case of dimension, that is in higher dimension, you will not have a similar statement of the ensemble, and this is very special to the large N duality and 2D?
Well, you know, you do what you can do, Kumran. We don't know what the bulk dual of super Yang-Mills is. None of us know what the rules in the bulk are. So we have to learn by taking simple models. And so we have to try to extract the lessons of these 2D models and see which ones might apply in higher dimensions.
No, Stephen, I'm not explaining myself clearly. I'm saying the model you're thinking is 2D is not 2D. That's my point.
I disagree with that. I think there's a way of interpreting.
The models that you are referring to can be described as topological strings in Calabi-Yau threefold. Whether you agree or not is not the point. You can describe those amplitudes as worksheet amplitudes in those gravity theories, in 60 theories.
Yes, I'm quite willing to accept that. Let's talk about that.
That's 60 theories. So talking about that theory as saying you have a 2D gravity is like saying worksheet theory is a 2D gravity, even if you're talking about type 2B in 10D.
Yes, but I think there's a way of thinking about string theories having 2D gravity. It's just a question of what you. Come on, let me finish. Come on, let me finish my answer. The question is what you call the Calabi-Yau in the example. See, I would call the Calabi-Yau superspace. By super, I mean the space of many universes. It's certainly, there is that space there. It's a question of what you call it. So there's certainly a description of this embedding space, as there are for these minimal strings and some kind of Liouville description. But the question is, we don't want to call it space-time. We want to call it some bigger space. We want to imagine we're little ants living on the string world sheet.
Well, you can, but clearly not the right description, Steve.
Well, that's a question, whether it's the right description.
Well, it's like saying in type 2B strings, the superspace of some worksheet strings. Does the 10D supergravity is what we know is the right language in the effective theory. You can describe it in terms of worksheet, that's fine. But that we know is not the right picture. That's all.
No, yes. I think I agree with everything that you said, Then the question is how you use it. Then the question is, suppose we don't live in two-dimensional world sheets. Suppose we live in four-dimensional, quote unquote, world volumes. What is the analog of superspace? Or do you need such an analog?
No, you won't get it. The point with that, this suggests that you're not going to get it. And that's why you're going to get difficulties on ensemble higher dimensions. That's you're exactly going the same problems you're going to face in higher dimension is the reason that 2D works on higher, you're going to have problems.
Yeah. That's why what one tries to do is what I discussed in the final part of my talk. You don't integrate over the matrices. That would be like integrating over the Yang-Mills fields. You imagine that you have fixed fields. And then you're very much like a situation in higher dimensions. How is the world sheet picture change when you don't integrate over the fields? That's like studying SYK with a fixed set of couplings, or in the work of eigenbrains, by taking one of these low-dimensional matrix string theories and don't integrate over the matrices. This is what Blumert, Mertens, and Verscheid call eigenbrains. How does that change that world sheet picture? And that would be somehow the analog of how super Yang-Mills would look. So that's precisely the goal of these kinds of analogies, is to try to draw a lesson from these simple models that we can study, but that would apply in the higher dimensional non-average.
Well, but I think that the lessons we already know from string theory suggest that there are no higher analogs. But then yeah.
Well, Comrade, I'll ask you a question. I'll take a brief.
Or we can discuss in the discussion session if we are running out of time.
Well, can you?
I was going to suggest.
Yes. Okay.
Yes. Sorry, Steve. Please do complete. But then let's move it on to one more question, and we'll have to close.
I don't think what I would say would be the most fruitful thing. Why don't we wait for some other questions? I'll make room for other questions.
Okay, there was one more hand raised. I think Pedro Vieira had his hand up. Pedro, did you?
I had my hand up, but I would prefer to postpone to the discussion, not to. I'll move it my question to the discussion session. I think it's going to be a fun session.
Okay. I actually don't see any other hand up. So Steve, maybe you can complete what you were going to say, and then we can close it. Go ahead.
I'm afraid I forgot what I wanted to say, which probably means that it's a good idea for me not to continue.
Maybe, yeah. Let me then just ask you a quick question, but feel free to postpone to discussion, which is, you said that the wormholes were in fact also related to the noise. I mean, there is this connection. And why is it that, I mean, to some extent, the wormholes represent ensemble averages, because you have multiple boundaries and multiple theories over which, and so why is it that the ensemble average is being able to calculate the noise averages? I mean,
well, it's because you can try to compute the ensemble average of the square of something. And if you compute the ensemble average of the square of something, you know something about the variance of that thing in the ensemble.
Yes.
So it's true that you can, suppose gravity just tells you how to compute ensemble averages. Well, there's a lot of things you can compute. You can compute a quantity and its square and its cube. And so you can learn all kinds of things about the distribution of the ensemble from things you can compute from averages. And so that means gravity, if you accept it can compute everything in the ensemble, should teach you, let's say, about the variance. Now, I'll just conclude with a remark. I mean, I talked about wormholes and noise going together. You might ask a question, what happens in something like the replica wormhole story, where you have wormholes that are essentially, very closely analogous to these. The point is, in the replica wormhole story, just a second, the replica wormhole story, the boundary systems are not decoupled. There must be a faster way of doing this, but you'll forgive me here. And so what that means is that you imagine that left and right are coupled somehow. That means you don't have this permutation symmetry. That means this configuration would be different than this, because there would be, let's say, some kind of coupling, because you're tracing out over the coupled Hilbert spaces. And so the observable you're talking about couples the two entangled systems. And so then one of these would have a bigger action than the other. And it turns out that the replica wormhole saddle has the right action, the more favorable action, and that means that the noise is exponentially small in S compared to the signal. So there's a special thing about these factorizing quantities that the noise and the signal are comparable. In the replica wormhole story, the noise isn't absent. It's just small by e to the s or e to the minus s. And so noise is ubiquitous. And the fact that it's small in the replica wormhole story is both a feature and a bug. It's a feature in that you're pretty sure you're doing the accurate calculations. But if your interest is in the noise, it's hard to see. And there are other quantities like the black hole S matrix where the noise will be order 1 or individual matrix elements. And so noise isn't absent, okay? It's just in certain quantities, it's not there. It's small. That was my comment.
I see. Okay. Well, thank you very much for a great talk. And let's move on to Mukund. Mukund Rangamani is our next speaker. Mukund, go ahead. I'm going to try and do a better job and remind you at 25 minutes without getting too absorbed in your talk this time around. So go for it.
Thanks, Sandeep, and thanks again to all the organizers for putting together this wonderful workshop. Steve said in trying times. So I wanted to tell you today about some work we've been doing in the context of trying to understand real-time holography, and in particular with applications to replicas and open quantum systems. So the broad goal of what I'm after is to better understand the real-time gravitational path integral and stationary phase approximation there too, which impacts a large range of questions ranging from computation of causal response functions out of time with various out of time orderings, replica observables in dynamical situations, as we just heard. And often the practical and effective strategy in any quantum system is just to do these calculations with the Euclidean path integral and then analytically continue these results. This strategy, in fact, is our sort of go-to strategy in gravity, where the Euclidean path integral has, over the last 5 decades, given us a lot of important insight into a variety of problems, ranging from black hole thermodynamics to its upgraded versions, as Juan said in the discussion, in terms of the Ryuta-Kanagi formulas and various fine-grained entropy quantities from gravity, as well as for the computation of gauge-invariant observables into their correlation functions. But from a practical standpoint, it leaves unanswered a very important question, which is what exactly happens in the real-time dynamics, what's going on as the system evolves. And you may ask this question, and over the years, we've come to appreciate that the world of contours that we might want to draw in quantum systems is rich and diverse. We can have causal response contours like the Schwinger-Keldysh contour or more general OTO contours, or we can start drawing replica contours and put operators and compute correlators in replica contours. Here, there's a single density matrix, whereas here there are multiple density matrices. And all of these are things that we can study in quantum mechanical systems. And the question really I want to ask is, suppose I give you these contours in the boundary, what do I do in an ADS-CFT context in the bulk? What geometries compute them? How and what can I compute with them? I'll primarily focus for the first part of the talk on the simpler Schwinger-Keldysh contour, and in the second part of the talk, I'll generalize a bit to the replica contour. There's interesting things to be understood with these more general contours, which I won't have anything to say about in the course of the discussion. To set up the problem, the real question is, I pick one of these contours as a boundary condition for the ADS-CFT path integral, and say, compute for me from the bulk, which geometry gives me the appropriate stationary phase approximation to the bulk gravitational effective field theory. And from there, compute real-time observables and translate them into physical statements in the low energy effective field theory. Okay? So for example, a question that I've been very interested in is basically deriving the effective field theory of systems with conserved charges. In particular, can we get derived strongly coupled plasma dynamics? So 2 themes I'll talk about today. One will involve computing thermal observables, the other will involve computing Renyi entropies in time-dependent states. So on to the first problem. So this is something I've been doing for about 1.5 years or 2, with Logarithmic and various collaborators. Some of these papers have appeared, and some will appear in due course. So let me motivate this problem from a slightly different standpoint, not just the gravity standpoint, but just from a much more fundamental standpoint in quantum systems. Imagine just having a quantum system which is coupled to an environment, and you integrate out the environment. So you sort of start having a system and an environment, and you have some coupling between them, you integrate out the environment. For the purpose of discussion, I'm going to take the environment to be holographic, and it's very much inspired by this very nice idea, which dates back to Polchinski and Faulkner, of thinking of semi-holographic systems as useful ways of deriving dynamics, effective field theories for strongly correlated systems. If you're asking real-time questions, if you're not doing Wilsonian RG in Euclidean setting, if you integrate out the environment, then what you end up with, as was emphasized a long time ago by Feynman Vernon and studied in the context of harmonic oscillators in quantum mechanics by Caldera-Leggett, you end up with a system Lagrangian, the sort of your probe readout systems Lagrangian, which is in some kind of Schwinger-Keldysh double setup where you have a set of right degrees of freedom, a set of left degrees of freedom. But more importantly, because you've traced out the environment, you have generated some entanglement which manifests itself in terms of influence functionals. And the crux of trying to derive any low energy effective field theory in this context is constraining these low energy influence functionals completely. And I'll focus on an example where you can think of a probe system, which is basically a scalar field, let's say, coupled to a thermal holographic plasma. And we want to understand what is the effective field theory that I can write down for this probe system after integrating out the holographic degrees of freedom. As someone said earlier this morning, imagine you want to slightly go away from the ADS throat, and you want to think of the dynamics from the point of view of the operators that are taking away from the ADS throat. The trouble is that the answers depend very much on what class of operators you couple in the plasma. So there are two classes of operators. This we know from holography, and here's where the strongly correlated part of the system, of the holographic system is useful. You have, as Steve mentioned, you have operators whose thermal characteristics are dictated by quasi-normal modes, as Veronica Hogany and Gary Horowitz taught us a long time ago. And these plasma operators come in two classes. I'll call one class a Markovian class. These correspond to rapidly decaying quasi-normal modes, where the time scale of decay is set by the temperature. And there's a second class, which I'll call non-Markovian or memory modes, which are long-lived quasi-normal modes, typically associated with critical phenomena in the bulk, either having to do with presence of conserved charges or phase transitions. And these have short, very long-lived quasi-normal modes, though the time scales I'm going to talk about long-lived are not as long as what Steve talked about just moments ago. I'm going to be mostly focusing on, in Steve's discussion, the slope part of the two-point function. So famously, in this context, Polycastro-Son and Starinets showed us that the stress tensor correlator of thermal plasmas modeled holographically have hydrodynamic poles. You see a shear diffusion pole, or if you look in a different channel, you'll see sound modes with attenuation. And these modes, if you try to integrate out, say you couple your probe system to the energy momentum tensor in the thermal path, as you integrate out the holographic thermal path, you'll end up with something non-local in the influence function. So it's not a priori clear what the rules of the game are for writing down such influence phases. Secondly, there's a crucial point here, which is that you also want to understand what are the fluctuations associated with such bulk modes. What are the bulk Hawking quanta from the bulk point of view, and how are they encoded in such effective actions? Now, from a practical standpoint, you could ask this question directly in fluid dynamics, and various groups have tried to address this question over the past decade. I want to sort of put that aside, table that discussion for a moment. I've given references here of some of the salient groups that have worked on this, but I want to come back, ask this question from the point of view of gravity, and ask gravity the following question: tell me what to do. And we'll see very clearly that, as always, gravity is far smarter and will give us the answer. So we need to compute these real-time correlators. The question is, what do I compute them on? That was a question I posed at the very beginning.
And again, this question has a lot of history, but the most updated and cleanest prescription for computing Schwinger-Keldysh correlators goes back a couple of years ago to this nice paper by Glorioso, Crossley, and Liu, who argued that what you compute is since you have two since you have two left and right contours in the Schwinger-Keldysh boundary path integral, you fill that boundary Schwinger-Keldysh contour with a complex geometry. You think of it as a two-sheeted spacetime, where you only keep the domain of outer communication, the future half of the domain of outer communication of two copies of the black hole. So I emphasize that I've drawn the full Penrose diagram of the eternal black hole, but I'm not doing the usual thermophile double construction. I'm only keeping these two shaded pink regions. And I've drawn a cartoon here, which sort of shows how I can think of that as cutting open the Euclidean path integral and gluing a two-sheeted geometry that's smoothly glued across the future horizon. So, but from a practical standpoint, all you can have to say is that there's a you complexify the radial coordinate and define a contour which encircles the horizon, picking up appropriate monodromy factors as you go around. A very clever, nice way to write it is to write it in terms of a complexified tortoise coordinate, and the monodromy you pick up is basically coming from the fact that the horizon function f of r has a simple pole as you encircle the horizon. So this logarithmic branch cut has been normalized to give you a monodromy of 2 pi as you go around the horizon. Okay, so let's table the discussion of non-Markovian modes for a second and ask what happens if you do simple probes, which are fast decaying. Then the story is very straightforward. You have two boundaries. You just impose sources on both boundaries and compute. So it's a double Dirichlet problem as far as gravity is concerned. And in fact, you can actually do this calculation pretty straightforwardly by computing the structure of quasi-normal modes. Compute an infalling Green's function, which sources prescribed on the boundary and falling and sort of regular on the horizon. And you can use this contour to tell you how the outgoing Green's function works by basically using the time reversal inherent in the equilibrium thermal state. I've written out the answer for the bulk field in terms of a combination of the infalling Green's function and something that you might naturally call the Hawking Green's function, because it actually knows about the thermal Bose-Einstein factors if I'm talking about bosonic probes. Okay. And once you have this structure, you just compute directly using Witten diagrammatics the influence phases. And we were able to do this and there was earlier work which completed this in the context of probe strings and Langevin dynamics. But you can package this open effective field theory of the probe into a stochastic effective action with couplings that can be determined exactly from gravity. So I'm not giving you expressions for what the couplings in this effective action are. They're available in a paper. But what I want to emphasize for you is that these couplings obey all the rules of nonlinear fluctuation dissipation relations that you expect for such stochastic systems to have. If you look specialized to simple examples where you can do explicit calculations, say in 2D holographic CFTs, the BTC background, you can actually derive explicit formulae. These formulae that I've given here are given in a low energy gradient expansion, but you don't have to do that if you're working in 2D. And the other important statement I'll make is that there's been various confusion in the literature of open quantum field theories of what renormalization effects are, and the holographic system provides a very clean way to disentangle them and gives you some insight, which was quite useful to understand. Okay, so that's the story for the Markovian stuff. But what about these long-lived modes which have to do with the conserved currents or bulk critical phenomena, and what do we do with them? So the traditional approaches to this problem are complicated by the fact that if you want to say study the dynamics of gravitons, which correspond to boundary energy momentum tensor, you're stuck having to deal with bulk diffeo or gauge invariances. And there are three sets of issues which are closely interlinked, which complicate the discussion and have led to a lot of confusion in the literature. One is that one tends to typically study this problem in some kind of radial gauge where you fix the radial components of the bulk gauge fields or metric to 0. But this radial gauge doesn't play well with the sort of inherent time reversal present in thermal Schwinger-Keldysh constructs. Second, the radial momentum constraint, which is a constraint, it forces, which in a radial ADM evolution, it forces the difference of currents on the two boundaries to be on shell. Now, what this means is that some set of bulk degrees of freedom are being put on shell. So if you're trying to integrate them out, you're going to have issues with the fact that you have put in low-lying Goldstone modes on shell. The third problem, which is closely linked, is that even the energy momentum tensor or any current, it has pieces which are both Markovian and non-Markovian. So it's not like it's just purely Markovian or purely non-Markovian. It's some admixture of both. So you need to sort of disentangle all these three facts. And again, so you ask, how do you do this? And the answer is, ask gravity. And gravity tells you a very clean answer, which is, don't ask the question in terms of bulk components of gauge fields or matrix. Just ask the question directly in terms of gauge invariant bulk variables. So if you, for those of you familiar with cosmology, it's the same kind of discussion you would have where you talk about gauge invariant variables in cosmological perturbation theory. So for the stress tensor, I'll just say the answer, what happens, you can just parameterize the stress tensor in terms of transverse stressless vector and a scalar part, and these parts are decomposed with respect to rotations perpendicular to the direction of momentum transfer. And surprisingly, this A decouples all the Markovian and non-Markovian degrees of freedom. B, it actually tells you that each of these components can be described in terms of an effective scalar, which has characteristics defined as follows. Markovian modes have a coupling to gravity that's growing as you go to the boundary, whereas non-Markovian modes are very floppy and their coupling sort of decouples as you go to the boundary. It's a very closely related story to probes of hyperscaling violating backgrounds that people have studied in the context of ADS-CMT. But I'll just advertise that there's a very nice universal template that gravity gives you, that all these non-Markovian modes can be modeled as effective scalars proper in a coupled to some background dilettante. So effectively, every problem that we've encountered so far can be packaged into a class of scalar fields, no mass, but with a coupling that is modulated between the horizon and the boundary. And in fact, all that matters is not the precise nature of the coupling, which enters into the actual coefficients in the Schwinger-Keldysh effective action, but rather how the coupling behaves as you go towards the boundary. So this parameter M that I've defined here basically demarcates the range of Markovian and non-Markovian fields. Fields with M greater than -1 are Markovian, fields with M less than -1 are non-Markovian. And I've given a table here of various components coming from gauge fields and gravitons in various examples that you can sort of decide. You can basically compute whether they're Markovian or non-Markovian. But gravity also tells you something more. It tells you that because these non-Markovian modes are floppy near the boundary, you should quantize them with different boundary conditions. In fact, if you directly take the decomposition of in these polarization modes and plug them into the Einstein-Hilbert action with the Gibbons-Hawking boundary term, you are told naturally by the dynamical principle that these non-Markovian modes should be not satisfying, not quantized with Dirichlet boundary conditions, but with double Neumann boundary conditions. Okay. In other words, you shouldn't integrate them out. Rather, you should keep their field values and not their sources. So you don't compute the generating function of the non-Markovian modes of correlators, but rather compute their Legendre transform with respect to waves of the non-Markovian operators. And this is an input that comes straightly out of the gravitational action. This I emphasize because this causes some confusion. People say that you could, are we imposing these boundary conditions by hand? The answer is no. This is an input coming from Einstein-Hilbert gravity plus boundary terms. And various earlier works have made these observations. But as far as I know, this is the first time that we were able to see this directly from the point of view of the bulk dynamical variational principle. So, in other words, what gravity instructs you to do is to compute something called what we call the Wilsonian influence phase, where you turn on sources on the two boundaries for the Markovian fields and waves and for the non-Markovian fields, and compute this Wilsonian effective action. And I'll just flash here the answer for the stress tensor dynamics in n equals 4 super Young mills. This is a problem that I mentioned, because has a rich history going back 20 years. And here's an action that comes out of this discussion. So I've broken this up into polarization data. So the tensors are characterized in 4 dimensions by 2 polarization boundary sources. This is Markovian. The vectors are characterized by 2 polarizations, and this is the momentum flux. And the sound mode is characterized by a single mode, which is basically the sound field in the bulk. And the action has these 4 pieces plus non-Gaussian terms I'm not writing. And there's a piece which comes from the fact that the black hole solution has background free energy. So this is the background pressure term, which corrects itself into a sort of what in a paper about 6 years ago we call class L hydrodynamic action. So you could reproduce that on the nose from gravity. There it was conjectured based on input from quasi-normal modes and fluid gravity, but here you can sort of just derive it from the bulk directly. And then the bulk action for the remaining terms is basically some structure of the kind I showed you before for the Markovian fields. Since I'm just writing Gaussian terms, there's a piece which is a retarded propagator corrected by appropriate Bose-Einstein factors to give you fluctuations. So the one term gives you the retarded Green's function, and then fluctuation dissipation tells you that the fluctuation is given by Bose-Einstein factor times the retarded Green's function. And here are the expressions to quadratic order in gradients for the retarded Green's function for the Markovian part and the inverse Green's function for the non-Markovian part. This 0 of this inverse Green's function basically tells you where the shear dispersion relation is, recovering the famous result of eta over s is 1/4 pi. And you can do more, you can do sort of other modes in the problem, and other people have also commented on deriving this effective action in previous discussions. So this is what you get if you start by inputting into the discussion this complex geometry. So in the remaining few minutes, I want to tell you a little bit about how you can justify these complex geometries as appropriate saddles. So this is some work I had done previously with Aitor Lefkowitz and Ji Dong, but more recently I've been working with my student Sean Colin-Ellerin and folks from Santa Barbara, and which came out in these 2 papers. So here I'm going to generalize the discussion and look at one for the case of sake of discussion. I'm going to generalize it by allowing non-trivial spatial dependence. So I'm sort of taking one piece of this bracket piece that shows up in the replica contour and showing you the time evolution forward and back in the ket and the bra, but also indicating spatial information so that if I want to compute reduced density matrix elements, I can cut open this path integral, impose boundary conditions on the cuts, and compute appropriate boundary reduced density matrix elements. Once I have these density matrix elements, I can compute Renyi entropies by doing boundary replica trick. And so the contours will look similar to this, except that there is spatial information in terms of where the cuts, which parts are glued, which bras and which kets are glued to which ones. If you take this boundary contour, you can write down an ansatz for the bulk geometry, where your boundary contour, your boundary Cauchy surface is extended into some bulk Cauchy surface with the entangling surface extended into a codimension 2 splitting surface. And there are a couple of interesting regions, causal domains in this region that I want you to focus on. So associated with the region A in the boundary, there's a homology surface, which is an extension of the piece of the bulk Cauchy surface that is connected to A. The entangling surface extends into a splitting surface, which I said is a codimension 2 surface, and it extends out in the boundary, into the bulk. The past domain of dependence of the homology surface, I'll call the homology wedge. This, if we're talking about entanglement entropy or von Neumann entropy in a fixed background, this would eventually become the entanglement wedge, but for now it's just, or the path of the entanglement wedge, but for now it's just some piece in the ansatz. And then there is a causal path of the splitting surface, which would be important, which I've called the Milne wedge. So you take this ansatz, and then you ask gravity to do its job. You glue various pieces of this ansatz together as dictated by the replica construction. So kets and bras of the same density operator are glued in the complement region, and kets and bras are glued cyclically between different replica copies. So I'll just focus on replica symmetric saddles, and a priori just declare to you that you have to have complex Lorentz signature metrics, because if you look at what the splitting surface is doing, it's a codimension 2 space-like surface, but it's normal, being has a time-like component, but it has to switch directions between going from one replica to another, and that it can't do in a smooth fashion in a Lorentz signature geometry. In fact, the discussion of what it needs to do can be understood by looking at the splitting surface and working in a Gaussian normal chart around the splitting surface, as was emphasized in the Euclidean discussion by Lefkowitz and Maldacena. And I've adapted to the Lorentzian normal bundle light cone like coordinates. I've put tildes here because these are light cone coordinates that are positive in the space-like domain. And all you need to know is that the metric is smooth and real in the homology region, in the homology wedge, but it's complex in the causal past, if I'm talking about a ket, or causal future if I'm talking about the bra, of the splitting surface. And you can give analyticity conditions in terms of these light cone coordinates that the metric in the local neighborhood of the splitting surface depends on fractional powers of these light cone coordinates, but in a manner that's analytic, explicitly coming from replica symmetry in the first two of these combinations. But what's crucial is that as you cross the light cone and go from the homology wedge to the Milne wedge, this combination in light cone combination has to cross the light cone, and the light cone coordinates cross the light cone, and you have to pick up branch cuts which you have to regulate by an I epsilon prescription. Okay, so the I epsilon prescription.
Sorry to interrupt. Mukund, sorry to interrupt. You're at the 25-minute point. Yeah.
Thanks. I'll be done in precisely 2 minutes.
Okay.
So there's an I epsilon prescription that one can give, which has also been discussed in this recent paper by Goto et al. And with that I epsilon prescription, you can just compute in the bulk path integral in stationary phase and show that the effective action, the on-shell action which computes the entropies, is given by the imaginary part of the gravitational action. Why is there anything imaginary? The answer clearly has to do with the fact that we are jumping light cones. So there's a piece that comes from crossing the light cone of the I epsilon prescription. But more importantly, the real part, which would have given you a pure phase in the gravitational path integral, cancels between bras and kets. So there's the net answer is purely imaginary. You can understand this, as was pointed out a long time ago, by a suitable complexification of the Gauss-Bonnet theorem. In fact, by putting appropriate regulators around the splitting surface, you can prove that the Einstein-Hilbert plus Gibbons-Hawking term evaluates to a purely imaginary term proportional to Euler character of this half disk times the area of the splitting surface. So I'll just flash this slide because this was a tour de force computation that my student Sean Colin did, which is to basically use this technology to reproduce some results that were computed in the Euclidean context by Tom Faulkner for computing Renyi entropies in holographic 2D CFTs for multiple disjoint regions. I've just drawn here 2 disjoint regions, which are labeled by their endpoints. And what I've done is also I've relatively boosted these 2 regions with respect to each other. And this is one important example because although you can write a single Cauchy surface that sort of straddles these joint regions, which is space-like, the corresponding bulk geometry is you have to actually compute an extremal surface to get the bulk Rene and bulk von Neumann entropy, and therefore this is a good test of the Lorentzian prescription. In this case, you can actually do the computation by basically working in Pfeffer and Graham coordinates, where the only piece of data you need to know is how to build the branched cover of this double cut plane in the boundary. And I'll just say in interest of time that the computation can be done and you reproduce the answer quite beautifully. In fact, the answer can be obtained in 2 lines if you use the complex Gauss bonnet here. Okay, so in fact, all I need to tell you is that the physical answer depends on how much energy you need to put at every branch point where the twist operators are placed to close the boundary into an appropriate Riemann surface if you're working in Euclidean space. And the variation of the Rene entropy with respect to the endpoint is simply captured by the amount of energy you put at that point. So I just flashed for you in the last half an hour progress we made in understanding real-time gravitational path integrals in 2 different contexts. And I think there's a lot more to do. And in particular, many questions that have been discussed in earlier talks and should be better understood from the point of view of this real-time dynamics. So with that, let me stop.
Okay, thank you. Thanks a lot, Mukund, and thanks for keeping to time. Floor is open for questions. I don't see any hand up yet. Oh, Juan has his hand up. Juan, sorry, please go ahead.
Yeah, I have a question. So the way you described the real-time gravitational replicas, it sounded like you were doing this on the original geometry, but maybe I was confused.
No, so that's why I
expect that the replica would involve a different geometry. Okay, go ahead.
Yes, you're right. So I mean, I was too fast on that one. That's why I said this is an unscience. We still have to solve the bulk equations.
Mm-hmm.
Okay, so.
Okay, and then the geometry is modified both in the homology wedge and it's modified everywhere, right?
Correct. Okay. It's exactly like what you would expect by putting. So you could do the exact same calculation that you and Mathur did by imagining that you put here a cosmic brane of some tension and allowing that to back react. But the key point is that there's a well-defined variational problem, which you can, with boundary conditions that are prescribed in the Lorentzian context.
Okay.
So your discussion had an advantage that you could say the covering space was smooth and smoothness was clear what it meant. And so all I'm saying is that analogous notion is an appropriate analyticity statement in these light coordinates.
Okay.
I see. Okay. Any other questions? I don't see.
Jensen has a question.
Can I ask a question?
Sorry?
Yeah, I have a question.
Please.
Mukund, could you remark on why the geometry was real inside of the what you call homology wedge?
Yeah, so physically, the way I think about it is that this is, so let me give you the sort of heuristic answer, which you can justify. The homology wedge is basically coming from the Euclidean section. It's purely space-like with respect to the boundary description. So here, you could just take the Euclidean answer and continue. So it's like saying, if you want to, for example, think of CFT correlators. If you want to get real-time correlators, you could just analytically continue. But the CFT correlators are guaranteed to agree with the Euclidean correlators in the corresponding Euclidean domain. And the homology region is precisely that Euclidean domain. So all the non-trivial action is crossing this light cone.
Maybe is there something interesting if I, for example, put this twist operator to be, instead of space-like, to be time-like?
You want to compute some 2-point function of twist operators that are time-like separated?
Yeah, yeah.
That's a good question. I think it can be done, and it's probably related to discussions that people have had in the past of computing what are called, the name escapes me, but it's related to the discussion of geodesic Witten diagrams. I'm sure one can make a statement, but I haven't thought about it to give you an immediate answer. Maybe someone else does.
Because in that case, the naive gamma will be complex, right?
Correct. Gamma would have to be, that's correct.
So I accept.
Yeah.
I think Henry has a
something
question.
in the same vein as Jemin's question, but slightly simpler, is not to compute time-like separated insertions of twist operators, but have a splitting surface and then have some other operator insertion to the future of the splitting surface. So far you've described the geometries all to the past of the splitting surface, but if you wanted to insert some operator that was just maybe a probe thing that's not going to back react to the future, is that something that's straightforward to describe, extending the geometry to the future of the splitting surface?
I mean, so we'd have to do the following. If you want to compute correlators of operators in a state at a time later than where the state has been prepared. So here I'm preparing the state on this Cauchy slice, right? In the boundary or in the bulk, I'm preparing it on a single Cauchy slice. If you tell me how to evolve the boundary to that time, let's say you inserting no other sources, I just do standard Hamiltonian evolution, and then insert the operator, then I think we can do the corresponding bulk statement and do exactly what you're asking.
Yeah, so the thing I had in mind was you have some initial state, you evolve it forward in time, you insert some twist operator, you evolve it forward in time again, you insert some probe operator, and then oh, I guess you have to I guess this is different if you're, whether you insert that
you have to tell me something
on
about
one sheet or another on what the time ordering is, but okay.
Correct, exactly.
Okay, we're actually out of time, but there's one more hand, and since it's the last talk, let's anyway take the question, but then that would be the last. Alexei, go ahead.
Thank you. Can you hear me well?
Yeah, I can.
Yes.
Yeah, my question is about possible applications. So in the recent years in condensed matter literature, people discuss this phase transition when you couple your quantum system to an external one and essentially perform a series of measurements. So this is like an example when you have an open quantum system, and they see a phase transition depending on the rate of these applied measurements. So have you thought about analyzing this setup using your techniques?
I think it can be done. So to be honest, I mean, there's something I have been thinking about with a student in Davis, Frederick Gia, which is to do correlated noise systems, which would pick up something of the kind you're asking. So you have two probes in an environment, and you ask how does the noise correlate them. It was partly inspired by something along the lines you're asking, which is to think about random tensor networks and doing projective measurements at various nodes of random tensor networks to prepare the random tensor network, which gives you cross correlations. The one issue I have is that it requires us to be a bit more careful about what other geometries and saddles contribute. And I don't have a full answer for you yet, but I think in principle, my tentative answer would be yes, you can do it. But once one understands not just the Schwinger-Keldysh contours, but also perhaps OTO-like contours or replica Schwinger-Keldysh type contours, if that makes sense.
Okay, yeah, I see. Thank you.
Okay, I think we'll have to leave it there. Thanks a lot, Mukund, very much. Let's all clap and thank Mukund. And I hand over to Nathan and the organizers for any last words they have for today.
Okay, so thanks very much. So we'll meet again tomorrow. Just for people who had some problems with the sound on the videos from the first day, they've been replaced. So the videos on the first day should be okay now. Okay, so we look forward to seeing you all tomorrow morning.
Thank you. Thanks a lot.